Okay, I think we're back to live. Can I get a live in the chat or a 10 out of 100 in the chat? Yeah, we're back. Okay, welcome back everyone to the Weather and Climate live stream. We are, it says we're only 1 minute in, but we're actually 10 hours and 1 minute in. And I am Henri Drake. I'm an oceanographer and climate scientist, and I have with me my co-host, who is now going to be the solo host for the next few hours. Is it Marie McGraw?
Yeah.
Okay, sorry, saying your name wrong last time. And I'm welcome to the stream.
Great. Happy to take over. I know it's pretty late on the East Coast, but those of us farther west, you know, the night is young.
I'm in California too, but I'm tired, so I'm going to head out.
Why did I think you were in New York?
All right, thanks for taking over, Marie.
You've still been doing it for 4 hours. All right, so as Henri said, we're finishing up with hour 10, so we've got about 90 hours to go this weekend. So in the next hour, we have two exciting talks. We'll be hearing from Nina Oakley about rainfall forecasting for decision support in post-fire debris flow areas. And then we'll hear from Martin Wolf about air quality and cloud formation. So before we start with the next talks, just a quick reminder of why we're all here. High quality weather and climate forecasts are essential for everybody. They affect us on a personal level, like choosing which shoes you might wear to work today, or deciding whether or not it's safe to go hiking the next day. They also affect us on big nationwide and international scales, affecting systems like agriculture, urban planning and architecture, transportation, and supply chain logistics. The U.S. has long been a global leader in weather and climate forecasting. As an example, U.S. scientists led the development of not only one of the first programmable computers, but they used this computer to produce the first computerized weather forecasts, so innovating in sort of two fields at once. And in subsequent years, U.S. scientists have improved global weather and climate predictions by investing heavily in weather satellites, radar, on-the-ground observations, weather balloons, radiosondes, planes and ships that observe weather and climate in remote regions, and more recently, unmanned vehicles and things like the Argo floats we just heard about. So the strides we've made in weather and climate prediction in the last 75 plus years have been incredible, and they've been supported by the American public through our public science institutions like NOAA, like NASA, like the National Science Foundation, and so on. But in the last few months, we've seen that the scientific enterprise in the U.S. has been put at great risk. Things like National Weather Service offices that are so short-staffed that they are reducing their observational coverage and balloon launching, which hurts our weather forecasts. Weather and climate labs dedicated to understanding our planet's future have been closed abruptly or severely limited in funding. So if this worries you, or if other cuts to U.S. science and research worry you, please contact your representatives using the link on your screen and tell them to save our forecasts, keep the lights on for weather and climate science, and talk to your friends and family about this too. So we hope that in these talks that you learn something new and fun about weather and climate, and please post any questions you might have for our speakers in the chat. And finally, just a reminder that all speakers, hosts, and volunteers are appearing in a personal capacity and are expressing their own personal views, which may or may not be the views of other participants or of the places where they work. So without further ado, we're going to hear from meteorologist and climatologist Nina Oakley about probabilistic rainfall forecasting for post-fire debris flow hazard decision support. So whenever you're ready, Nina, take it away. You're still on mute, Nina.
So great to be here, and thank you so much to the organizers for all your hard work, and everyone who's listening in and making this event, getting the word out. So I am a geohazards climatologist at the California Geological Survey. So, and what this means is I'm a meteorologist and climatologist who works in collaboration with geologists, hydrologists, and engineers on rainfall-driven geohazards such as landslides and debris flows, both outside of burn areas and within burn areas. And I should note for folks that aren't familiar that that the California Geological Survey and other state geological surveys were separate entities from the U.S. Geological Survey, but work in close collaboration with them, and that geological surveys are major users of weather and climate information, especially precipitation information. And so it's really, we're going to go way more into watching the previous few talks were really on the climate side, but we're going to go a little more into the weather side and be talking about 15-minute rainfall intensity in this presentation. So I think it's really cool following the climate folks to see the scope of this work that we do under meteorology and climatology. But what I will be talking about today is work I did with a multidisciplinary and interagency team. I'm going to be speaking to a publication that was published in the Bulletin of the American Meteorological Society, and the link is there, to explore ways to improve decision support for post-fire debris flow hazards using ensemble rainfall forecasts. And if you don't know what those terms mean yet, you will after the presentation. And this project demonstrates the value of the meteorology community collaborating with the geohazards community to advance the warning of geologic hazards. And this work was supported by the NOAA National Weather Service through the Sea-Star program, as well as the California Department of Water Resources. So the goal, we had several goals in this work, and the first was to provide a primer on what post-fire debris flows are. So you'll get a bit of that today if you're not familiar. And what we present in this work is a conceptual framework for taking rainfall forecasts, ensemble rainfall forecasts, which we'll talk about in a minute, and integrating them with post-fire debris flow hazard models, and then looking at how to process and visualize the output so it can be used by decision makers to make decisions around hazard areas, evacuations, and things of that nature. And we're going to use the 2018 Montecito debris flows that occurred on the Thomas Fire in Southern California. There's a picture of some of the impacts from that event on the right-hand side of the screen there. We're going to use that as the test case for this work, and in this event, a very impactful post-fire debris flow event where 23 lives were lost and roughly $1 billion in damage occurred. And so the point of this study is not an evaluation of how well the forecast models performed for the event, but rather to explore the feasibility of integrating these rainfall forecast models with post-fire debris flow models to provide better decision support. So for those who aren't familiar with post-fire debris flow hazards, so following a wildfire, when steep terrain is burned at moderate to high severity, it may experience runoff generated debris flows in the first few years following a fire. So these are, the fire reduces or removes the vegetation from hill slopes. And so now when raindrops fall, they are making a greater impact on the ground and can start to loosen material. And you also may get a hydrophobic layer developing in the soil. And if you walk around on a burn area right after a fire, you'll hear, especially in Southern California, you'll now that the soil has been changed by the fire, you can hear the soil particles moving downslope into the channels and loading up the channels with sediment that can then be flushed out when rainfall occurs later. And so when we're talking about post-fire debris flows, the short duration rainfall is really critical to trigger these rather than storm total rainfall. So we're thinking about hourly or sub-hourly, with the 15-minute rainfall intensity really being the best predictor of post-fire debris flow activity. So this is rainfall at the really short duration. Storm total rainfall, we don't see a great relationship between that and post-fire debris flow activity. And during periods of high intensity rainfall, the material can be scoured off of the slopes into the channels. Any material that's already in the channels can be moved down slope and produce a potentially damaging post-fire debris flow. Antecedent rainfall also isn't necessary. This is different from shallow landslides that occur after prolonged rainfall. Post-fire debris flows can and often do happen with the first intense rainfall following a wildfire, which sometimes, in the case of the Montecito event that we'll use as an example, sometimes these events are occurring before the fire is considered totally contained. So the U.S. Geological Survey has developed a model that's used to indicate where in a burn area post-fire debris flows are likely to occur based on the factors such as the soil burn severity, the steepness of the terrain, the erodibility of the soil, and the rainfall intensity. And so let's take a look at that model. So this is an example of the USGS model output for post-fire debris flow likelihood for that for the 2017 Thomas Fire, where the 2018 debris flows occurred. And this model is widely used in the U.S. for emergency planning post-fire, and it provides information on debris flow likelihood at each one of those small basins that are delineated on the map there for a given rainfall intensity. So the example I'm showing here is for a 15-minute rainfall intensity of 24 millimeters an hour, which basically means receiving about a quarter inch of rain in 15 minutes. And so you can see there's some areas of the burn area in the north and west side of the burn area that had a higher probability of debris flow than the southeastern portion of the burn area. And this model output is really critical for identifying high hazard areas and is used to inform the development of fire-wide debris flow thresholds that are then used operationally by the National Weather Service. However, this map is static, and so it just gives you the likelihood of debris flow across the burn area at that fixed rainfall intensity. And we know that in reality, on a large fire like this is about a 280,000 acre fire, and there's very complex terrain. The San Ynez and Topa mountains run east to west along there. That peak rainfall intensity in the storm is highly variable in space. So our work explores the feasibility of using this likelihood model to vary the rainfall intensity input into the likelihood model for each basin based on a weather forecast. So this is once these fire-wide thresholds for triggering rainfall for debris flows are developed, National Weather Service forecasters will watch the forecast to determine the potential that the incoming rainfall will exceed that threshold somewhere on the burn area and potentially produce debris flows. And so, though that 15-minute duration, as I said, was the best representation of initiating post-fire debris flows, hourly forecast information tends to be used in practice as it's more widely available in operational forecast models and weather stations. So this is an example of messaging for a fire from the National Weather Service in San Diego to their partners. For this fire, the rainfall threshold was half an inch in an hour, and then they indicate that it's likely to be exceeded in those two windows of the forecast period. And so, well, these types of communications, and this is a particular format that the San Diego office uses. Not all offices have the same sort of product to communicate to their partners. So, well, these types of communications will continue to be important. As the science advances, we want to look at how we can enhance decision support and provide more detailed information. So what we're exploring here is integrating rainfall forecasts with the USGS models to create tools that provide spatially explicit information and uncertainty quantification. And we do this with the Thomas Fire example. So we're working with this 9th of January 2018 post-fire debris flow event on the Thomas Fire, and I'm showing you a radar image from that event. And so if you're not familiar with radar imagery, we've got the coastline in a very light red. You can see the outline of the Thomas Fire burn area. We're in Southern California at Santa Barbara and Ventura counties is where the burn area spanned. And we've got this narrow band of high intensity rainfall that was present along the storm's cold front. And so yellow and red colors are higher intensity rainfall, and then green is lighter intensity rainfall. And so we want to run a forecast representing this band of high intensity rainfall passing over the burn area. And it's only a few kilometers wide, this band, so it requires us to use high resolution or mesoscale modeling. And so we set up and run a mesoscale model, and to represent the uncertainty, we know there's challenges in forecasting these very small bands of high intensity rainfall. And so to represent the uncertainty we know is present when we're modeling these features, we run a large 100-member ensemble for this storm event. And if you're not familiar with an ensemble forecast, this is where I've got a little diagram in the bottom here that's a schematic that shows how an ensemble forecast is where we run the forecast many times with slight perturbations to the inputs to the forecast to create a spread of potential forecast outcomes. And so ideally, you capture the event that actually happens, the rainfall intensities associated with that in the spread. And we did, in our case, we did capture the observed rainfall in our ensemble spread. However, it was at the high end of the distribution. And we ran this model out at a 24-hour lead time, as that's a lead time that we found useful to decision makers to have information at that time to decide on things like evacuations and road closures and things of that nature. So we'll take a quick look at how our model performed. So these histograms show the ensemble spread at the location of 2 rain gauges where debris flows occurred in the event. So we've got the rainfall intensities along the bottom in millimeters per hour, the peak 15-minute rainfall. And so there we've got all 100 binned into different rainfall amount bins, and this is at two different weather stations that were in the area that experienced debris flows. And we see that the ensemble mean, so the mean of those 100 simulations that we ran, is much lower than you see the vertical line for the observed for both weather stations. So ideally, we'd like the ensemble mean to be closer to the observed rainfall. That would give us higher confidence in that outcome. But in this case, we have the observed much higher than the ensemble mean. So this situation highlights that consider the value of having an ensemble and considering the full spread, as the observed values could be, in this case, we're at the higher end of the distribution for this study. So now let's use that forecast model output as an input to that post-fire debris flow likelihood model and see what we get. So we've got our ensemble forecast, and we can link that with the likelihood model and start producing some informational figures. And so for each basin on the fire, we can take the storm maximum, the ensemble mean peak 15-minute rainfall intensity, and use it as an input to that likelihood model rather than using the static value that we saw in the earlier slide. And then so that's what's shown on the left-hand side is if we input that 15-minute rainfall intensity along with the other variables such as the steepness of the terrain, the soil burn severity, the soil erodibility. And then on the right-hand side, we're looking at the standard deviation of those 100 ensemble members. So this tells us about how uncertain was the likelihood of debris flow. And so I've put a black box around the area where we had the most impactful debris flows. Now there were also debris flows in all the area with the dark red on the northern side of the fire, but that's more remote area where there weren't as many impacts to humans. So got a square around the Montecito area. And so, well, just using the ensemble mean, we still get high likelihood of debris flow occurrence. It's also the area where we have some of the greatest uncertainty, which presents challenges in for decision making. And we also know that the ensemble mean was low compared to the observations, but in this area, even using the ensemble mean, we're still seeing high likelihood. And so for brevity, I'm just showing one example, but we could do the graph on the left. We're using the ensemble mean. We could do the ensemble 75th, 90th percentile, et cetera, to give more insight. So, and another thing we can do when we have a large ensemble like this is we can look at the number of ensemble members exceeding some value. So we can compute a rainfall threshold for each one of those small basins, and then we can we know that the thresholds for initiating debris flows, that the thresholds that we're using are for initiation of any debris flow, but for the major destructive events, they may be multiple times over threshold. And so we can look at, on the left, how many ensemble members said 1 time over the debris flow threshold. In the center, how many 2 times over the debris flow threshold, or on the far right, how many members said 3 times over threshold, to give insight to where there's the greatest potential for major events. And again, we know that the ensemble was that our observed values were at the tail end of the ensemble distribution, but we still do have several members showing 3 times over threshold in that highlighted red area where we had impactful debris flows occur. So to wrap up, yes, we successfully demonstrated a conceptual framework for integrating ensemble rainfall forecasts with post-fire debris flow likelihood models and volume models, which we talk about in the paper but are not shown here. One of the limitations that we face is the uncertainty in the precipitation forecast and the time it takes to run this large ensemble. And we can overcome this by evaluating and optimizing the model setup for that large ensemble forecast for these specifically for post-fire debris flow events. And another challenge is that the debris flow likelihood and volume models are really well developed for Southern California, where the most data has been collected, and for the first year after the fire. And so we still need to do more data collection in other places outside of Southern California, and improve the models for out years after the first year that typically has the greatest susceptibility. But a lot of progress has been made in the last couple of years to collect data outside of Southern California. And the field's also making strides in debris flow runout and inundation modeling. So not just whether the likelihood of a debris flow occurring, but also the where it's going to go and how deep the deposition will be. And so we hope to continue to work with others to keep developing these tools, and also evaluate the effectiveness of these tools and visualizations for decision making. We did not, we just presented this framework, but we haven't gone out and worked with social scientists and worked with end users to determine whether these are the correct visualizations, if there's better ways we could communicate this information. And in order to advance our ability to forecast and communicate information about these damaging events, it's really valuable to continue to have the support for interdisciplinary collaborations between meteorologists and climatologists in the geohazards community, and interagency collaborations. So with that, I thank you very much. And if there's any time for questions, I'm happy to take a question.
Yeah, thanks so much. That was an awesome talk, Nina. I love weather and geology, so it's really
great.
Thanks also again to our organizers, and also to all of our viewers who are spreading the words. I keep seeing in the chat people posting about this in various other places on the internet, so that's awesome. Thanks so much. All right, so we're halfway through hour 10. We've got 89 and a half hours to go. And again, we're here because we care about weather and science, and we know that we need good weather and climate predictions to function as people and as societies. As another example of ways in which the U.S. has been showing a leadership role in weather and climate is our satellite program. The U.S. put up some of the very first weather observing satellites in the 1970s, the very first GOES, geostationary weather satellite. And we've been kind of leading the world in global satellite coverage ever since. But these programs are also at risk for from these funding cuts, and satellites like those, they do more than just tell us weather. They're also really important for things like GPS. So if you want to be able to like record your run and know how far you ran, you need satellites. So again, if you are worried about the cuts to weather and science, please click the banner, call your representatives, and talk about this with your friends, your family, and your community. Spread the word. So hopefully you learned something new about fire, rain, and debris flows. And in our next talk, we're going to talk about air quality and clouds. And again, post any questions you might have for our speakers in the chat. And finally, our disclaimer that all speakers, hosts, and volunteers are appearing in a personal capacity and expressing their own personal views, not the views of any employer they may work for. So with that in mind, our next talk is going to be by Martin Wolf. And Martin Wolf will be, as an atmospheric chemist, who will be talking to us about air quality and cloud formation. So we're going to go in a little chemistry direction. So Martin, whenever you're ready, feel free to hop on. All right.
Hello, everyone. I am going to upload my PDF of slides. Here they are. Great.
Seeing some
Thanks.
excitement in the chat for chemistry. So yes, it's chemistry time.
I would say it's always chemistry time, but it's also always time for all the sciences. Looks like my slides are processing. But what I'll say is that the title of my talk, which looks like it's gonna show up here, is It's Up in the Air. And the reason it's called that is twofold. One, I am an atmospheric chemist by training, so everything I study is up in the air. But two, due to budget uncertainties and research funding uncertainties, my research is also very much up in the air and not in the way that I would like. So in case you're just joining in, or in case you have been living under a rock for the past couple of months, here's a dispatch from the world of climate funding research. And that is that climate funding is under attack. And this is clearly bad news for people like me and several of my friends who have lost their jobs because of the attack on funding. But it's also bad news for you. If you've ever opened up your weather app on your cell phone, or if you care about protecting you and your loved ones from stronger hurricanes or crazy wildfires, you should care about the funding for weather and climate research that me and all of my colleagues are presenting on during the course of this wonderful live stream. And this should definitely alarm us. But I just want to start off my talk by saying thank you to the organizers for bringing everyone together to give us a chance to talk about the research that we're doing, but also bringing together our broader community to be able to learn about how the research that we are doing as a community is critical to protecting the health and safety of everyone around the world. So here we are, the next 20 minutes of your life, if you're tuning in. I'm going to start with just a few slides on who I am, because I think it's important to know the person behind the scientist. And then I'll talk about different sources of air pollution, in particular, particulate matter or aerosols up in the air, which is the type of pollution that I study. And then, since it's getting nighttime in most of the United States, I'm going to take you on a quick speed date where I'm going to introduce you to some of my favorite clouds. And then you might think, well, air pollution and clouds, are they related? Well, I'm here to tell you that yes, they are. So I'll conclude the talk by talking about how air pollution impacts cloud chemistry and how clouds form and precipitate and impact Earth's climate. So here I am. I got my PhD in climate science and atmospheric chemistry from MIT in 2020. This is a picture of me hovering above my cloud chamber. So that's right, we can make our own clouds in the lab to study them in controlled environments. And I was constantly thinking about clouds. So here's a cloud inside my my thought cloud here. I then did what's called an American Association for the Advancement of Science, AAAS Policy Fellowship, where I worked at the Environmental Protection Agency here in the United States on their climate policy branch. And this branch had two mandates. One was quantifying all greenhouse gas emissions across the United States. This is something that's required of the United States under the United Nations Framework Convention on Climate Change. We also worked with developing countries to help them better mitigate their greenhouse gas emissions and really adapt to climate change. And it was a real pleasure to be able to work at the EPA for a year to help people around the world address the climate crisis. Up until very recently, I then worked for the Intergovernmental Panel on Climate Change, or the IPCC. So the IPCC, you can read here, was created to provide policymakers with insights into the science that researchers like myself and my colleagues here are doing. We firmly believe that good policy should be based in climate science. And that's exactly the point of the Intergovernmental Panel on Climate Change reports. So you can see here down at the bottom, the reports are broken up into a couple of different chapters or reports. One is the kind of science of climate change, the physics and the chemistry. Other reports focus on how we adapt and how we respond to climate change. The part of the report that I was working on was that third one, which is mitigating climate change. In other words, reducing greenhouse gas emissions. Now, all of these are ultimately compiled into what's called the Summary for Policymakers. And again, this is an opportunity for policymakers to base their decisions in the latest research that my colleagues and I are doing. Now, due to recent funding cuts, I and several other climate scientists working for the IPCC lost our jobs, which again is, it's sad for me, but that's not why I'm here to complain about that. I'm here to let you know that US scientists, more broadly speaking, are now being prevented, or due to budget cuts, they're less able to participate in IPCC processes. And that's a real shame, because the United States has some of the world's leading climate scientists. And we want US climate science to be able to make it into these reports to keep you and your loved ones safe. Okay, so you made it through my biography. Congratulations. Now let's get into the science. I'm wearing the bow tie for a reason. I want to talk to you about different sources of air pollution. So Earth scientists generally love to look at pictures of Earth from space. Now here's one. Oceanographers love pictures like this because it shows that there's a lot of ocean on planet Earth. When I look at pictures like this, though, I get really sad because something is clearly missing, and that's the atmosphere. This, with all the clouds introduced, is what a picture from Earth from space really looks like. But thanks to a lot of the research, especially my modeling colleagues here, we also have other ways of knowing what's up in the atmosphere. So this is model output from the NASA Goddard model. Shout out to all of my Goddard colleagues on the calls today. That show different kinds of particulate matter, or different kinds of aerosol particles up in the air. Now, this isn't a picture of Earth from space. Don't get me wrong that there is in fact some false color here, but it just goes to show how much stuff is up there in the atmosphere, kind of between us and the satellites that are looking down. We can see that there's dust, there's biomass burning, there's sea spray. There's also these sulfate aerosols, and these come from burning fossil fuels. So there's all these different sources of particulate matter, like the ones we just saw. But one thing that they all have in common is that they're really bad for human and environmental health. when we talk about air quality and human health, poor air quality is actually the 4th leading cause of early death around the world. 90% of people around the world breathe air with unsafe levels of particulate matter or aerosols in it. And huge numbers of people die prematurely. So even, ignoring weather and climate for a second, we can tell it's really crucial that we continue to study atmospheric chemistry from a human health perspective. But aerosols also impact climate, and thus they impact our health in other ways. Some of you are familiar with this graph already, but there are many things that are warming and cooling the Earth's climate. Our well-known greenhouse gases are exerting a warming impact on the Earth's climate. But you can see over here to the right, there are ways that aerosols are warming the climate and ways that aerosols, or these particulate emissions up in the air, are cooling the climate. Now, they're not offsetting all the warming from the greenhouse gases, so Earth's climate is still warming. But hopefully this just goes to show that there's incredible complexities here. And in fact, the complexities are so great that we still don't fully understand climate change. We know that the Earth is warming, but we don't know exactly how much and what the drivers are. This goes to show that we need more research into what's happening here. So you saw in the previous picture that aerosols are both warming and cooling the climate. Well, what's going on there? Well, there's some really dark aerosol particles that absorb sunlight coming into the atmosphere and warm the atmosphere. But on the other hand, there's brighter, more highly reflective aerosol particles that are up there that are reflecting the sunlight or scattering the sunlight back towards space. And these have a cooling impact on climate. And this is kind of the two end members, really white, really black and dark and absorbing. I like with classes that I teach, I like to throw up this slide and have people just kind of think about all the, there's a whole rainbow of aerosols up there that are having different impacts on climate. So maybe you can think of a few different colored aerosol particles that are having different climatic impacts. Ones that come to my mind are kind of a reddish orange desert dust coming off of the western coast of Africa. We have pollen. This was basically a live view from Washington, D.C. today, where we had all this pollen coming off of everything that's in bloom in Washington, D.C. spring. We have sea salt aerosol or sea spray aerosol. Even though the ocean's blue, the sea salt is quite bright and reflective. On the other end of the spectrum, we have this fossil fuel combustion, or soot, which is really dark. And the soot is especially problematic because when it lands on things like snow, it changes very highly reflective surfaces into very absorbing surfaces that can help, that can unfortunately melt ice regions and glaciers. So that was just a brief overview of different kinds of aerosol particles up there and how air pollution directly impacts climate. But now I'm going to introduce you to a couple of clouds real quick. So put on your best bow tie and let's go on the speed date. There are, as it turns out, over 100 different kinds. We actually call them species of clouds. But no matter, we can distill it down into a simple cloud atlas. There's really thick clouds that reflect more sunlight. And then there's really thin clouds that actually allow sunlight to pass through them, but they trap outgoing heat, so they can actually warm the planet in that way. Overall, most clouds reflect more sunlight than they trap heat, so clouds overall have a cooling impact. But there are special kinds of clouds that actually warm the climate. These are cirrus clouds. These are especially relevant because airplanes, contrails, can turn into cirrus clouds, and they have a slight warming impact. Okay, so there's all these different kinds of clouds. One thing that all clouds have in common, no matter what kind of cloud they are, is that they each form, the cloud particles, whether they're liquid droplets or snowflakes, each form on tiny pieces of air pollution in the atmosphere, tiny aerosol particles. So now you might be starting to think, well, he was just talking about aerosol particles, right? And now he's talking about how clouds form on aerosol particles. We call these special cloud-forming particles cloud condensation nuclei, if water droplets or rain droplets form around them. And we call them ice nucleating particles if snowflakes form around them. So now we're going to bring it all back together. We've talked about air pollution. We've talked about clouds. How does air pollution impact clouds? Well, let's find out. One is that if you emit more particles, if you emit more pollution, basically, into the atmosphere, you end up with larger snowflakes or larger water droplets in your cloud. And these clouds are, it turns out, less reflective. They're a little bit darker, and they reflect less sunlight back towards space. Now, if you're in a really polluted atmosphere and your cloud is forming there, suddenly there's a lot more competition for all of that water vapor up in the air. And each snowflake or rain droplet in the cloud's not going to be able to grow as large. And it turns out that these smaller snowflakes or water droplets are much more reflective of the sunlight, so the cloud appears brighter. And you don't have to take my word for it. This is a satellite picture of ship tracks off the coast of France and Spain and Portugal. As ships are going through a kind of background cloud layer, you can see that the ship tracks have emitted all of these, pollution from their smokestacks, and it's actually made the clouds where the ship has gone through brighter. And what happens in my little slide here in my cartoon, and what happens out in the ocean also happens in your kitchen. That's right, folks. Next time you bake, take a look at how bright and reflective crystal sugar is, granulated sugar, compared to powdered sugar. You'll see that the powdered sugar is much more brightly, much brighter, much more reflective than the granulated sugar, even though it's made of the same stuff, right? And the same thing happens in clouds. Now, another way that air pollution impacts clouds is by cloud dissipation. And this is basically a fancy way of saying make clouds precipitate. So it turns out that a lot of the air pollution that human activity is putting out into the atmosphere contains particles that are really good at forming snowflakes and clouds. And this matters because snowflakes, once you put snowflakes into a cloud, the snowflakes, because of some more complex thermodynamics that we don't need to worry about now, the snowflakes grow really big. And as soon as you get something really big up in the sky, of course it's going to fall out. So you can actually induce precipitation in clouds by emitting air pollution. And this is actually quite common. Over 70% of rain starts out as snow. We had a lot of rain on the East Coast today, and it started out as snow somewhere higher up in the atmosphere. It just melts as it goes lower down into the atmosphere. Okay, so as I'm going to begin wrapping up here, I wanted to leave you not with kind of a complex swirl of different cloud cartoons and different pictures of aerosols, but I wanted to leave you with this quote from one of my favorite artists, Joni Mitchell. I'll read it to you because I think we have time. This is from her song, Both Sides Now. She says, "I've looked at clouds from both sides now, from up and down, and still somehow it's clouds' illusions I recall. I really don't know clouds at all." And you can all thank me in the chat for not singing it to you, because that would be good for no one. But I think what she's saying here is that there's still so much we don't understand about clouds, both metaphorically and quite literally. It's amazing that although humans have been looking at clouds for millennia, there's still so much that we don't know. And in fact, they're one of the largest uncertainties in our understanding of Earth's climate system. So we need more research funding to figure out what's exactly happening with them. Thank you so much for the opportunity to talk with you today. Here's my email if you want to reach out. And I look forward to taking all of your questions. Looks like there's a lot of love in the chat, so thank you for that.
Awesome. Thanks, Martin. And yeah, that is a tough song to sing even when you're by yourself in the car. So, okay, we've got a lot of questions in the chat. So we're going to start with one that I think that you'll be able to answer pretty quickly. This is Idiocy asks, are clouds formed in dense particulate conditions less likely to produce rain because the particles are smaller?
Yeah, that's an excellent question. Very astute. So I think that your username is it's Good question. The answer is yes. Clouds form in very polluted environments that have smaller rain droplets in them are less likely to precipitate.
And on a related note, we saw a couple of questions asking about why might someone want to induce precipitation?
Excellent, yeah. So what I mainly studied was not doing it on purpose, i.e. through weather modification. This is happening whether I intend to have it happen or not, just because we're constantly putting air pollution up into the atmosphere. Now, there is a whole other application to this field of research where different researchers, not myself, but others, are attempting to change cloud chemistry to make it rain. And you can think of a couple of different reasons why I might want to do that. For my friends and colleagues out in the West Coast, where you suffer from frequent droughts, much more severe droughts than we're suffering from in the East Coast today, you can actually induce rain from a cloud. Now, it's not that simple. And the science is one thing, but when you think about the kind of geopolitical considerations of this, that's just as difficult of a conversation. Because let's say the state of California decides to make a cloud precipitate. Well, what's going to happen to the precipitation in the state of Nevada or New Mexico or Colorado downstream? You're going to get a little bit less precipitation. So this is definitely something where the science and the governance or the policy need to evolve in lockstep to make sure that we're considering the issue from all angles.
Okay, we're going to take a little pivot, and I'm going to ask you a question that we could spend literally 100 hours discussing. So feel free to just give sort of a very big picture answer. But related to some of your work on pollution and with the IPCC, can you talk just a little bit about how air pollution affects public health? Just again, 10,000 foot overview, because we could spend hours.
Absolutely, yeah. As we were talking about briefly on one of the slides, air pollution is the 4th leading cause of early death on average around the world. I think it's about 4 million people die prematurely because they're breathing unsafe air. This issue is quite severe in developing countries, but here in the United States and other more developed countries, we still suffer health issues because of poor air quality. Now, I really like to talk about this because it shows that we should care about air pollution regardless of our thoughts on climate change. There is reason to dedicate research funding to improve air quality because I don't know about you, but I want to live with healthy lungs to carry me into ripe old age. One reason for that is because I want to come back and listen to Both Sides Now by Joni Mitchell when I'm in my 80s, as she continues to sing it and re-sing it and re-record it, because our understanding of life and science evolves as we go through different decades.
Yeah, and I just anecdotally, I grew up in the Midwest, and I always found that regardless of what people may have thought about climate change, when I talked to people my parents' age who grew up in the 60s, I grew up in a town famous for having a river that would catch on fire, and that's why we have the EPA. But when you talked to them about pollution, the people, especially the people who remembered when the air was dirtier, when acid rain was a huge problem, when the river was literally catching on fire, they remembered that, and they would say, no, things have gotten a lot better. So yeah, I think air quality is a really great way to connect with people without having to talk about things that they may have a different opinion on.
Right. Yeah, we've made big improvements in air quality in this country the past couple of decades. Let's make sure that we continue to make that progress and not backslide.
Yeah, air quality is a huge success story. So that's a huge reminder that public science and supporting science does lead to actionable change in relatively short time scales, in our lifetimes. So we do succeed. The ozone hole is like another one. We do see success. This does matter. Okay, so one last fun question. What's your favorite kind of cloud?
All the questions have been fun so far. I am really basic, and I really like the cumulus clouds, which are those white, fluffy ones out there, because I love to stare at them and think about what I see in them, what animals, what shapes. One time I swear I saw one that looked like myself. Maybe that's just me being a complete narcissist, but I love, they're the most interesting to paint, I think, because they're constantly evolving. And as a matter of fact, and Joni Mitchell, she calls them ice cream castles in the air. So I also think that she's talking about cumulus clouds as well.
I assume we're thinking shallow cumulus, like the cute little ones that come and go on like a summer afternoon.
That's right. And when I think of my perfect day, I think of sky full of nice cumulus clouds.
Nice. My favorite is lenticular because it looks like the clouds on that poster in Mulder's office in the X-Files, in case anyone was wondering. All right. Thanks again, Martin. That was awesome. There are a few more questions in the chat. There were some great questions asking for more details about cloud seeding and about the role of microplastics potentially as a CCN. So if you're interested, feel free to dive in and see if you can find any of them. Sadly, we just ran out of time. So thanks again. And thanks to everyone in the chat for the great questions.
Thank you, everyone.
Yeah. And go tech. Yeah. All right. So we're coming up on the 11th hour of our stream. So I'm going to be with you for another hour. So this means we've got about 89 hours to go. So our next hour, we're going to see two more exciting talks. First from Professor John Horel about flash flood forecasting in Utah national parks. And then we'll have a second talk from climate scientist Matt Luongo about modeling ocean dynamics. And before I turn it over to John, we're just going to do another quick reminder of why we're here. We're here because we care about weather and climate data and forecasts. They affect us in many ways. We have seen the U.S. be a global leader in weather and climate by improving satellites, radar observations, balloons, planes, ships, and more. So we've made a lot of strides in weather and climate prediction, and they've been supported by the U.S. public through our public science institutions like NOAA, NASA, and even the National Park Service. The NPS does a lot of science. But in the past few months, we've seen our public science enterprise be put at great risk. So as an example, a lot of research aimed at improving air quality and visibility in our national parks like our national parks in Utah, which we often think of as our best idea as a country, is at risk of being severely reduced or even cut. If you go to a beautiful place like Canyonlands, you want to know that you can actually see the things you came there to see. So if you are worried about these and other cuts to U.S. funding and research, please use the link on your screen to contact your political representatives and tell them to save our forecasts and support weather and climate science, and talk about this to your friends and your family and your community. So we hope that you are learning fun things about weather and climate from this live stream. Keep posting in the chat. We're getting lots of great questions and comments. And again, just a reminder that all speakers, hosts, and volunteers are appearing in a personal capacity and are expressing their own views. Okay, so now I'm going to turn it over to Professor John Horel at the University of Utah. I'm pumped for this talk. I love visiting the Utah National Parks. Hope to go back many more times in the future. And hopefully I'll learn something that keeps me safe from flash flooding next time I'm there. So John, go ahead.
All right. Hey, thanks so much. It's been so much fun to watch the earlier presentations from especially Nina and Martin here just most recently. And I have to add, Marie, my favorite clouds are also lenticular. It's got the flying saucer clouds. You know, I get a lot of, we get people calling about those fairly frequently. So again, I'm from the University of Utah. and here representing a group that does research in a variety of areas. But what I really want to focus on is how research is so dependent on the resources that are available from NOAA and the National Weather Service, and particularly the people that are on the front line providing the types of forecasts that help protect lives and property. So Nina was talking about debris flows. I'm going to kind of get back into a related topic, talking about flash floods. But first, I'm going to talk a little bit about our drought that's going on in this area as well. And the picture at the bottom of the screen here is looking north towards Utah from Arizona. And these step-like mountains are what is called the Grand Staircase, and it's part of a very vast national monument. So first, talking about the situation in the southwestern U.S., we have been through a number of years of drought and then had a little bit of a brief break over the last couple of years. And now, particularly southern Utah, Arizona, New Mexico are back in it. And the Grand Staircase is that blue dot in the map there as well. So we'll be talking about that. So there's many agencies that are supported by NOAA and the National Weather Service. Directly, the one on the left is information that comes from the National Weather Service office here in Salt Lake City. But the one on the right is by what's called a CAP, one of the research programs that involve researchers in different parts of the country. And the one here, the Western Water Assessment, is put out monitoring conditions and involves a lot of stakeholders dealing with water resources in the West. This has been such an issue for us here in Utah that Governor has released an executive order related to trying to control our water supply this year. So that's sort of the yin of having too little water and now moving into flash flooding and what the potential is for this this summer. This is an indication again from another National Weather Service group, the Climate Prediction Center, that put out seasonal forecasts. The precipitation amounts here in terms of showing that it might be a little bit above normal in the southwestern U.S., but even though this is an important part of it, this is not going to pull us out of drought, even if this forecast were correct. So what's driving the flash flooding in Utah, Arizona, New Mexico, that area, is what's referred to as the North American monsoon. And so just like the Indian monsoon, a much larger beast than the one here, it really starts in the Sierra Madre Mountains of Mexico and extends up into Arizona, New Mexico. I always describe it as southern Utah is kind of the tail on the dog when it comes to the North American monsoon. So it's very episodic. We get kind of periods of monsoonal behavior with a lot of rainfall and then quiescent periods in between. What really makes this area unique is there's not very many people living in southern Utah, but as Marie talked about, there's a heck of a lot of people that come to visit. And they are not aware of the risks that they often are putting themselves in. And it's up to the kinds of forecasts that are issued by the National Weather Service and information provided by the Park Service to keep these people safe. So I want to see in the chat, those of you who visited some of the national parks and national monuments in the area. This is my favorite part of the country. I spend a lot of time in between Zion and Bryce Canyon and then get down to the north rim of the Grand Canyon. I feel very privileged to be able to go down to this area. So you can get a sense of sort of the lay of the land. There's a variety of national parks, national recreation areas, national monuments. It really is a tremendous resource for our country. And just like the National Weather Service and NOAA, parks and BLM are under considerable budgetary pressure right now, which is affecting operations in the parks. So again, back to the North American monsoon. this is a kind of a busy figure, but I'm up here in Salt Lake City. This box is kind of the area that I'm going to focus on. This is southwestern Utah. Here's Arizona. The blue shades indicates northern Arizona gets a heck of a lot more lightning than what I'm talking about here in southern Utah. And it's, lightning is typically, we can have a lot of high base thunderstorms without a whole lot of precipitation, but lightning is one of the best ways to be able to identify the kind of cumulus clouds that Martin was talking about in the last talk. And this is another product that comes from another group within NOAA and the National Weather Service that generates this national, the multi-radar, multi-sensor grid of information from lightning. There, in terms of areas where risk from flash flood fatalities, you can see, not too surprisingly, the most is in Texas and up through the arc of the Midwest. But you can see that Utah and Arizona are not too far behind. We had 3 fatalities, unfortunately, last summer in southern Utah, and one of those was actually across the border in Arizona. So what does it take for a flash flood? Well, it shouldn't come as a big surprise. It takes rain, but it doesn't take a whole lot of rain because we have a lot of bare rock and bare soils. And so if you have that upstream of narrow channels, or what are referred to as slot canyons, then you can be in particular risk. And one of the riskiest locations in the parks is the Narrows hike. It's a very accessible hike. And again, in chat, if those of you that have slogged up the Narrows or came down the overnight hike from that, is just fantastic. But it's like Disneyland on a busy weekend. There are so many people hiking up on this in this storm, and they are up this river, and it's a lot of people are at risk. And so the access to the Narrows is closed by the Park Service when the Salt Lake City Forecast Office issues a flash flood warning, one of the products that they do. But after conversations with the national parks, the Salt Lake office also issues a flash flood potential ranking. And part of the research that we've done is kind of evaluate how that might possibly be improved by looking at other kind of machine learning approaches. So one of the places that I spend a lot of time is on a tiny little river called the East Fork of the Virgin River. And whenever there's a flash flood, I kind of go down to this crossing because I know there's going to be people that are going to try to cross this in the middle of a flash flood. So let's see if I can pull, or Marie, do I click on the video or do you do that?
Ooh,
let's see. Well, we may not.
Yeah, you try it. And if not, we'll see if.
Yeah, we can skip it too. But I can't seem to do anything with it. Well, anyway, imagine, I'll just go to the next slide. You would have just seen this water moving really fast. And unfortunately, the driver of this car thought that he should try to cross the river, even though I'm there with my arms crossed saying, please don't try to cross the river. And fortunately, they didn't. He tried really hard to try to find a way across here. And if he did, it would have been very much a fatality. So how often do we get flash flood reports in this area? Well, you can see part of it is you got to have somebody there, or you have to have automated equipment from the U.S. Geological Survey that monitors stream flows. And so over the last several years, which is what we've really looked at, 2021 was a really big year. And this last year was kind of more normal. So the places that are at risk are slot canyons in particular, because they are really beautiful to go and visit. This is a data set that Mike Seaman at the Salt Lake City Forecast Office generated. The blue kind of boundary here that's the park boundary, and you can see all of these slot canyon, all of these stream areas, and then the slot canyons that are in them. And so here's where, here's where all the floods have taken place. And so over the last 4 years. And so you can see that most of these have happened, have been reported in these slot canyon areas. And it requires having information. There's many more flash floods that occur that are not actually reported. So the National Weather Service issues flash flood warnings here in the state. And you can see over the last 4 years, 2021, the top one there was the most active year where they were issuing so many forecasts in this area. So the flash flood potential rating is really something unique. It's something that the Salt Lake City office came up with, again, as I mentioned, initially with the Zion National Park, and then they've expanded it to other parks as well. And I showed this, you can't probably see the details, but this little signage here is actually at the entry point to the Narrows hike, the one that I showed where people are such at risk. And so the Park Service moves the marker over to indicate whether there's increased risk of flash floods before people start hiking up that area. So the point is to try to give very specific forecast guidance for the public for these types of areas for each of the national parks, whether it's not expected, possible, probable, or expected. And I'm just going to highlight one particular day last summer, August 13th. And this is for the Grand Staircase Escalante. So this is a forecast issued about 2-3 a.m. in the morning for that day, and saying, yeah, today flash floods are probable. And then the next day, Wednesday, they're saying, no, not expected. And you can see that it was pretty widespread. And so they give that information out in a variety of other ways through social media. So this is a Facebook kind of posting, because again, there's a lot of people, if you're just coming to recreate, they're not going to know where to go to get the information. And so it's really important for the National Weather Service working with a lot of the other federal agencies to get this information out. So this was a pretty active day. And so then they actually put out later that afternoon a flash flood warning for this area, which is in a particular stream here in the Escalante area. And so then, you know, what our research is looking at a lot of these kind of things. And so seeing here, this is the high plateau. This is one of the staircases, and then it's stepping down, and you can see sort of the Escalante River here. And this is the town of Escalante here. And so this shows that the lightning was occurring right on the slopes, and it as well as lightning occurring all over the area. But what that ended up happening for was the largest stream flow of the last several years in this area. And so, and this is pretty typical with these kind of flash floods. In this case, there was several days in a row where they had thunderstorms. And so this is the first day, and the stream flow went up. But this is the one that was associated with the most damage here. And this was the highest discharge, the flow in cubic feet per second that was observed in this stream over the last several years. And I keep hitting. Okay, so what can you do? Well, one thing is, again, recognize that the National Weather Service, working with all these agencies, is really about trying to get the information out. And especially when you're dealing with international tourists, being able to get that information out to them as well. So the National Weather Service, for these kind of public safety things, has, you know, these flash flood safety warnings available, and, you know, and what those actually mean. So when a flash flood warning is out, it means it's happening, or else it's going to happen really soon. And so that's when like for the Zion Narrows, that's when they'll close it so that people are not able to go hiking up that canyon. So to give you some of the background as far as where a lot of the research comes from for this, again, the Salt Lake City Forecast Office has presented this kind of information in national meetings, and they live it. They put out the forecast, and they're constantly trying to improve their forecast on this. One of the major studies of flash floods in this area was done, and it was related to the largest fatalities observed in Utah, where unfortunately there were loss of life both in a small town that was related to one flash flood, and on the same afternoon, and so there were 12 people killed in that town. And then another 9 were killed in a slot canyon in Zion National Park. And then this is an example of the kind of research that we've done, and then continuing to do that. And we'll be looking at these kind of things during this monsoon season as well. So if you want more information, we take advantage of a lot of the information that comes from the National Weather Service, and then package it in ways for different user communities. So just like what Nina was talking about, our research group provides forecast guidance taken from the National Weather Service and makes it available to fire behavior analysts, the people who make decisions about where to position equipment. Those are these Alaska Fire and Fuels projects and Great Lakes Fire and Fuels projects. Mesowest and Synoptic are ways to be able to get access to information. We do a lot with new research on how to deploy equipment in novel ways. And just like what Martin was talking about as far as air quality, we have sensors on light rail cars and electric buses in Salt Lake City. And that's because we have a 4-season air quality problem. So we have wintertime particulates, spring and summer dust and particulates, summer wildfire particulates, and summer ozone. So it puts our residents at considerable risk. And then a lot of how do you use this information? So we do a lot of things related to data mining, et cetera, and then sensor systems, different ways of being able to look at information. So returning back to that car, I typically will, after there's been a flash flood and somebody was so anxious to get across, I'll go back either later that day or in this case the next morning to see, as in this case, that there are tracks going across, that they made it across. And you can see what the normal flow is like in this particular stream, how quickly it can change in these things, and people can be caught very unaware by that. So with that, I'll stop and take any questions that people have.
Awesome. Thank you so much, John. That was fantastic. And as all the chat comments will tell you, super, super relevant, especially as we head into the summer, which is sort of peak season for our national parks. So we've got a bunch of awesome questions. We've got a couple questions that are related to why is forecasting flash floods in southern Utah so unique, and is this event widely known, especially considering, as you highlighted, how much tourism there is in this area?
Yeah, no, that's really important. And no, it's not unique just to Utah. The same situation exists wherever you have the combinations of, thunderstorms and sort of impermeable soils, things where the water is not really able to be absorbed into the ground as it is in, say, the Midwest and eastern part of the country as, much easier. Here, it doesn't take a whole lot of rain when you put it basically on hard rock. It's just going to run off, and so it collects, and so that exists throughout what's sort of the Colorado Plateau country, and this exists around the world. So it's not unique by any means, but it does, in terms of the Weather Service forecast offices, they all have to develop ways to be able to communicate risk. So, for example, the Flagstaff office works very closely in getting the information out to the rafters on on the Colorado River in the Grand Canyon to be able to give them updated information on risk in the canyon itself. One of the fatalities this last summer was in Havasupai, and it was just a monumental flood, and unfortunately one person was swept away from there.
Yeah. Yeah, thanks again. And actually, that kind of segues into another question that we had from Charlotte on the in the chat. So, do dry climates like those in Utah see worse effects from flooding than wetter climates? And I think you kind of answered that, but maybe you can elaborate on that a little bit.
Well, I mean, you have to put it in. I mean, as you can see, sort of where the risk of flooding is across the whole country, and worse in areas where you've got a lot of water happening. I mean, an area like Houston in Texas will, 10 inches of rain is not uncommon in a hurricane or, major convective system going through those areas. So it's not to belittle those kind of situations. If anything, they're more substantial. But the difference is you have people that are typically living there that are aware of where the risks are. And so this is happening in locations where, I mean, you look at some of these slot canyon areas, you would think you would never see any water in these places. They are bone dry. And then in a matter of a couple of hours, it can turn into a raging torrent.
Yeah. And so again, sort of building on that, we have another question about do humans play a part in causing flash flooding? Obviously, humans can play a part in sort of a social sense by maybe like making poor decisions or underinformed decisions that lead to bad consequences. But are there other sort of human impacts that affect flash flooding?
Well, the hardest thing with, dealing with climate change issues is the impact on precipitation. And especially in these areas, you can't really evaluate precipitation on the basis of, say, monthly totals or something like that. So because these things can be so short-lived, but that nonetheless, just the large-scale circulation changes that are happening around the globe impact these kind of very localized effects as well. And then the other thing is just resource. It's less of an issue with flash floods than, say, wildfires in the West, as far as building in extremely hazardous locations. That's kind of the biggest issue when you think of wildfires, is just the impact of increased building in the wildland urban interface, where you have, you can generate such increased risk. In these kind of places, that's a little less of an issue. I mean, again, there's, towns that can be impacted by this, but for the most part, these are pretty remote locations.
Yeah, as someone who lives in the Front Range area, I am super scared about fire. We've got a couple minutes left. Is there anything else you want to share with us as someone who works closely with both the Weather Service and the Park Service? Is there anything else you want to share about how funding cutbacks might directly affect the super important work you do? And you can decline to answer that if you want.
Yeah, no, well, I mean, part of it is we see it. I mean, I'm an educator, so one of my recent master's students was hired by one of the federal agencies working in fire, and went through the as an intern, being fired, being rehired, and those kind of things. I mean, it's devastating on young scientists. It just makes it's just so hard right now to be able to predict what is going to happen as far as the workforce when we have this kind of situation where entry-level positions have been so severely hampered, through the policies right now. So hopefully that'll get squared away, and that decisions will be kind of a little bit more forthcoming. It's tough on universities. We want to be able to send our brightest and best out, to be able to be working for these kind of agencies and serving, the community. And it makes it tough.
Yeah, it is. I feel for the people who are just starting their careers right now. It is not an easy time. I mean, it's not an easy time at any stage, but it's really hard at the beginning. Okay, well, thanks again to Professor John Horel for an awesome discussion of flash flooding in Utah national parks. So if any of you make it out to Utah this summer, hopefully you keep some of this in mind. And again, just another reminder of how important science is to our national parks. So we're halfway through hour 11 of this stream. We've got 88 and a half hours to go. And big ups. We've got a lot of people here from Tumblr, which is sending me back to like 2010. So that's pretty fun. And also another thanks to our awesome organizing team, because pulling this off is huge and a big undertaking. So once again, just reminding you that we are here to demonstrate that we value weather and climate science, and that we need good, high quality weather and climate predictions and models to function as people and as a society. The U.S. has had a long, storied history of leadership in weather and climate. U.S. scientists, among many other things, built the first computational climate model back in the 60s. It was a long time ago. And we've continued to improve weather and climate predictions, both for the U.S. and the entire globe, by investing heavily in top-of-the-line weather satellites, radar systems, on-the-ground observation systems. Professor Horel just talked about a lot of these. Observations like weather balloons and radiosondes, planes and ships that observe weather in remote or extreme regions, unmanned systems, and so on. So we've made a lot of strides in weather and climate prediction, and they've been supported by the American public through science institutions. But as we know, in the last few months, a lot of this science research has been put at risk. Another example, cuts to the NOAA National Marine Fisheries Service are believed to have already contributed to overfishing in such a short time. So I saw that a few days ago. That's wild. So if you are worried about these cuts and other cuts to weather and science, please use the link on your screen to contact your elected representatives and tell them to save our forecasts and support weather and climate science. And again, talk to your family, your friends, and your community about these issues. Truly, raising awareness goes a long way. It really, really does, even though it doesn't always feel like that. So hopefully you've been learning lots of new things about weather and climate. Again, post any questions you might have for our speakers in the chat. And a reminder again that all speakers, hosts, and volunteers are appearing in a personal capacity and are expressing their personal views, not the views of their employer. So to wrap up our 11, we're going to hear from climate scientist Matt Luongo about ocean dynamics and climate change. So Matt, go ahead and start whenever you're ready.
Yeah, great. All right. Well, thanks, Marie, for hosting. It's a lot of fun to be here, especially on the first day here. I've loved to see the energy. So my name is Matt Luongo. I'm a postdoctoral fellow at the University of Washington. So I'm coming in from Seattle tonight. It's been a beautiful day here. And today I'm going to be talking about using a model hierarchy to clarify ocean dynamics relevant to tropical Pacific climate change. So I've kind of bolded the things that I'm hoping to really get across in this talk today. I'm going to be talking primarily about the ocean, so following up Sarah Perkey's great talk earlier. But I'm going to be talking about tropical Pacific climate change, why the ocean is important for that, and then using a model hierarchy. So I think that will become apparent in a little bit. So one of the things that really excites me about the field of climate science and about my place in it as an oceanographer is interactions between Earth systems, because that's really what shapes the field of climate dynamics. If you're an atmospheric scientist, you're focused on the atmosphere. If you're an oceanographer, you're focused on the ocean. But if you're a climate scientist, you really need to focus on the interactions between the atmosphere, the ocean, the ice, the solid Earth, and the biosphere. So I'm going to be talking today about coupled climate processes, which involve two or more components of the climate system. And specifically, I'm going to be talking about coupled ocean-atmosphere interactions. And those are particularly important in the tropics. And I'm going to be talking a lot about the tropical Pacific today. So just as an example of a coupled ocean-atmosphere interaction, I want to talk about the mean state of the tropical Pacific. So what I'm showing here is just a really simple cartoon. This is a slice of the equator. Basically, you can think of it as an average over a couple of degrees of latitude, where the x-axis is west to east and the y-axis is depth. And this is going down into the ocean. So basically, at the equator, trade winds and upper ocean circulation couple to really drive mean flow. So it's a bit more complicated than this. We have to think about convection in the atmosphere, and we need to think about return flow and all that type of thing. But I'm really just going to focus on this very simple kind of schematic cartoon here. Basically, we have trade winds coming from the east along the equator, and those trade winds are pushing a surface current. So basically what's happening is you're having this warm equatorial water that's warmed by the sun, and it's being pushed by the trade winds into the Western Pacific, where it really piles up. And when it piles up, it tilts this thing that's called the thermocline. And the thermocline you can really think of as kind of the interface between the upper ocean and the deeper ocean. And what's important here is that the thermocline is tilted in the tropical Pacific. So we have this tilted thermocline. We have more water that's moving towards the west from the east. And for conservation of mass, we have to then upwell water to replace that water that's moved from the east to the west. So this is kind of a mean state understanding of the tropical Pacific. And the tropical Pacific, many of you have likely heard of because of things like El Nino events. So when we think of this kind of mean state understanding of the tropical Pacific, it's important to understand the coupled Bjerknes feedback, because the coupled Bjerknes feedback leads to El Nino events. So for instance, what I'm saying here is that if we, for instance, had weaker trade winds, that would lead to a weaker surface current, which would mean we would pile up less warm water in the Western Pacific, and we would have a cool anomaly in the Western Pacific. The thermocline would be tilted less, which would mean that we could have weaker upwelling, and there would be a warm anomaly in the Eastern Pacific. And this is just a cartoon understanding, but it's the exact opposite for La Nina events. So in those types of situations, we have stronger trade winds, which would lead to a stronger surface current, an increased thermocline tilt, stronger upwelling, and then we would have a cool anomaly in the Eastern Pacific and a warm anomaly in the Western Pacific. Now, these El Nino and La Nina events are really important for global climate. It's been really, fun to be right after Professor Horel, because I think his work from 1981, I cited on maybe the 5th slide of my PhD defense, showing how changes in the tropical Pacific affect global climate. But it's really important that we understand these coupled dynamics, because they're crucial to understand societal climate impacts. ENSO, which is the El Nino Southern Oscillation and includes El Nino and La Nina, is actually the leading source of year-to-year variability in global climate. So during the 2015-2016 Super El Nino events, for instance, we had very severe wildfires in Indonesia, and we had flooding along Peru in the South American West Coast. And then during La Nina events, it's kind of like the opposite, except we have different climate impacts as well. So we had a triple dip La Nina from 2020 to 2023, which contributed to the North American drought. And I'm showing here the kind of canonical bathtub ring that we see in the Colorado River reservoirs. And also during a La Nina event, we can expect a stronger hurricane season in the Atlantic. So in 2011, we had a strong La Nina, and that contributed to a stronger than average hurricane season, which impacted, for instance, Hurricane Irene, which I remember growing up on the East Coast. So that was talking about interannual variability. So kind of year to year, we have a La Nina one year, we have an El Nino one other year, but predicting how the tropical Pacific will respond to climate change involves understanding those coupled interactions and also has major global consequences. So if we think of it, instead of we're thinking of year to year and we think of this kind of long-term trend, it's really important to understand how the tropical Pacific temperature patterns and whether they look, for instance, more like an El Nino or more like a La Nina, because these will globally affect hydrology. So you can think of drought, floods, mountain snowpacks. They're going to affect land and sea temperatures, so heat waves, both on land and in the ocean. They'll affect fisheries as temperature and oxygen are driven or change as a result of these patterns. Hurricanes and typhoons, like I said earlier, La Nina means a stronger Atlantic hurricane season, and an El Nino means a weaker hurricane season. They'll also affect the rate of climate change. So given the exact same input of CO2, we would expect the planet to warm more if the tropical Pacific looked more El Nino-like in the future, and many, many more. The tropics are really important for global climate. So to predict these impacts, we need to be confident in the coupled equatorial dynamics that create these patterns. But these coupled climate processes, which are common in the tropics, raise these really difficult chicken or egg type questions. So the question then becomes, is the ocean driving the atmosphere? Is the atmosphere driving the ocean? Or are both driving each other? And usually that's the case in the tropics. So you can think of our kind of cartoon of the Bjerknes feedback. I started with changes in the winds, but I easily could have started with a change in ocean circulation and then eventually got to a change in the winds that changed the ocean circulation. So this is a positive feedback, these chicken or egg type questions. And how do we deal with that? Well, climate model hierarchies are really the gold standard for understanding coupled dynamics. There was a nice talk earlier from Professor Ben Santer, who was talking about consilience and using different levels of understanding and levels of proof to get to the same thing. And this is kind of a similar idea here, where basically you start with the most complex model that you can, and you sort of peel back levels of complexity until you can explain the phenomenon of interest. So you can start at the very base of this period here, which is just a cartoon of the hierarchy of models, and think of a really simple one-dimensional energy balance model or radiative convective equilibrium model, and you just start to build up complexity. Today, I'm really just going to be focusing on a very narrow niche within the hierarchy of models, sort of towards the top, I would say, in terms of that pyramid, where I'm going to look at kind of a coupled global climate model. So this is sort of what you would imagine in the CMIP from IPCC reports, a partially coupled climate model, which I'll talk about in a second, a realistic ocean model, and sort of a really simple ocean flow model that I can run on my computer. And the question that I'm going to be looking into is, what dynamics drive the subsurface temperature pattern of the tropical Pacific Ocean's response to climate change? I don't have time to get into all the specifics of the numerics and everything here, so I've tried to really abbreviate this and kind of focus on talking about El Nino and the Bjerknes feedback and whatnot. But basically, what I'm looking at here and what we're all seeing on the right is a coupled global climate model, that's a GCM, response to greenhouse gas forcing. So I've done a really idealized example of climate change here by abruptly quadrupling CO2, just in order to really slam the climate system with kind of a hammer to see how the ocean responds to it. And we can see a couple of things that are kind of interesting. We see it's much warmer near the surface. We see that there's this kind of interesting cooling response in the middle of the tropical Pacific. And again, this is a depth section. So depth in the ocean is on the y-axis and longitude is on the x-axis. So it's kind of maybe surprising that we would have any cooling at all from greenhouse gas forcing. And then we have this sort of like sloping warming response in the subsurface Eastern Pacific. And this white line is just an example of a constant temperature line in the tropical Pacific, just to show you how the thermocline is tilted. So I'm going to be showing you a lot of plots that look kind of like this, and we can decompose this complex dynamic response into winds, remote warming, and local warming. So kind of moving down the hierarchy of models, step one is linearly partitioning that response that I just showed you, the ocean's full response to greenhouse gases, into buoyancy and momentum. And when I say buoyancy, I really mean density-driven impacts on the ocean. So that's changes in temperature and changes in salinity, as those are in the equation of state for the ocean. And when I say momentum, I'm really talking about the fact that winds viscously push the surface ocean. So you can think of like if you're blowing on a bowl of soup or something, or coffee, and you blow hard enough and you get kind of mixing from this actual mechanically driven impact of the winds. And the way that I get to this is by something called overriding surface wind stress in the model. So basically in a fully coupled GCM, I'm going to really simplify this here with this cartoon. We have an atmospheric GCM that's kind of doing its thing. It's taking the time steps that it needs, and it's passing the atmospheric state to the coupler, which is kind of like the head honcho of a climate model. And similarly, below it, the ocean is doing the same thing. So the atmosphere and the ocean pass their state to the coupler. The coupler deals with interpolation and conservation of energy and timekeeping and all of that. And what it does is it calculates these fluxes that then go between the atmosphere and the ocean. And so these fluxes, then allow the ocean and atmosphere to be coupled in a coupled GCM. When you override surface ocean wind stress, which is this kind of technique in these models, basically what you do is you turn off the handoff of momentum fluxes from the coupler to the ocean. And instead you give it a specified momentum flux that you understand. And what this does is it disables momentum feedbacks, like that Bjerknes feedback I was talking about early on. And so with this understanding, we can decompose the fully coupled response to climate change. So hopefully you should recognize this plot on the left here, which is the fully coupled equatorial temperature response to that greenhouse gas forcing. And on the right here, you can see that it's actually just a sum of the wind-driven response on the right and a buoyancy-driven response in the middle. So this wind-driven response, you can see, is kind of resulting in that kind of interesting cooling, and the buoyancy-driven response is really most of that strong warming. Now, the details of that I'm going to get into in a second, but that momentum force response really interestingly features this sort of east-west temperature dipole. And this temperature dipole implies a decrease in the thermocline tilt due to a decrease in trade wind strength. And that's the Bjerknes feedback. That's what I was talking about in our cartoon earlier, right? So we have decreased the strength of the trade winds, so we've slackened the tilt of the thermocline. So then the question is, what's happening in the buoyancy-driven case? So step 2, as we're kind of moving down the hierarchy of models, is using an ocean-only model to clarify those dynamics. So it stands to reason, there's been a lot of research in the field that I'm not going to get into here that have looked at the impact of the subtropics temperature effects on the tropical Pacific. Specifically, folks have really looked at the impact of cloud forcing off California or Peru and how that might then impact the tropical Pacific. But it stands to reason that that full response could be the result of both remote and local surface forcing. So I've input these two temperature fields driving my ocean model, which is the remote impact on the left and the local impact on the right. And kind of interestingly, we see that we can effectively recreate the full equatorial response as a result of a simple sum of these regional forcing simulations. So the remote simulation, which is on the left here, you can see kind of features a strong surface warming, a kind of interesting cooling. The remote has this really coherent warming of the thermocline. And when you add them together in the ocean model, you get something that looks quite a lot like what we had in our coupled model. And it's not perfect, and I totally recognize that, but it's entirely different models. So these are millions of different lines of code. So it's pretty impressive that we can even get that close. So this remote temperature forcing causes this coherent thermocline deepening. So you can see that we kind of have this strong warming in the thermocline here, which is, again, you can just kind of imagine as this white line that I'm showing. So this is a coherent deepening. So you can imagine that the thermocline is moving down, which looks like a warming signal, which matches previous ocean tunnel literature. So in this work that I did a while ago, we applied a cloud forcing off of California, and we kind of dug into the dynamics that have to do with these really interesting global planetary waves. And we can see, if you just kind of flip between the two of these, that our remote warming effect looks quite a lot like we just have this cooling impact that I looked at earlier. But what is happening in the local response, where we have that kind of interesting cooling? So the next step, as we then kind of move down the hierarchy of models, is to use a primitive equation model to explain the local equatorial dynamics. So don't pay attention to all the details on this slide, but basically we can model the equatorial ocean as a 1.5 layer system where the lower layer flow is kind of negligibly small compared to the upper layer flow. And this is just a really simple schematic of what these 4 equations that I have on the right here are trying to recreate. And it doesn't matter what these equations are necessarily. I'm just here to tell you that those 4 equations are what are running this model. It's run in a Python notebook on my laptop, and it's super fast. And when we kind of treat the equatorial ocean like this, we can see that our response here on the left, which we think was kind of interesting, where we have this surface warming, and then we have kind of a cooling of the central western Pacific, and then maybe a bit of a warming towards the surface eastern Pacific, looks quite a lot like what would happen if we just applied surface warming. So basically, if we had the equation that's in the top middle here, which is just the steady zonal momentum equation, and we solved it for a perturbation where we just applied a surface warming, we would have to increase the tilt of the thermocline. So this is kind of interesting in the sense that we can get a tilt of the thermocline without any changes in winds. So now this plot on the right here is in terms of latitude and longitude, so it's a bit of a different orientation than what I've been showing you. And we see that we would have the thermocline would get shallower in the Western Pacific and deeper in the Eastern Pacific, which looks like that relaxed thermocline tilt that I was talking about earlier. So then we can bring it all home. And this is something that I think climate scientists really love to do, is when you're kind of peeling back this hierarchy of models, you're able to effectively understand something. So we use this full model hierarchy to kind of dynamically interpret the fully coupled GCM response to greenhouse gas warming. So on the left here, we have that fully coupled response, and we saw that it's actually a result of buoyancy and momentum, and we can kind of further decompose the buoyancy into remotely driven impacts from sea surface temperature and local driven impacts from sea surface temperature. Now that's pretty cool because this understanding provides obvious insight into the multi-model response to greenhouse gases. So everything that I've been talking about so far has been this really idealized forcing where I've abruptly quadrupled CO2, which really isn't realistic, right? We're increasing it a little bit by little bit each year. But if we then consider kind of a realistic climate change forcing scenario and an average of many different GCMs, we see that this pattern is actually quite similar. So this is on the right here, the 1958 to 2022 subsurface tropical Pacific temperature trend, given our best guesses at greenhouse gas and aerosol concentrations. And that then begs the question of how modeled historical subsurface temperatures might differ from observations. So on the left here, we have actual observations of what we've seen. And we can see that it's pretty similar. We still have this kind of interesting cooling response, but for instance, the cooling is closer to the surface in observations. So in order to really fully understand the dynamics contained within the models, we need to go through this hierarchy of models to understand what exactly is going on in these chicken or egg type questions. And that's a really important first step before we compare with observations. So why does this matter? So to truly understand future climate impacts on society, we need to understand how the tropical Pacific is going to respond to climate change. So this is a picture or a plot that I took from the IPCC 6th assessment report that looks at late 21st century projections of temperature minus late 20th century projections. And models predict a long-term El Nino-like warming in response to climate change. This will impact global temperatures and precipitation. But how much do we trust that? Do we trust that? Do we think it's going to be more El Nino-like, or do we think it'll be more La Nina-like? And in order to actually test this understanding and test our projections of the future, we need to first of all understand how well we understand the dynamics that created the model's estimated response from 1980 onward. And we need to understand how well that response then agrees with observed temperature changes. So we really need to have these kind of idealized experiments to understand what the more realistic model experiments are doing, to then understand how the observations and the models maybe need to be tweaked to better estimate climate change. And this work has really only been possible thanks to taxpayer-supported federal research funding. So during my PhD, I was supported by NASA and NSF, and as a postdoc at the University of Washington, I'm supported by NOAA and a cooperative institute in Seattle. And cuts to these federal research agencies obstruct further progress on these important topics. And our nation's forecasts and preparedness will suffer, whether it's weather forecasts or climate forecasts decades into the future. So I'd like to say thank you, and thanks to the hosts and organizers for this opportunity, and I'm happy to take any questions.
Awesome. Thanks so much, Matt. I was also a postdoc at UW way back in 2019.
Oh, cool.
So yeah, I got to be a COVID postdoc, which was quite something.
Yeah, I was a COVID grad student, so I can kind of empathize.
Yeah, exactly. Being a COVID postdoc was better than being a COVID grad student, though, for sure. I was like very relieved to be done with grad school by then. But yeah, UW is an awesome place to study the ocean and weather and climate. So we have a few questions from the chat. So there are a couple of questions actually about sort of the patterns and responses you're seeing in your sort of more simplified, idealized models, and how that corresponds to both like physical geography. I'm assuming that means continents, etc., and then the ocean outside of the tropics. So do these results how does sort of like more realistic geography and topography affect them, and can you extrapolate from the tropics to the extratropical oceans?
Yeah, that's a good question. So I've really only focused on the tropical Pacific here, but everything that isn't just that simple Python model that I can run on my computer has quote unquote realistic geography, so it's maybe a degree resolution, which is fairly coarse for climate models, but it does have kind of the coastlines and bathymetry and everything in these models. So what you're seeing here is effectively an average from about Indonesia to Ecuador in these plots. And if you can, the tropical Pacific is a very specific place where, the thermocline is tilted and we don't have the Coriolis parameter, which I'm not going to even get into here. But this is really a specific equatorial kind of dynamic response question, and things would look quite different if we were to look in the extratropics. For instance, if we were to make the same plot from Asia to California, for instance, it might look a little bit more like that buoyancy-driven response that I'm showing in the top center here.
That's a great answer. And then, well, first I want to correct myself and remind us we're still, COVID has not left us. It is still out there. So, be careful. And we've had a couple questions that I think are sort of related. So we had one asking if you could maybe re-explain the Bjerknes feedback, and then related is a similar question about climate change affecting the strength of the trade winds. So I think you can probably kind of answer those together.
Let me just bring up my cartoon again of the Bjerknes feedback. And this is kind of, an interesting thing to keep in mind when we have these sort of El Nino events. So again, in normal times, we have trade winds going from the east to the west at the equator. And those trade winds are driving surface currents, which then tilt the thermocline because we have more water piling up in the Western Pacific than the Eastern Pacific. And because of conservation of mass, as those waters move from the Eastern Pacific to the Western Pacific at the surface, we need to upwell more water from the deep ocean to replace them. Now, the Bjerknes feedback is just this coupled ocean-atmosphere feedback where the winds and the surface ocean couple together to either decrease or increase the state of the mean state in the tropical Pacific. So in an El Nino state, if we have weaker trade winds, we'll have a weaker surface current, and we'll have less of a thermocline tilt. And what that ends up happening is you have this warm anomaly off of South America and this cool anomaly near Indonesia. And then similarly, the Bjerknes feedback just in the opposite direction is if you have stronger trade winds coming from east to west, you'll drive a stronger surface current, you'll increase your thermocline tilt, and you'll upwell more cold waters. So you get this kind of cold anomaly off of Peru and this warm anomaly off of Indonesia. So this is kind of this really basic cartoon understanding of the Bjerknes feedback, and that's ultimately what sort of drives these El Nino and La Nina events. And then what was the next question, Marie?
So there was also a question about climate change affecting the strength of the trade winds.
Yeah, that's a great question. And that's kind of exactly what I'm looking at here in this response, is because we're thinking about the decadal trends because of climate change. So this Bjerknes feedback, as I'm kind of describing it here, is an interannual year-to-year thing. But if, for instance, climate change was leading to, as I showed, more El Nino-like or more La Nina-like responses over the long term, like if we averaged over many decades, then it absolutely is going to affect the strength of the trade winds. So while it might not be as strong as this kind of interannual year-to-year variability that bounces back and forth, if we kind of have this long-term trend towards more warming in the Eastern Pacific than in the Western Pacific, for instance, we would have less strong trade winds overall, if that makes sense. So basically, if we take what the IPCC report has said, which is that we should have a long-term El Nino-like response to climate change, then we should have weaker trade winds.
All right, awesome. Okay, I'm going to ask you one more question before I pass this off to our next host. And this is coming from someone who has also worked on a hierarchy of models at various times, including pretty idealized models. So I just was wondering if you could share any maybe like general big picture thoughts you might have on how these sort of more simplified idealized models really do help us understand an infinitely complex real world, even in the age of like, you know, throwing everything into a neural network and letting it go. I think there's still a place for these idealized models.
Oh, absolutely.
I would love to hear your thoughts on that.
Yeah, absolutely. I mean, the solution to this is not going to just be we throw something into a black box and then see what pops out. We really need to understand what the physics are happening in these models. And I think some of the work that I've worked on here and I've shown here shows us that we don't even understand necessarily what's happening in these responses unless we kind of really dig into this hierarchy of models. And it's really as we peel back these layers of complexity that we can actually then understand what's happening in these completely deterministic models that we've built. And they're 10 million lines of code, these GCMs, and they're all written in Fortran. But it's only once you're then making this hierarchy of models that you actually can understand what is happening in the physics that we've coded. And so we need to understand that before we would certainly throw it into a black box of AI to try to guess what's going to happen.
Yeah. And I totally agree. And I'm saying this as someone who is mostly working on AI now. But
yeah, no doubt.
The more AI you do, the more you are like, we can't use this for everything. At least that's what I see.
Absolutely.
All right. So thanks again, Matt. That was an awesome talk. And thanks for all the questions from the chat. And also I noticed in the chat, we've got a ton of young and early career scientists in all sorts of fields, not just weather, climate, and oceanography. So it's awesome that you guys tuned in, and good luck with all of your work. Try your best to keep it going and not get too discouraged. I think we will fix this someday. Okay, so it is 1 a.m. East Coast time, 11 p.m. here in Colorado and Utah, where our next host is, and 10 p.m. in California. So keep on hanging out, those of us who don't have to go to bed yet. And I am going to turn you over to Vanessa Sun, who is a PhD student and atmospheric chemist at the University of Utah. So,
hi everyone. I know that we had some Utah talk earlier, and a lot of people were really excited about that. So great to see some love for Utah. So we're currently at hour 13 of the Weather and Climate live stream, which means we've got like 87 hours to go. My name is Vanessa Sun. I'm a PhD student and atmospheric chemist, and I'll be your host for the next couple of hours. For this segment, the following hour, you're going to be hearing from 2 graduate students about their weather and/or climate research. Please remember that these speakers are not representing the views of any specific institutions or employers, but instead in their own personal capacities. Before we begin, we want to remind you why you're here, listening to the stream in the middle of the night, I guess. Weather and climate forecasts are important for you and to everyone in this country. Luckily, the United States has long been a world leader in weather and climate prediction. We developed the first computerized weather forecast to help you know what you can expect in the coming weeks, and we made the first computer models of the climate impacts of carbon pollution, so you can know what to expect in the decades to come. To make these forecasts work, we've created an unparalleled network of observations using everything from weather stations to satellites, planes, balloons, boats, and floats. The resulting forecasting and observation system is a true scientific miracle, and we're excited to share some of that miracle here with you. This miracle was made possible by decades of investment by you, the American public. However, in recent weeks, funding cuts have put this miracle at risk. This has resulted in loss of observational coverage due to short staffing at weather stations, which is already hurting our forecasts. Laboratories dedicated to understanding our climate's future are being closed or shrunk, and funding for our basic understanding of the weather and climate is disappearing. Many meteorologists, atmospheric and climate scientists have lost their jobs, and programs that have trained generations of these scientists are being shut down. It doesn't have to be this way. If you like what you see here today while you're listening to the stream, then we encourage you to use the link on your screen to contact your representatives and tell them to save our forecasts to keep the lights on for weather and climate science so we can keep this miracle alive. Either way, we hope that you learned something about weather and climate through our talks today. And please feel free to ask us any questions about our science in the chat, and we'll have a few minutes at the end for questions at the end of each talk. So without further ado, our first speaker is going to be Ryan North, who is a graduate student at Texas A&M University. He will be presenting a climatology of lake breezes at O'Hare International Airport. Hi, Ryan.
Sorry, I can't hear you. So am I good?
Yeah, you're good.
All right, perfect. So thank you for the introduction. And I'd also like to thank you all for joining us here this evening. For those of you in Central Time like I am, thank you for starting your Thursday here. And I'm honored to be here and present my work here. And of course, thank you to the Weather and Climate Livestream team who's working hard to keep everything running here. And it's been a great day of talks. I've really enjoyed sitting through them. And then sort of a final acknowledgement. I'd like to acknowledge Gino Izzy and Eric Lenning of the National Weather Service in Chicago, who were my mentors for this project, who were really, really helpful and provided a lot of help along the way. So generally, if I was giving this talk sort of in a lecture hall somewhere, I would ask the audience to raise their hand if you've ever flown in or out of Chicago O'Hare International Airport. And since we're sort of here on the internet, I can't really see your hands, but I would raise my hand as I've been to O'Hare many times, and I'd imagine many of you in chat have as well. So before we actually start talking about lake breezes in Chicago, I thought I'd give you a little background about myself. So I am a weather enthusiast at heart. I love talking about the weather. I love teaching about the weather, and I really just love the weather in general. It's been a passion of mine ever since I was a kid. And I really like winter weather, so I especially like winter weather. So although winter weather has nothing to do with this talk, I put some really cool images of a nor'easter on the right side of the screen here to give you sort of just an idea of how beautiful winter storms can be. Just to give you a little bit of a path to, or maybe my journey to where I am right now. I am currently a PhD student at Texas A&M University. I did my undergraduate degree at SUNY Oswego, and that is in meteorology. I got my master's in atmospheric science in 2023 from Texas A&M. And sort of when I tell people that I'm a PhD student, a lot of people just sort of shake their head at me, and then they're like, I don't really know what that means. What does a PhD student sort of actually do? So I thought that maybe I'd give you a brief overview of my role here as a PhD student. So I really have two primary roles. One of them is research, and the other one is teaching. So my research mostly focuses on coastal weather phenomena, so precipitation along coastlines and land and sea breezes, or in the case of this talk, we're going to talk about about lake breezes. And then on the teaching side, some semesters I do some grading, and then some other times I've actually had the pleasure of teaching my own class, and these usually range from introductory to meteorology courses and also just introduction to the climate change and climate courses. So just to give you a little bit more background about me and sort of how this particular project came to light, I am an alumnus of the Ernest F. Pauling Scholarship Program. This is a 2-year scholarship program that is funded by the National Oceanic and Atmospheric Administration, or NOAA. Part of it is they give you a stipend towards your undergraduate tuition during your junior and your senior year of your undergraduate education. And then they also sponsor a 10-week paid internship where you get to work on a research project. And I had the pleasure of doing my research project at the National Weather Service in Chicago, Illinois. And on the right here, just some pictures I took of the office. One of the inside, one of the outside. Very, very basic photos, but to me, the day I got to that office was an amazing experience, and I was so excited I had to take these pictures. So to actually move into the objectives of this study. So the real main objective of this was we wanted to build a lake breeze climatology for Chicago O'Hare International Airport, or ORD, if we go by the 3-letter identifier for the airport. And I'll explain where that identifier actually comes very shortly. But if you're not familiar with the word climatology, you could think of this as a database where all these events have been characterized, and we have a bunch of different parameters with them. So once this climatology was built, the next step was to sort of use this to help forecasters make better, more reliable predictions for the airport. And the goal of this is always to improve airport operations, reduce delays, increase safety, things like that. So one of the fun facts I learned along the way as I was working on this project was where the actual identifier for Chicago O'Hare comes from. So ORD doesn't really sound like Chicago O'Hare at all. That's because it actually comes from the original name of the airfield, which was Orchard Field, and then it was renamed to Chicago O'Hare. So if you've ever wondered where ORD comes from, this is sort of a little fun fact before we get into the science. So to give you some background information of why this project was so important is it's actually very challenging to forecast lake breezes because they are on a small scale in the environment. And it's even more complicated when you throw in the fact that O'Hare is one of the busiest airports in the United States. And because of this, accurately forecasting the lake breeze can mean the difference between a minor delay and a widespread delay. And I'm sure many of you who raised your hand who have flown to Chicago O'Hare have also probably spent more time in the airport than you had originally planned for due to some type of delay, whether it be weather or operational. So part of the research of this, and sort of the reason that this project was so important, was we wanted to try to get accurate forecasts so those delays are as minimal as possible. So as we go forward in the talk here, I would like you all to sort of think about this one question that I have here, because that's really what this project is framed around. So the question is, what if a simple shift in wind direction could change how an entire airport operates? So O'Hare is an extremely complex system with lots of moving parts. But what if something simple as the wind shifting from the west to the east could make such a big difference? So to actually answer that question, we first have to discuss what is a lake breeze. So you may have heard this by a different name before because it's called different things. Sometimes it's called a sea breeze, sometimes it's called a bay breeze, and sometimes it's even called an ocean breeze. And this is because these types of events are ubiquitous across the world's coastlines. And the name we give them comes from the body of water they come off of. So in the case of Chicago, Chicago is next to Lake Michigan. So since this breeze is coming off a lake, we call it a lake breeze. To sort of help you with the explanation, I've included this schematic here on the right, and inside the thick black box here, I've put the actual sea breeze part of the whole circulation. So a sea breeze forms during the day because the land actually heats up faster than the water temperature. So because the land heats up faster than water, we create low pressure over land and high pressure over the water. And air always flows from high pressure to low pressure. So the air starts to flow from the water to the land. We call this an onshore wind because it's blowing onto the coast. And we give this the name the lake breeze because it's coming from Lake Michigan. And why this is so important to O'Hare is that this is often associated with a very sudden change in wind direction. So we abruptly go from westerly winds to easterly winds. So that leads us to the question, how do lake breezes actually impact Chicago O'Hare in general? Well, it all has to do with airplane traffic, and because airplane traffic is sensitive to the actual direction of the wind. And specifically, it has to do with how planes take off and land. So planes always take off and land into the wind, both for efficiency and for safety. So if there's a sudden shift in the winds from this lake breeze, this can force a runway change, and depending on when this change has to occur, this can cause delays and disruptions. So given O'Hare's close proximity to Lake Michigan, we have to worry about these lake breezes. So to give you an idea of just how close the airport is to Lake Michigan, I put a map here on the right with 3 of the Chicagoland area airports. So anybody who lives in Chicago or maybe has flown southwest to Chicago may have gone through Chicago Midway or MDW. That's actually closer to the lake, but Midway is so much smaller than O'Hare, we didn't really focus on that for this study. O'Hare is here in the middle at 16 miles away from the lakeshore, so the lake breeze doesn't actually reach O'Hare every day, but it has the potential to given its proximity. And then I've also included Rockford, Illinois on here just as an example of an airport that's pretty far from the lake, where the lake breeze is generally not going to impact the operations at this airport. But this has all been very hand wavy. I do like to talk with my hands, but I also have a graphic to actually show you this shift in the pattern of air traffic. So this is the runway configuration for Chicago O'Hare, and the thick black lines here are the runways. So the one that I'm pointing out here is 9 left and 27 right, just as an example. So under completely normal conditions, the airport is going to want to run what they call west flow. So imagine the wind is blowing from the left side of your screen, or blowing from the left side to the right side. This is a westerly wind. Under these conditions, planes are going to land from the east, and they're going to take off to the west. However, now imagine that the wind direction in this case shifts from being from the right side of your screen to the left side. We now have to flip the airport on its head. So planes are now going to land from the west side of the airport, and they're going to take off to the east. So on my little slide here, that took very little time to make. But in terms of the airport, this transition can take up to an hour, which, depending on how much traffic is at the airport during that hour, could really cause delays. And second of all, to shift from west flow to east flow actually requires an extra air traffic control tower to be staffed. So not only do we have to worry about ground operations, we also need to make sure that we have enough air traffic controllers, which can be very difficult right now given the low staffing of air traffic centers. So we have to make sure we have enough air traffic controllers to actually be able to staff this as well. So just to give you an idea of how many planes actually can land at O'Hare in a given hour, I have a table here on the right of some of the United States' busiest airports and the amount of planes they can land in that hour under perfect conditions. So as I mentioned, Midway is considerably smaller than O'Hare, and we see that Midway can only land 32 planes per hour at a maximum. Well, O'Hare is actually toward the top of airports in the United States for landing 114. So at any given time, O'Hare has the capacity to land a lot of planes, and I've included the other ones on here for the sake of comparison, and since this is a stream for people all over the United States, maybe your hometown airport made it into the talk as well. So you might be asking, if O'Hare can land 114 planes per hour, do they actually ever get close to this limit? So to show you that, I've pulled up the airport arrival demand chart. This was for this past day, so for Wednesday. I pulled this Wednesday morning. And how you read this is the bottom axis is time. The lighter gray is in Universal Coordinated Time, UTC. But if you're not familiar with that, I've put the Central Daylight Time, or the local time at Chicago, in the thick black text below. The height of the bar is how many planes are going to land in that hour. And this thick black line is the maximum amount of planes that can land in that hour. If finally, the color shading here shows you how close to that limit they are, where red is over the limit, yellow is very close to the limit, and green is we have some space to move things around. So what we notice is that during some of the times of day, like at noon or 4 p.m. here, the airport is pushing their capacity, if not over capacity. So we need, if a lake breeze were to happen at these times, we might need to worry about it. So here's another example of airplane traffic. I really like to show this video in giving this talk because you can actually see the planes coming in and landing. So right now they're running east flow, and about halfway through this video, you're going to see this flip on its head right there, and now you're going to see how the airport was just shifted, where they're now all landing from the east. So this is a time-lapse video. So this made it look like this was a really quick process, but again, this takes about an hour. So with that, let's actually get into the science a little bit. So the data that was used for this study encompassed a 20-year period from 1996 to 2016. So I did this project in the summer of 2019. So we wanted to make sure we could get complete data to work up to this. And we focused on key meteorological variables. So we used wind direction, wind speed, air temperature, and cloud cover, just to name a few. And this data came from the ASOS network, or the Automated Surface Observing System. And on the right here is just a picture of what one of those looks like. These are actually at airports all over the United States. This is a joint project between the National Weather Service, the Federal Aviation Administration, and the Department of Defense. And this is actually the primary source of surface weather observations here in the US. So we pulled the data from our Chicago area airports. So with that, let's actually get into some of the results here. So the first thing we were interested in is frequency. How often are these events actually occurring at the airport? So on this graphic, I said I wasn't going to talk about Midway, but I did put Midway on here for anybody who was interested. The red bars are going to be for Midway. Those aren't orange. Those blue bars are going to be for O'Hare. The x-axis here is years, so you have 1996 all the way to 2016, and then again the height of the bars is how many events there are. And what we see is that the amount of lake breezes that reach the airport are actually very variable in a given year, where you have on the low end only 21 lake breezes at O'Hare in 2000, but on the high end there were 44 of them in 2005. So to get a better idea of sort of what we can expect, we look at the median value. So the 50% value, 50% of our observations will be below, 50% are going to be above. And that value for O'Hare is 35. So on average, we can expect there to be 35 lake breezes in a given year that reach the Chicago airport. So, or roughly 10% of the time. But the next thing we were interested in is the onset time. When are these actually reaching the airport? Because that's what we're really interested in. So to show that, I have a histogram here on the right. The bottom axis is time, again in UTC, and then the top of the bars is the frequency of their start time. And I've highlighted in the thick black box here the highest frequency of start time, and this is from 2 to 5 p.m. local time, with an average of about 3 p.m. So now that we know that most onset times of the lake breeze at O'Hare starts between 2 and 5 p.m., let's go back to our airport arrival demand chart to see what are the arrivals look like in that time frame. And what we notice is that within that time frame, O'Hare is actually pushing its limit right at 4 p.m. So if this event were to come through at 4 p.m., we might expect there to be delays. So if this is a well forecasted event, we might be able to move some of that traffic around in order to spread out the impact of us having to shift the airport. Alternatively, maybe we forecast that lake breeze to come through at 3 p.m. on this day. Well, we have some wiggle room there, so we may not have to actually do that much to keep the airport operating smoothly. So before I wrapped up my talk here, I thought I'd sort of go over sort of what federal funding has meant to my career and sort of what it can mean to students in the future. So my research, both at grad school and here in my undergrad research, has been made possible through support from NOAA, NASA, and the National Science Foundation. So from all of you, the taxpayers. And without this support, I wouldn't have had the chance to teach the hundreds of students that I have while here in my time at A&M. And I wouldn't have had the opportunity to work with amazing people at the National Weather Service in Chicago to help improve forecasts at one of the nation's busiest airports. So these kind of summer internships and government-sponsored scholarships allow students to contribute to public safety, to science education, and climate literacy, which is a big topic of today's talks, which has been wonderful. And was one of my favorite classes that I got to teach, teaching a class on climate change to sort of inform students on what climate change means to them. So the proposed funding cuts, it threatens student-led research projects like this one. It also can threaten those hands-on teaching experiences that come from doing an internship or being out in the field on a field project. But really, it also affects the pipeline of future scientists and forecasters. It can be really disheartening hearing about all of these cuts and what this means, and it might discourage people from going into this field. But to sort of look ahead on what continuing support from all of you, the public, would mean, specifically for me and maybe in the terms of this project, I'm here today because someone believed in students like me, and with continued support, I can continue to pay that forward. So I love what I do. I love talking about the weather. I love teaching about the weather, and I love mentoring students, and I love exploring the atmosphere. We have a term in the weather world for people who love the weather. We're called weather weenies, and I am definitely a weather weenie. And it is one of my greatest enjoyments in life to share that with others. And while doing all of this, the research I do also gets to contribute to data-driven forecasting, which can benefit local communities and it can benefit critical infrastructures like airports. So specifically in the context of this project, if I were to come back to this project with some new funding, I would love to expand this to other airports. There are many coastal airports throughout the country, such as San Francisco or JFK. I can think of many of them, or even Miami. That this would be a really cool study to do. And I'd also love to be able to evaluate some of the long-term trends of the lake breeze at Chicago to see how the effects of climate change might be impacting this phenomena. So with that, I am going to say thank you for everyone for sticking around here, and I'll open it up to any questions
All right,
that you might have.
that was a great talk. Can you hear me now, Ryan? I'm just making sure because you couldn't hear me earlier. Maybe not.
Sorry, I missed your question there. Could you repeat that?
I was just making sure you could hear me for a little bit. You can hear me now?
Yep, I can hear you now.
Okay, great. Yeah. Maybe there's a lag, I'm not sure. It was such a great talk and was quite different than some of the other talks that came before you. A lot of the people in the comments were really excited about your airport work. And one viewer wanted to know if, or just say that they would love to see your work like this, describing daily weather patterns at Denver International Airport. And I just wanted to mention that I really like Denver International Airport because they have all the conspiracy theories about how it was built and everything. Yeah, so that'd be exciting. Do you have any thoughts about Denver International Airport?
Expanding this to Denver would actually be pretty interesting. We could.
I think there's a lag, so sorry about that.
In Denver, you don't. It's not coastal. You don't get this land sea breeze circulation. Yeah, sorry about that. I have to open it on YouTube because I can't hear you through the streaming platform. But in Denver, you actually would get the mountain valley circulation, which is similar to the land sea breeze circulation, but instead of being driven by the difference between ocean or water temperature and land temperature, it's actually a difference in temperature between the mountain surface and the lower valleys. So you get a very similar daily circulation like this. So Denver would be a very interesting place to do this.
Yeah, it's great. Someone else wanted to know how you found out about this particular topic or why you started studying it in the first place.
That's a really good question. So I happen to love travel and I love airplanes. So when you do the hauling scholarship, they open up all this giant database of internships that are available, and I really wanted to work with airplanes. So I looked to see what I could find, and I found this project. And I emailed Gino and said, "Hey, I'd be really interested." We had an interview, and the first question was, "Do you like airplanes?" And I was like, "Yes, I love airplanes," and that's how it started. And ever since then, I've been doing land and sea breezes because they're so fascinating, and they're sort of everywhere.
Okay, that's really cool. I did an internship where I was part of a air traffic control group, and I feel like that's sort of coming on right now as I'm thinking about you talking about airports. I think I'm trying to see if we can fit in one or two last questions. Someone wants to know, how are the funding cuts going to affect those airport-specific sensor arrays?
So that's a great question. There have been some cuts to the National Weather Service, and specifically the technicians who work on those observation networks.
Mhm.
So we might see delays in getting those sensors repaired. And without those sensors, airports may have to delay traffic inbound or outbound, or they might even have to close the airport entirely, depending on the type of sensor that goes out.
Okay, that makes sense. All right, I'm trying to see if there's any more questions. Does anyone have any more? There was one who wanted to know how plane schedules are coordinated. I also noticed when you put up the plane times that there was the 4 p.m. had a lot, and 12 p.m. I think had a lot of planes.
Yeah, so I can quickly go back to that. So O'Hare, being a hub airport for both United and American, operates on their hub and spoke model. So they have a block where they try to get all their flights in so that you can make your connection, and then they all go out at the same time. So looking at a graphic like this, you get a pretty good idea of where they might put that block.
Okay, that makes sense. Yeah, I never knew that about how airplanes airports do their connections and everything. Okay, I think we have time for one more question. So it's gonna be the last one. Does architecture, like large clusters of buildings in a city downtown, affect wind patterns enough that planes can't take off or land at certain times, or is it negligible? Oh, it's kind of long.
Ooh, tough questions here. So there are height restrictions to buildings around airports because they do want to keep the departure and arrival gates, as they call them, clear. But I don't know much past that.
Okay. That makes sense. Okay. Well, everyone say thank you to our really great speaker today. I hope you all liked the talk on and quite different on airports. And thank you all for tuning in. All right. So I wanted to give a brief shout out to the people who are joining us internationally. I saw somebody tuning in from London who had just woken up. For me, I'm staying up late tonight, although in my time zone in Utah, it's not that late yet. I also saw lots of love for Tumblr earlier, and I was a Tumblr girly back in the day in my teenage years, so really appreciate all the people coming from Tumblr. All right, so we're about halfway through hour 13. I wanted to see how's everyone feeling. Whoever's been on for a while, and hopefully you've been enjoying the talks. Oh, someone's from New Zealand. Wow, that's exciting. Okay, so just to reintroduce myself, if you've just joined, my name is Vanessa Sun. I'm a PhD student and atmospheric chemist, and I'm going to be your host for the next couple of hours. Thank you for all the comments on the shirt and the earrings. I thought they were very appropriate. My necklace also says scientist on it. So for the next half hour, you're going to be hearing about another graduate student's research. So make sure to sit tight for that. Everyone's asking where the shirt's from. I got it from Etsy, but I don't remember which shop, so you might have to look up the text. So please remember that the speakers that we're having today and for the next couple of days are not representing the views of any specific institutions or employers, but instead being here and doing these talks in their own personal capacities. Before we begin, we want to remind you why we're here listening to the stream in the middle of the night, or it's the middle of the night for me. Weather and climate forecasts are important for you and to everyone in this country. Luckily, the United States has long been a world leader in weather and climate prediction. We developed the first computerized weather forecast to help you know what you can expect in the coming weeks. And we made the first computer models of the climate impacts of carbon pollution so you can know what to expect in the decades to come. To make these forecasts work, we've created an unparalleled network of observations using everything from weather stations to satellites, planes, balloons, boats, and floats. The resulting forecasting and observation system is a true scientific miracle, and we're excited to share some of that miracle here with you through this live stream. This miracle was made possible by decades of investment by you, the American public. But in recent weeks, funding cuts have put this miracle at risk. This has resulted in loss of observational coverage due to short staffing at weather stations, which is already hurting our forecasts. Laboratories dedicated to understanding our climate's future are being closed or shrunk, and funding for our basic understanding of the weather and climate is disappearing. Many meteorologists, atmospheric and climate scientists have lost their jobs, and programs that have trained generations of these scientists are being shut down. It doesn't have to be this way. If you like what you see here throughout this live stream, then we urge you to use the link on your screen to contact your representatives and tell them to save our forecasts, to keep the lights on for weather and climate science so that we can keep this miracle alive. Either way, we hope that you learn something about weather and climate through our talks. And please feel free to ask us any questions about our science in the chat. And we'll have a few minutes for questions at the end of each talk that we're going to be doing. So our next speaker today is Maggie Powell, who is a PhD student at Columbia University. She's going to be talking a bit longer than some of our other speakers. Since we have a bit of time after that we can fill, and so that means you might have some more time if you have more questions and things like that. And Maggie will be discussing sunlight and clouds over the tropical oceans, climate implications and insights.
Thanks, Vanessa, and thanks everyone for joining. It's been so fun to read all of the comments in the chat so far. So as Vanessa said, my name is Maggie Powell, and I am a PhD student at Columbia University. And today I will be talking about clouds and climate. But before let's see if I can advance my slide, perfect. Before I get into the science, I'll tell you a little bit about me and my path towards research. I'm still a student. And then I'll talk about climate models, kind of a climate modeling 101. Then I'll talk about clouds and climate and my research. And then I'm excited to hear your questions. So I am a second-year PhD student at Columbia, and I'm in the Earth and Environmental Engineering Department. And I'm advised by two professors, Pierre Gentine and Robert Pincus. And I'm interested in atmospheric science, clouds, and high-performance computing. And I think a theme to my work is that I'm interested in how energy flows through systems, whether they're small or big. So whether that's a tiny terrarium with water and energy flowing through it, or our atmosphere. So my path to research wasn't linear, and so I wanted to share it with you all. I started doing research as an undergraduate. I researched Arctic methane emissions. If you caught some of the talks earlier in the live stream, you might have heard about how methane is a really important greenhouse gas, similar to CO2. And for that research, I went to Alaska and got to study methane emissions coming out of all of these lakes. And I really enjoyed that work, but when I graduated, I wasn't quite sure whether research was the path I wanted to take. So I spent some time in the private sector. First, I worked as a consultant, and then I worked as a data scientist at a climate startup. And across both jobs, I got to see how weather and climate data is used by local and regional governments, NGOs, and businesses to make decisions on a day-to-day basis. And oftentimes they're making these decisions using data that is freely and publicly available because we pay for science in the US. But when I got to the end of my time at the private sector, I realized that there was still a lot of unknowns. Oftentimes our clients in the private sector would ask us a question and we'd answer as best we could, but we would also say there's a decent amount of uncertainty. And so a few times this would happen and I thought to myself, well, maybe I should try to help. And so I decided to come back to research and start my PhD. And as part of this degree, I'm doing research trying to improve our climate models. And I started in the fall of 2023. I will get into the science of clouds and climate, but I actually thought it would be fun to give you an introduction into how climate models actually work. And before you say to yourself, oh, that sounds kind of heavy, kind of technical for middle of the night, don't worry. I put together these slides in collaboration with my partner, who's a non-scientist, but who cares a lot about the climate. So they're coming at you from both the science and non-science perspective. And so I hope they'll be a lot of fun and teach you a little bit about how these amazing models work. So shout out to Shiv for helping me with these slides. It's a joint effort. So in the Earth system, there are many processes and interactions. And these include things like incoming solar radiation, clouds in the hydrological cycle, chemical processes, biological processes, and all of these complex things come together and form the Earth on which we live. But how do you capture such a wide variety of processes and interactions in a model? Well, let's start by defining what is climate. I'm sure a lot of you know by now, but climate is the prevailing or the average weather conditions in a region over time. When we talk about weather, we ask the question, what will the conditions be like tomorrow? When we talk about climate, we say, what are the average conditions here? And the result of messy and beautiful mixes of physical and chemical interactions on the global scale is climate. So there are many, many things that go into a specific region's climate. And it's one of the most complex systems on our planet, but that's part of the reason I love it. So how could you capture such a complex physical system? Well, at the end of the day, it's governed by the fundamental laws of physics. And because of that, we have fundamental equations, and so we can model it. So, okay, let's start with the basics. How can we do this? We're going to start with a super simple model of a closed water bottle and a light bulb. We have a few equations that can describe this simple system that can capture the essential physics. The first is the conservation of mass. So the water and the water vapor in the bottle, we could think of them as representing the Earth's atmosphere and oceans. And we have a fixed amount of matter or mass that doesn't just appear or disappear. And that's what the conservation of mass equation tells us. So the water molecules can cycle between the liquid and the vapor phases within our closed bottle, but they never really go anywhere. And that's roughly true in our atmosphere too. We also have the first law of thermodynamics, which says energy cannot be created or destroyed. So the light bulb adds energy to the water system, just like solar radiation adds heat to our Earth. And this energy has to go somewhere. It heats the water, it causes evaporation, and it's radiated away. The water bottle gives off heat. In the Earth's climate, incoming solar energy equals outgoing thermal radiation if the system is in equilibrium. But when greenhouse gases trap more heat, the system has to warm up to compensate. And then our final equation describing the system is Newton's second law. And so In our water bottle, there's not much room for wind, but when we think about the larger atmospheric system, we have temperature differences that create pressure gradients, and those drive air and water movement. So you might remember from physics class, force equals mass times acceleration. So these are these various accelerations and forces driving dynamical motion within our atmosphere. Okay, but the Earth isn't just a bottle of water and a lamp. There's a lot more going on here. Before we get too crazy, you might be just thinking, well, that's a lot of equations. How do we solve them? Well, that's where computers come in. No, not that kind of computer. We need something bigger. That's more like it. Supercomputers around the world run millions of the equations like the ones I showed on the previous slide to model what's really going on around the planet. Okay, so, but really, how do we model it? So we picture the Earth as a collection of vertical columns broken up into cubes of land, water, ice, and air. And when we do this across the planet, we get something that looks like this. So in each box, we solve a set of equations numerically using our computer that tells us about the physical, biological, and chemical processes going on, and tells us what is happening in that box in the next time step and what happens in the neighboring boxes. And what do we call this? It's a global climate model, or a GCM. GCMs are mathematical representation of the major climate system components. We've simplified a lot, but we've captured the main essence of what's going on. We have the atmosphere, the land surface, the ocean and sea ice, and their interactions. And the energy balance between these four components is the key to long-term climate prediction. Remember our bottle of water and the lamp, it's all about energy flows. Climate models are, in essence, computer programs. There are thousands of lines of code, and each model is created by a modeling group. They're across the world, and each modeling group consists of many scientists and computer programmers. These models usually run out to the year 2100, although they can run out longer, and they're advanced at roughly 30-minute time steps, generally at 100-kilometer grid scale. So that's 100 and 100 by kilometer grid scale at the horizontal level. And the smaller the grid scale, the more accurate, but also the more computationally expensive. With more boxes, you have to solve those equations more at each time step. But when you have that smaller grid scale, you can get better features. So looking as we increase resolution, you can start to resolve things like mountain ranges and valleys. And that's great. And we can see things that look closer to observations of the world in which we live. So a quick technical interlude, you're probably thinking 100 kilometers is way too coarse, and you're right. The processes that are going on in the atmosphere and other parts of the Earth system are happening at much smaller scale oftentimes. So things like snowfall and rainfall happen in smaller regions. And so in our climate models, we have to parameterize or make approximations of these smaller scale processes. These approximations are guided by our fundamental physical principles, and they also make use of our observational data. But they're a source of uncertainty. We're approximating something. And the equations we use to approximate cloud processes are one of the biggest sources of uncertainty in climate models, because we don't fully understand how clouds and aerosols impact the global energy balance. Clouds are particularly hard because they range a huge level of spatial scales. So for something like deep convection, this big massive cloud is a few kilometers across. But there's also processes going on in clouds at the centimeter scale or smaller. Think individual drops interacting with each other and ultimately going from cloud drops to raindrops. How do we capture all of this? So enough of the technical interlude. Let's get back to it. What do these global climate models actually tell us? Well, They're like an experiment in a computer. They let us play around with the various parameters of the Earth. And we have different emission scenarios of increased greenhouse gases, and we can see how those increases affect the planet. The model outputs temperature, humidity of different layers of the atmosphere, and precipitation. And it also gives us information about the ocean and the land, temperature, salinity, pH, and then the extent and cover of ice sheets. But a question that we all ask is, how do we trust them? So all models, including climate models, contain some level of uncertainty. But I like this quote from George Box, which says, all models are wrong, but some models are useful. So we can verify our GCMs by running them for historical time periods, not just the future. And then we compare the model results with the observed historical climate and weather conditions and see how well they match. We can also trust our models more by running ensemble models. So many models run at once with slightly different conditions. And this gives us a more accurate mean. It's like taking the average of a room guessing the number of jelly beans in a jar to get a better guess. So looking at the historical period, we can see the models, each model ensemble member is in yellow, the average is in red, and our observations are in black. That doesn't look so bad to me. So that concludes my How Do Climate Models Work 101. And now I'd like to move into a topic that is near and dear to my heart, clouds and climate. So you've heard me talk about the energy budget of the Earth. And this is important for studying climate science because at the end of the day, it's essentially an accounting problem. If you have more energy coming in than you have going out, and you have this imbalance, the system will warm up. So climate scientists spend a lot of time trying to track the flows of energy through the Earth system to make sure we've got our accounting right. And clouds are a huge component of the energy budget. They both block incoming radiation or incoming energy, and they trap outgoing radiation or outgoing thermal energy. So we can see that in a sky with clouds, the amount of sunlight reflected out is much bigger than if the clouds weren't there. That's the red box highlighted over on the left. And clouds also trap the outgoing thermal or heat energy. So when clouds are present, the amount of thermal energy coming out is much smaller than if they weren't. So we have these two competing effects, and in our present climate, the cooling effect of blocking incoming sunlight wins out. In our current world, clouds have a net cooling effect. But our world is changing. We've got this pesky data, this pesky imbalance highlighted at the bottom corner. And this is largely from human-caused greenhouse gas emissions. And just like the money in your bank account, this small imbalance grows over time, it compounds, and it warms our planet. And so returning to our figure of different emission pathways, we can see that by the end of the century, we're looking at a warmer world. And at the first order, the primary effect is which emission pathway we choose. But there's still some uncertainty for a given emission pathway. And because clouds interact so strongly with both sunlight and heat energy, small changes in cloudiness can have a potent effect on the climate system. So they're a large driver of these uncertainty shadings that we're seeing in the figure here. So a lot of my research is related to the question, how do clouds affect current climate and how do they affect climate change? So all cloud processes have the potential to change with global warming. Cloud feedbacks are any change in a cloud process that is caused by climate change and influences climate. And as I said, clouds are a big part of that energy budget, so they can have a big impact too. In general, high clouds amplify global warming because they trap that outgoing heat, but there's a lot less certainty about shallow or low altitude clouds. They are primarily affect our climate by determining the amount of reflected sunlight, and small changes in their fraction or their distribution across the Earth can affect that energy balance. So I'll conclude by talking about my research. I'm interested in cloud and radiation interactions for that second category of cloud and sunlight interactions. And particularly, I'm interested in something called 3D radiative effects. Before I lose you, this is the last technical slide, but like I said before, all models are wrong, some models are useful, and we have to make trade-offs and simplifications. So we know sunlight can be scattered by clouds in any direction, but in most models of the Earth's atmosphere, that radiant energy, sunlight, moves just in the up and down direction because it's expensive to calculate it in all 3 dimensions. And for the most part, that does a really great job. It gets us a really good energy balance. But there can be small 3D radiative effects that affect things like cloud circulation or local temperatures, and I'm studying those. So those are just 3 of them shown here. But in general, I'm really interested in how we can make our models better so that we can do better regional planning for climate resiliency and protect our communities. And with that, I want to say thank you so much for joining the live stream. My research is funded by the federal government, and I think that training the new generation of weather and climate scientists is essential so that this work can continue. And thank you. Looking forward to hearing your questions.
Thank you so much for sharing, Maggie. Can everyone tell Maggie that she did a great job? You can drop your questions in the chat. We're looking through them to see what you all want to know more about. We have a lot of questions on clouds, Maggie, for you. I like this one a lot. Do different kinds of clouds have different effects on the climate?
Totally. Let me go back to one of my earlier slides. So there's a phrase that I heard a professor say once that I really love. So clouds affect the climate because they're white and bright and because they're cold. So low clouds are warmer, they're lower down in the atmosphere. So in general, they're warmer. The reason cold clouds trap energy is essentially they radiate or release less energy up. So the warmer the cloud, the less of a trapping effect it can have. So in general, low clouds don't trap as much heat, but they reflect just the same in terms of the sunlight. So in general, low clouds have typically a cooling effect, whereas higher clouds, think like deep convection, those big, beautiful anvils and things like that, have a warming effect.
Someone else's question is a little similar to this. They want to know if cloud shape and size can be impacted by climate change as well.
Yes, that is an excellent question. I love that question. So there's a lot of complicated physics going on, but one thing is there perhaps a way that cloud shape and size might affect climate is if you had a cloud that was the same amount of mass, let's say, but it became skinnier and taller, it would have a smaller reflective surface than, say, a wider and flatter cloud. And that would affect the amount of sunlight that's getting reflected. And so that's one of the concerns, for example, for some of these shallow clouds over the ocean, that they might decrease in their coverage.
Okay. Robert had another great question, so I'm hoping it's okay that I ask another one of their questions.
Sure.
They want to know, is there a critical climate moment where clouds are no longer affordable by climate economy, or will there always be some type of cloud around?
Oh, it's a very interesting question. I love all these questions. So I guess it depends on the cloud type. I think in a warmer world, we're always going to have some we're always going to have clouds, but it's really the question of the distribution of the different types of clouds. But, you know, for example, some of these like very low, they're called stratocumulus clouds over that blanket a lot of the oceans. For example, there's concern that their coverage might decrease dramatically if we got to a certain level of warming. But I don't think we'll ever be in a cloudless world, fortunately, because I love clouds.
Someone wants to know what your favorite ensemble is. They also said, do you like CSM2 LE? I'm not sure what the LE means, but I've worked with some CSM2 output before.
Yeah, I mean, we're repping US climate and weather science here. I think I have to say CSM.
Okay. In a similar vein, another fun question. Do you have a favorite cloud shape or cloud type, maybe? Yeah. Shape and type?
Well, I guess I'll go back to my title or this slide of one fun thing is because my like family and friends know that I study clouds, whenever one of them takes a flight, I get a cloud photo, which is such a treat. But these we're seeing some shallow cumulus and then some deeper convection with some anvils. I would say just the kind of classic canonical puffy shallow cumulus is my favorite, but they're also beautiful.
I did a research project on contrails, so I'm quite attracted to those kinds of clouds specifically.
Nice.
Okay. So another more technical question from Annie Pinecone. I know clouds need seeds in order to form the droplets. Does high carbon output cause more clouds? Oh,
good question, Annie. So you're exactly right. We need something called a cloud condensation nuclei. The thermodynamics of our atmosphere mean that it's quite hard for a cloud drop to form without it. But oftentimes those are things like sulfate aerosols or sea salt. I think maybe organic compounds can be a condensation nuclei, but I don't think CO2. So high CO2 output doesn't cause, I guess, more and smaller cloud droplets.
Okay. Bob Hudson wants to know, this one isn't starred, so I'm hoping that the director for this can put it up. How does your modeling of clouds depend on anthropogenic aerosols?
Yeah, so I am running radiation models and looking at clouds, and I guess we choose the cloud droplet number concentration based on anthropogenic aerosol levels. And in our current model, we're choosing kind of a simple single value that's representative of conditions over the ocean. Those tend to be cleaner than over land. But it would be a really interesting improvement or development to, do some more detailed cloud aerosol modeling for some of my work.
I think this was one of the previous speakers. Henri Drake wants to know, there's a theory out there that the low marine clouds off the coast of California could potentially disappear. Have you heard about that and any thoughts?
Yeah, so there's a paper from Briant and Tapio Schneider that looked at this, where they basically ran a high fidelity or high resolution model of these low marine clouds, and they increased the CO2 forcing and the temperature, and ultimately at some point saw these cloud decks completely break up and disappear. And then in the second half of that paper, they actually, cool back down, and they see that it takes longer for these clouds to recover than on the ramp up. So it's a very interesting result. That study was done in an idealized framework. And so I would be interested in further probing that idea with kind of more of the large scale dynamics included. But it's a really interesting paper and kind of points to some of the tipping points in our climate system that we have to think about.
Great. I was wondering, since Maggie, you're going to be talking with me a little bit about the next session, if you wanted to go a little bit longer, or how are you feeling?
I'm feeling good. I mean, I'm happy to answer other questions, or we could move to the next component, whatever you think.
Okay. I guess we can move on. Unless anyone has any super pressing questions. Let's see. I'm double checking. I kind of like this one. Okay, so Sage wants to know, could certain areas with less cloud cover be able to affect areas that usually have more cloud cover? I know sometimes the lakes affect the areas around them, which can in turn affect farther states further away. Okay.
Interesting. So one thing I think about when I hear this question is that the amount of sunlight reaching the Earth's system coming from the sun is different at different latitudes. So up by the poles and the high latitude, there's a lot less sunlight than at the tropics. So for example, if we went from having, let's say 100% cloud cover for some low clouds in the tropic, and we move that to what used to have 0% up further, and then we had 0% at the tropics, we would still actually have a net warming effect because less sunlight would be reflected now that those clouds have moved. So I guess we would have to think about, do those two areas have the same amount of incoming sunlight? Do they have the same surface albedo? So the surface can also reflect sunlight coming out. But I like that question. It made me think.
I think we can do the last question. Mike Nader wants to know how you got into this field, but maybe this specific research area. They might have missed the beginning, and at what time.
Mm-hmm. Yeah, so I did some research about Arctic methane emissions. I was interested in greenhouse gases and their sources and sinks. And for this work, I was doing some modeling of the Earth's boundary layer and clouds. And while I really loved the methane component of the work, I became more and more fascinated about how the physics of our atmosphere work. And so when I came back to grad school after my stint in the private sector, I thought, okay, I'll try to learn more about clouds.
Okay, great. There's a lot of great comments and people who are joining. Somebody said, greetings from a fellow atmospheric scientist from Germany, and they really liked your presentation. But anyway, I thought that the last question would be a very good segue into our next phase that we're going to be covering in live stream. So everyone, please thank Maggie for a great talk and for answering all your questions. I'm watching the comments come in. Okay.
Thanks.
Yep. So it is officially past midnight in my time zone. That makes us at hour 14 of the weather and climate live stream, which means we have about 86 hours to go. For those of you who just joined, especially those who are waking up in Europe, apparently, my name is Vanessa Sun. I'm a PhD student and atmospheric chemist, and I'm going to be hosting for the next couple of hours. And for this segment, we're going to be shifting gears a little bit from the atmospheric specific topics that you've been hearing about for the last hour. And we're going to be joined by Ash Gilbert. Oh, great. I see Ash. Who will be chatting with me a bit about undergraduate research opportunities, especially a bit about the National Science Foundation research experiences for undergraduate programs. And please remember that we are not representing the views of any specific institutions or employers, but instead speaking in our own personal capacities. Before we get to that, we want to remind you why we're here listening to the stream in the middle of the night. well, the middle of the night for some people and the morning for other people that are just joining. Weather and climate forecasts are important for you and to everyone in this country. Luckily, the United States has long been a world leader in weather and climate prediction. To make these forecasts work, we've created an unparalleled network of observations using everything from weather stations to satellites, planes, balloons, boats, and floats. The resulting forecasting and observation system is a true scientific miracle, and we're excited to share some of that miracle here with you. This miracle was made possible by decades of investment by you, the American public. But in recent weeks, funding cuts have put this miracle at risk. This has resulted in loss of observational coverage due to short staffing at weather stations, which is already hurting our forecasts. Laboratories dedicated to understanding our climate's future are being closed or shrunk, and funding for our basic understanding of the weather and climate is disappearing. Many meteorologists, atmospheric and climate scientists have lost their jobs, and programs that have trained generations of these scientists are being shut down. But it doesn't have to be this way. If you like what you see here, then we urge you to use the link on your screen to contact representatives and tell them to save our forecasts, to keep the lights on for weather and climate science, and so that we could keep this miracle alive. Either way, throughout this live stream, we hope that you learn something about weather and climate through our talks. And please feel free to ask us questions in the chat and keep hyping us up that you've been doing a good job with. All right. Ash, do you want to introduce yourself actually for a little bit before we
Sure.
get questions and chatting?
Yeah, hi, I'm Ash. I'm a PhD student at University of Colorado Boulder. I'm I guess a fourth year, which I don't know, makes me feel old. Yeah, I started to study Arctic science. I will be presenting later in this live stream, but not necessarily about Arctic stuff.
Okay, great. It's good to know. I wasn't sure if Maggie was going to come back because I thought Maggie was asking some of the questions. So, not really sure. But if not, it's okay. We can. Okay, she got booted. Well, let's see. I don't know if she's gonna come back. If she doesn't come back, I guess we can. Oh, hi, Maggie. Welcome back.
Thank you. Sorry, my Wi-Fi.
Oh no, it's okay.
Out, but I'm glad to be back. Sorry about that.
Oh, it's okay. We just went through this the messaging about why we're here, and Ash also introduced himself. So yeah.
Awesome. Well, I have some questions to ask you both about your research experiences. So I guess the first one is, will you tell us about your first research experience, what it was, what you did?
I can go first. My first research experience was actually back in high school. I was a junior, and I got to spend the summer in a chemical engineering lab, and I helped sort of make they weren't DNA, but they were sort of like, instead of, it's like 4 bases. It was kind of like DNA. It was another way to sort of store data, but using, sort of DNA-like molecules, which was really cool. So that was sort of like, got me into like, I want to do research in college and sort of do science in general. Yeah.
It's so cool that you got to do that in high school. I was just curious how you got started doing that, because I didn't do that then.
My high school had we had an engineering magnet program, so I'd been taking engineering classes since I was a sophomore, and they sort of had an opportunity if you wanted to do research for the summer, you could, so.
Okay, cool. Well, I'm coming from a very different perspective because I did not even like science when I was in high school. I really liked math growing up, but didn't really vibe with science as much. And originally went to college. I wanted to be a writer, and we were very far from that. So I only got to start doing research and getting into science a little bit later in my undergrad. And I did one of the aforementioned National Science Foundation research experiences for undergrads. I was doing theoretical mathematics originally, and my program was at the Mathematical Sciences Research Institute, which is an independent research institution, like specifically for math. So it might be quite a bit different than scientific research, but that was my first experience.
Awesome. Okay, so then I want to hear about your first REU experience. And for those watching online who might not know what an REU is, can you tell us about it?
Sure. So an RU is an undergraduate program for, it's a program for undergrads, but they're all funded by the National Science Foundation. And basically what happens is you apply, and they usually take somewhere between like 10 and 15 students. They're housed at universities or other institutions. And then the university or other institution, using funds from the NSF, will pay you to come out and do a summer of research for like 10 weeks. And so you get to do a research project during that time. Sometimes you'll get career development. At least the one hosted by my university, we always give them a Python boot camp before they showed up so they knew how to code. But it's a really good experience to sort of just see and taste what research is like, without having to do like an unpaid internship or something like that. But it can be really, really impactful.
Yeah, I think it's important to mention that it's really also an exploratory space for students to try out research. Like, it might not be the case that students end up going to grad school for that particular topic or something in the future, but it gives them a chance to just try out and see what research might be about, and give an experience and also get paid while doing it.
Awesome. And so what makes an REU different than doing research at your home college or university?
I like what Ash was saying earlier about some of those professional development opportunities that they offer. Since I was in math, mine had LaTeX. I don't know if we did a workshop. I don't think we did a workshop. Some of them do workshops, but that's like that was sort of built in. And there's some kind of like professional development component usually to these programs. Mine was really interesting because when I did the program, it was like the 15th year of the program. So it was a super long running program. And what they did was they did something really special that year, because they brought speakers to all these different panels and to talk about like their experiences in grad school and things like that. But they were actually all alumni of the program, which was really cool that my program did this. But we got to just hear from like all these different people who had went through the program before to talk about where they are now, and like how, if they went to grad school afterward, like how that trajectory was. And to kind of see that program's legacy was very different than I guess what you would get if you were just sort of like volunteering in the lab in your university. And they really kind of give you a sense of community and to meet other people. Also people from other schools. That was a big part of why I went to RU, and it was special about mine. There was a person from Guam and lots of other schools across like the country. And I think that was really nice for me to meet all these other people, because I went to a school that didn't have math research opportunities for me. And it was very important that I'd be able to meet mathematicians at like other schools at that point in time. I'm sure it's the same for scientific RUs as well.
Yeah, I'd also like to add that they can be a really good experience, particularly if your home institution, like not all institutions like are like really big universities. So if your university is not strong on research, you can come to an RU at a university where they are strong on research, and
Right.
you can get that experience with really good researchers.
Yeah, so I mean, I think the question that maybe a lot of us have is then, how do you anticipate the potential loss of funding for REUs would affect the new and the next generation of scientists?
It's not going to be good. But like, you know, an REU can be how somebody like gets interested in science. So like we're just sort of cutting off that stream of new baby scientists, like of just that interest in scientists in general. And even if you don't like go into the fields that your REU is in, you know, it still gives you like may give you passion for science, or maybe it sort of shows you, hey, this is not what I want to do. Either way, you're sort of, you know, kneecapping sort of the training pipeline for scientists.
I want to reiterate that I was in a position when I was in undergrad where I went to a school where I didn't have research opportunities, and like the only way that I was able to really get that and like move forward with my research career was through doing a specific like NSF REU program and funded federally as well. So it's really hard to hear that like this year a lot of I'm assuming across a lot of other fields, but I know that for like atmospheric science, I've heard of some being cut. And like at my university, our program isn't running this summer, and it was something that really encouraged me to get started in my research career. And I basically tie everything that like I've been able to do from being able to do that specific program and the empowerment that like the people who did that program gave me. Like I'm still friends with people from like my REU program. Some of the directors who ran it like went to my master's defense like last year. Like I think that those bonds were just really important for my development to as a researcher, and that I can see how that would have, you know, the same effects for all different kinds of young researchers. And it just makes me sad that like we won't be able to sustain those programs without funding. And we're already seeing that like this year. So
yeah, I'll just add on, my school is also not running ours. And I also trace a lot of my career, you know, I've had a bunch of research experiences. The REU is one of them, but I think the REU, for at least for my grad school experience, the REU was really, really impactful. The person that I worked with during my REU, I continued to work with her through the rest of my sort of undergrad career and sort of sporadically on this project. And I ended up sort of from that REU project, I ended up writing a proposal for my NSF fellowship, which I got, and that funded 3 years of my grad school.
wow.
So like I can point to that and say, yeah, that REU made a difference in absolutely made a difference in my career. You know, I don't think for some people who get for sort of shorthand, the NSF Graduate Research Fellowship provides 3 years of funding for graduate students who apply. They usually give about $2,500 out a year, and they give them to sort of senior undergrads to second year grad students. This year they only gave about 1,000, so that's like 1,500 students who do not have grad school funding, and for some of them that may mean the difference between not going to grad school and going to grad school.
Yeah, I also just want to add, I think not having REUs or not having as many grad students, it doesn't just hurt those, you know, young scientists. It also hurts the whole field. From my experience working with undergrads, there's such an amazing, you know, exchange of ideas. They approach problems in a way that I hadn't thought about. And I know from talking to professors or senior researchers in the field, they feel that way too, that it's really the collaboration between generations of scientists that allow us to, you know, push the needle forward. And so it's not just, you know, hurting in the future. It will be, I think, losing this kind of collaboration almost immediately.
Yeah, I was really excited because I really wanted to mentor through the RE program at my school. And like my biggest dream is to like one day be able to direct my own RU program because like mine gave me so much. not having that mentorship aspect, I guess we can probably have someone like at our university, but we wanted to have a student that was coming in from Florida or something like that, and it was just really influential as like me being a grad student, getting to mentor somebody, them getting a mentor that's like not just at the professor level, and like really that interaction across different scientific generations, as you were saying, Maggie.
Yeah. I'd also like to add that, at least the RU in my department was formed and spearheaded by the graduate students. We all have significant involvement in the RU, and we all look forward to mentoring them and seeing them every summer, and like losing out on sort of just having them here and that mentorship experience, because I've had so many amazing mentors, both sort of, professor, research scientists, and graduate students throughout sort of when I was an undergrad, and I was like, I want to be able to give this to other people. I want other people to have this amazing experience that I did, and to sort of see that people won't have that. It really hurts.
Yeah, and just looking at the chat, I see that a lot of folks out there have had similar experiences or feel the same way. So Marie says the leadership development aspect also of NSF graduate fellowship is really important, shouldn't be underestimated. It gives students the freedom to explore their curiosity in a way they can't otherwise.
Paulina earlier in the chat also mentioned that their RU was also in math, and that they changed research directions even though they did like it, and that it was amazing that they got the chance to try out different fields. And I think Henri said something similar to that about trying out new things, but I can't seem to find that one. It was further up in the chat, I think. If anyone in the comments has any questions about any of these, we'd love to be able to answer some. Greg Lender mentions that the National Renewable Energy Lab in Colorado has various opportunities for summer research stuff. I wanted to bring that one up because I actually interned at NREL. I had, this is not like the NSF funded REU programs, but I did some internships at NREL, who they're mentioning, in Florence Livermore, and National Lab, and being able to do different internships and different kinds of research experiences was really interesting. As a actually, I wasn't an undergrad anymore. I was like, I did those right after I graduated, but those programs are also being impacted by funding cuts. Because they're also government labs, just not like the NSF funded programs.
Yeah, those are is NREL Department of Energy?
Yes, it is.
Okay.
Yeah, it's the only national lab focused on clean energy, and it's the smallest one too. I was in the wind power group, and I really liked my supervisor there. I still keep in contact with her. And she's been a great mentor to me, and those kinds of programs have been good too. I'm not as sure about like the government internships in terms of like NOAA. I know that a lot of people do those internships though. So
yeah, one of my friends is doing those this summer.
Okay, let's see if there's any more questions. Do you see any good ones, Maggie? Sure. Or comments.
Looking through, yeah. I could also talk about my first research experience, which was
sure
also NSF funded. Yeah. So I did research in Alaska for the summer, and well, it wasn't an REU, it was an NSF funded project, and it brought students from universities and colleges across the country. And I thought one of the coolest parts of that program was we actually did some community engagement. So we were doing field work out in the Yukon Delta of Alaska, but we did several days of community meetings and things like that in Bethel beforehand, talking with the community there because they were being affected by permafrost thaw. Houses and things were being like falling over because of the literally sinking and subsiding landscape. And having, I guess, NSF funding to engage in the community whose lives were most directly linked to the science we were doing was really eye-opening for me. And just having that kind of, I don't know, connection with the community, connection with students from all over the country was really special. And just like both of you said, I don't know that I would have gone into research if I hadn't had that first experience that was funded by NSF.
Yeah, it's really cool getting to do the local things when you go to a program and, you know, get to see the impact the local population or work with them. I think we have time for Sage's question. Yeah. I wasn't sure if you wanted to read it, Maggie. I can read it.
Oh, yeah, sure. So Sage says, would you guys have
Sorry, you can read it.
Okay. Would you guys have any tips for maybe in the future as someone who wishes to go into biology? I could approach others in climate fields to collab.
Yeah, absolutely. For example, I know there's someone in my department who's looking at sort of occurrence of disease in Malawi and how it conflates with climate factors. I don't remember the disease specifically, but like, yes, absolutely. Climate is very interdisciplinary. I think it was, Kate Marble, her talk earlier today was sort of talking about basically climate touches everything. So absolutely. And we'd be more than welcome. We'd be all more than happy to collaborate with you.
I would say that I think that it's a really interesting thing for undergrads to be able to like cold email professors and sometimes just talk to them about their work or just talk about like their professional journeys or something like that. I've had a lot of great conversations through just emailing not random researchers, but people that I was interested in. Like, for example, when I first got into atmospheric science, I really wanted to know about rocket emission impacts. And I emailed, actually, you might know them, Darren Tui at CU Boulder.
You emailed Darren?
And he talked to me for 2 hours. 2 hours.
He will talk to you off.
And it was while I was considering grad school in earth science, but I hadn't like committed to it. Like I didn't feel confident in it. And he literally talked to me for 2 hours just about like what he's done in the past. And like, it really encouraged me to apply to grad school and to really do that. And like, it was just a random conversation I had. I mean, I didn't end up working with him. But like I really encourage for anyone who's an undergrad here, like if you're interested in doing doing work with a professor that you haven't met before at your university, like, you know, try to put yourself out there. Or if somebody like on LinkedIn has a job that you're really interested in that sounds really cool, like I encourage you to like reach out and just chat with them, because like I feel like it's a lot about being proactive and just like learning from about different kinds of work that you could do that you might not know about without having conversations with different people. Not saying that you should email professors your conspiracy theories. Please don't do that. I've heard that some physicists have gotten a lot of those emails like all the time. But, you know, if you have a compelling reason and things that you might want to chat about, maybe you've read some papers by an interesting researcher like that, is something that I would encourage people to try out doing.
Yeah, I will second cold calling or cold emailing professors. They will happily, most of them will happily talk your ear off about whatever you want. scientists are happy to jabber on about science.
Yeah. All right. I see that it's 12:30 my time zone, so we'll transition to the next segment. We're about halfway through hour 14 of the Weather and Climate live stream, which means we have 85 and a half more hours to go. I hope you enjoyed hearing Maggie, Ash, and me chat for the past half hour about some undergraduate research experiences and things like that. For those of you who have just joined, my name is Vanessa Sun. I am a PhD student and atmospheric chemist. And now that we've had some of that chatting time, we'll be getting back to some of the scientific technical talks after this bit of a break. Katie Mills is going to be speaking for the next few minutes, and I'm really excited to hear from them. Please remember that our speakers are not representing the views of any specific institutions or employers, but instead in their personal capacities. So before we get to that, we want to remind you why you're here listening to this stream in the middle of the night or maybe early in the morning. Weather and climate forecasts are important for you and to everyone in this country. Luckily, the United States has long been a leader in weather and climate prediction. We developed the first computerized weather forecast to help you know what you can expect in the coming weeks, and we made the first computer models of the climate impacts of carbon pollution so that you can know what to expect in the decades to come. To make these forecasts work, we've created an unparalleled network of observations using everything from weather stations to satellites, planes, balloons, boats, and floats. The resulting forecasting and observation system is a true scientific miracle, and we're excited to share some of that miracle here with you through this live stream. This miracle was made possible by decades of investment by you, the American public. But in recent weeks, funding cuts have put this miracle at risk. This has resulted in loss of observational coverage due to short staffing at weather stations, which is already hurting our forecasts. Laboratories dedicated to understanding our climate's future are being closed or shrunk, and funding for our basic understanding of weather and climate is disappearing. Many meteorologists, I keep stumbling on that every half hour, atmospheric and climate scientists have lost their jobs, and programs that have trained generations of these scientists are being shut down, such as the ones that you just heard about for the last half an hour. But it doesn't have to be this way. If you like what you see here through this live stream, then we urge you to use the link on your screen to contact your representatives and tell them to save our forecasts, to keep the lights on for weather and climate science so that we can keep this miracle alive. Either way, we hope that you learn something about weather and climate through our talks and through our live stream. So next up, we have Katie Mills, and Katie Mills is a programmer providing petabytes to the people. They will be talking about how science belongs to everyone, open data if you can keep it. Whoever is directing, hopefully you can put Katie on. Oh, great. Katie, can you hear?
I sure can. Can you hear me, Vanessa?
Yes, you're all good, and your screen share is working properly.
Terrific. Thank you for that colorful intro. Good evening, everyone. My name is Dr. Katie Mills. I am a research software engineer and data scientist based here in Brooklyn. And I have been focused for a number of years now on studying data about our oceans, including data collected by NASA, NOAA, and our colleagues from around the world. Before I press on with that material, though, I just want to give a big +1 shout out to the conversation that just went on in the little chat in the half hour before this. I never realized that I wanted to be a research software engineer when I was first coming up in my undergrad and in grad school. And it was my undergraduate research opportunities that gave me the chance to discover my passion for data science and for research software engineering, things that I never really realized would be my scientific motivation going forward. And now fast forward 20 years, and I've been doing this for 2 decades now, building different kinds of software and data analysis tools for researchers that I've had the privilege to work with. And none of that would have happened without my undergraduate research opportunity. And then the other thing that I will just +1 from that conversation, just because it was so good to hear, is Yes, cold email people, show up at their labs, talk to them when you start out at, a grad school that you're at. When I started in grad school, I wanted to participate in the ATLAS, like the particle physics collider experiment group, when I was in grad school. So I just showed up to the guy's lab and said, "Hello, I'm your new grad student. Congratulations." And he didn't argue with me, and the rest is history. So I got to participate in a really exciting experiment just by showing up, right? So big +1 to all that. Anyway, back to my talk for this evening. So like I said, I am a research software engineer focused on oceanographic data science. And I'm speaking with you tonight to share a little bit of my research interests. And I hope by the end of the session, you can see why I think open data in oceanography is so exciting and so important, not just for the scientific community, but for the public, for everyone out there listening tonight. So before I press on here, Vanessa, I like conversations a lot more than I like lectures. So
Okay.
if you want to jump in with a question, either from yourself or from the audience, you think something could use clarification or a comment or something, just don't be shy. Okay.
All right. Yeah. I'll keep an eye on the comments.
Okay, great. So also, I don't have slides tonight. I got my start in research software development, building web apps for scientists. So everything I have to show you tonight is a website.
That's cool.
So I did not make these websites. They are mostly provided by NOAA and our colleagues. But so collecting data about our oceans is not new news, right? This is not some hip new fad that we just started doing. The US has been doing this literally for centuries. Right? NOAA has this nice little historical website that I hope you can see in my, you can see that there, that traces the history of ocean measurements conducted and directed by the US federal government all the way back to an order from President Thomas Jefferson in 1807. So we've literally been doing this for over a couple of centuries now. Back then, and I'm sure for centuries before that, seafarers needed to know things about ocean currents so that they could successfully navigate their shipping lanes and their, whatever else they were doing out on the ocean. And they needed to know about bathymetry, which is really like a $5 word for ocean depth, so that they could know where were viable places to anchor their ships, for example. So this has always been interesting to us. Also, for the historical perspective, if you head on over to NOAA's National Center for Environmental Information, great environmental data scientists working out of NCE. I'm a huge fan of theirs. You look at their World Ocean Database page and you scroll down to the bottom here, scrub down and read that. The latest major release of the World Ocean Database includes a bunch of data, including casts from the second voyage of Captain Cook, all the way back to 1772. All right. So the point I'm making here is this is not a new idea. Right? We've been doing this for centuries, and it's been crucial to operations of not just science, but commerce and exploration and many other things. The ocean touches us all. And so monitoring that data is really important, really valuable. So fast forward to modern times and talk a little bit about how this ocean observation data is used. And like I was alluding to a second ago, it's not just scientists, right? Fisheries, militaries, commercial seafarers, lots of other people use this data to do their jobs on a daily basis. Jobs like making more accurate and earlier predictions of dangerous weather so we can respond to them, both to keep ourselves safe and to protect our interests on the coasts. Doing things like operating underwater sonar more accurately. Turns out water density will bend sonar beams just like light bending through water. Right? So we need to understand with detail that density of water. Assessing impacts on commercial fishing, for example, right? As climates change, fisheries can die off. That has massive economic impacts on people. Predicting and mitigating dangerous algae blooms that can poison not just marine life, but people that are exposed to it. We need to be able to predict and track these things. And the list goes on, right? There are many, many applications for this data. We measure a lot more things than Captain Cook did these days, right? More things than just currents and ocean depth. Temperature, salinity profiles deep below the ocean surface are widely measured. but also things like biological markers, things like dissolved oxygen, nitrogen, pH, chlorophyll, lots of other stuff, so that we can understand both the physics and the biology of our ocean systems. So one question you could ask at this point, if we're excited about collecting all this data, is how? How do we do it? So before we jump into my personal work as an engineer and data scientist, which admittedly can get arcane, I want to start by showing you how the US and our colleagues around the world, through its scientific organizations and its universities, collect this data out in the field so we can learn about our oceans. Because honestly, it's really cool stuff. So let's start with the toys. If we go on to another NOAA page here, they give us a big list of exploration tools. So all these, there's dozens of different devices and methods for making measurements of our oceans, from autonomous underwater vehicles that can, pilot around underwater making measurements, conductivity, temperature, depth probes that can be dropped off the side of ships to make measurements and pull water back up for study, to things like remotely operated vehicles, a million different kinds of sonar, expandable bathythermographs, all kinds of different stuff. I'm not going to go through every single thing in this page tonight. We would be here till dawn. But there's many different tools and techniques out there for measuring our oceans. So let's talk about a couple of specifics here. Expendable bathythermographs are a really cool one. So what we have here is somebody loading an auto launcher for XPTs. And since the 1960s, XPTs have been kind of a popular probe for making these temperature and salinity profiles. So XPTs are single-use probes that are launched off the side of a ship, kind of like what's illustrated in the photograph here. And they make temperature and salinity measurements as they sink through the ocean at a known rate, creating a profile over depth of these variables, and then transmitting that information back to the ship through a couple of wires that are attached to a computer on board this ship. So you can see someone here with an auto launcher loading up new XPTs for making measurements as they sail along on this cruise. Each of those cylinders you see is an XPT that can make one of these profiles that looks something like the figure below. So this is super tiny. Let's try and embiggen that a little bit. Oh, it's still super tiny. Okay, now it's big but pixelated. But so this is what some of these profiles might look like. And let's start with the tile in the middle here. So this is on the horizontal axis temperature, and then vertically we're going deeper and deeper underwater. And this is a pretty normal looking temperature profile. You might not be able to see it on your screen, but there's a nice little vertical bar at the top here where the temperature is consistent with depth. That's our mixing layer, right? Where surface effects like winds, things like that, mix the water and keep it sort of a consistent temperature until we get to a very sharp thermocline here where the temperature is dropping rapidly until that rolls off and becomes a little bit more constant as we dunk down kilometers under the Earth's surface, or under the ocean surface, rather. Same thing for salinity over here on the right. So these are the sort of measurements that are really the stock in trade of physical oceanography, temperature and salinity measurements here. So what else do we have?
Before you move on to a different instrument, I just want to say that Pasta Poodle mentioned that they saw their first bathysphere this Sunday at the aquarium.
Heck yeah.
That everyone thinks that these tools all look like fun.
They do look like fun. They're something, like I said, deployed from the backs of. Can I get back to my? Here we go. Deployed from the backs of ships like this. So grad students and postdocs like yourself will go out on cruises and make sure these things stay maintained and manned and collect data as they go along. Like I said, this one is like an auto launcher. They're also launched from handheld devices as well. This guy's so good, he's not even looking at where he's firing the thing. But that sort of thing. The upshot of this is that this data gets collected along cruise lines, right? Sort of like what you see right here. So as we sail along one of these cruises, we're deploying these XPTs off the side to make these measurements. We end up getting really high quality measurements from these. Here's another example of Go Ship's standard lines for making ship-based measurements as they sail along. So we get really high quality measurements for these, but they're confined to the paths of these cruises. that either we hitch rides on as cruises of opportunity, or we conduct ourselves as science vessels. So here on this this webpage here, we have the reference paths for the Go Ship program. And that uses more CTDs than XBTs, but it's the same idea, right? Detectors that are deployed off the side of ships as they sail along and collect this data as we go. So this makes, like I said, really high quality reference data for us, but there's big gaps between these paths. Right? It's really difficult to get coverage of the oceans with a program like this. So enter the Argo program. So if you've been watching all night like I have, my colleague Sarah Perkey told you all about Argo earlier tonight. She did a great job, of course. So I will try and be a pale shadow of what Sarah talked about earlier. So for about 25 years now, there's been this oceanography program called the Argo program, which is this fleet of about 4,000 robots that drift around the world's oceans, making measurements of things like temperature and salinity, but also markers of life in the ocean, like pH and nitrogen, dissolved oxygen, stuff like that. So to give you a sense of scale, the United States is responsible for about half of the Argo fleet, so about 2,000 of those 4,000 robots. Let me just disclaimer here. I want to say very clearly, I am not formally affiliated with the Argo program. I do not speak for them. I'm just a really big fan of their work and a consumer of their data. I think they do really cool stuff. And I want you to understand a little bit about where this data is coming from, because I think it's exciting and fun. So one of the really cool things about these ocean robots, and that's what this big yellow fire hydrant looking thing here is that they're completely autonomous. Once these guys in the picture here chuck it over the side of their ship, an Argo probe can operate autonomously for about 5 years, collecting scientific measurements of our oceans. So we can see in the next diagram what those probes get up to while they're bobbing around our oceans. So that photograph from the last web page is this float deployment, step 1 here. And the neat thing about these Argo probes is they can automatically modify their density so that they can sink to a drifting depth or a parking depth of 700 to 1,000 meters around here. And then they just drift. They have no propulsion system. They just drift on the current for 10 days until it's time to take a measurement. When it's time to take a measurement, they squish down to get denser so that they can sink down to typically 2,000 meters is the density or is the depth that most Argo profiles are measured from. And then they expand a little bit. They have a little bladder that they can expand to reduce their density and start floating back up to the surface. And as they do so, they start making measurements of all those properties that I was talking about: temperature, salinity, biogeochemical properties for part of the fleet. This picture is a little misleading in that it only shows 2 measurements here, but really an Argo profile can have hundreds and hundreds of measurements as it moves up the water column. Once it gets to the surface, it extends a little antenna, beams the data back to us beams the data back to the folks at the Argo program for collection and distribution. So the result of this effort is truly impressive. This is a map of the last known locations of all of the current Argo fleet distributed by Ocean Ops. And as you can see, the coverage is tremendous. Right? We've got unprecedented coverage of in situ measurements of Earth's oceans. So to give a little sense of scale here, the engineering goal for Argo is to place a probe every 300 kilometers, like 300 by 300. And so that, if you relate that back to Maggie's talk earlier, Maggie was doing modeling on 100 by 100 kilometer grid points. So there's an Argo probe for every 10-ish of Maggie's grid points. So we're at least, approaching the order of magnitude there with the Argo array, which again, incredible accomplishment. Captain Cook could only have dreamed of this kind of coverage. So other profiling techniques like the CTDs and XBTs I talked about before that rely on science vessels or container ships to make these measurements en route would be overwhelmingly expensive to try and collect this density of information. Right? There's no way we could do that in terms of price. There's no way we could justify that in terms of just sheer emissions from trying to sail around and do this much coverage with manned vessels. So an autonomous array like the Argo array is really indispensable. So
lots of viewers are impressed by how many are on here. I don't know if anyone saw, but when you first pulled it up, my eyes were like bugging out of my head.
Yeah.
It was a lot.
Yeah, the fleet is about 3,800 probes right now, which is bananas. Right? That is so many in situ measurements. And like I was saying, it's approaching the ability to like approach the scales of modeling, like what Maggie is interested in, to provide boundary conditions for models like Maggie's. So cool. That's what Argo does and how it works at very, very high level. But I like to talk I'm running out of time here, but I like to talk for what little time I have left about this step 6 here. What happens here when these probes beam our data back to us? So I talked a lot about Argo probes and XPTs because I think they're a lot of fun for people to know about. But the same question can be asked for all of the data observing projects that I scrolled through a couple of minutes ago. Where does the data end up? Where does it go? So by and large, this data is made available to scientists, to students, and to you, the public, completely for free. So here is out of UCSD, the Argo page describing how to get a hold of Argo data. I won't take you through that, but it's all free. It's all available. You just grab it for yourself and your own purposes. And there's many other such efforts. The World Ocean Database from NOAA's National Center for Environmental Information, mentioned this earlier. It's an incredibly valuable resource maintained by NOAA and by NCEI. So,
Katie, I just want to let you know to watch your time if you were going to.
Sure. Yeah. Okay. So let me take my last couple of minutes here because I know I could do this. I could do this all night to get onto my research a little bit. This is all just kind of background review. So the free dissemination of data that you see from the World Ocean Database and from Argo and from many other collaborations follows from a school of thought that we call open data, which brings us finally to my personal interests and my work. So the concept of open data in the sciences started to get really buzzy in the early 2000s when the internet basically got mature enough to support it. Okay? So the internet got mature enough to make it possible for scientists to start thinking about the realities of sharing their data with each other and with you, the public. So traditionally, scientific data sets were kept private by researchers who collected them, both because they wanted to publish on them, and also because it just wasn't practical to share really big data sets pre-internet. This was the time when CERN and Fermilab were airmailing big magnetic reels back and forth to each other, right? That was the best we could do before we had the web. But the web came along, and in the 2000s, we started seriously asking, what if we didn't keep our data locked up in universities and labs? What if we made it freely available for everyone to examine and use? The benefits of this open data paradigm are manifold. Right? New discoveries could be made by fresh eyes looking at this data. Cross-disciplinary studies would become easier. And one of the most important parts, in my opinion, is that open data creates an opportunity to bring our science to you, the public, to engage your curiosity about your world in the form of educational activities for students, transparency on what your federally funded scientists are doing and discovering, that sort of thing. I firmly believe that the public should be able to come along for the journey of discovery scientists like me spend their lives on. It's your world too, and discovering it is a huge joy. We'd all like to share that with you. That's why I think open data is so important. But then, of course, reality comes to play. So, this idea of open data sounds great, sounds fantastic. We're going to make all this data publicly available. There's just one problem. It turns out that scientific data can be really hard to understand and consume, even for other scientists. So here we have the user's manual for the World Ocean Database. And if we look closely, it's 134 pages long. You needed that much PDF just to understand how to consume this data. Now, don't misunderstand me here. I am not pointing this out to criticize. NOAA has done a fantastic job here, carefully documenting the data that it's sharing. But you can see that consuming this data is not just going to be like, reading a Reddit thread somewhere. We need to do the work to make it easy, not just to download and access our data, but make it legible, right? Make it easy to consume and easy to use. And that's what my work has centered on for the last few years. So I've only got 5 minutes left and I want to do questions. So I'm going to quickly jump ahead to one of my other projects. So something I've been volunteering with for a long time now has been a project called the International Quality Controlled Ocean Database. And so what this project is about is about taking all that data that we collected and curating it, making sure that the best possible quality control has been applied to this data so that future consumers can do so confidently, right? They know that they look at the IQUAD flags, that experts have reviewed this data. This data has been through the best of our algorithms for ensuring its quality, and they can consume it with that confidence that the expert knowledge that went into reviewing it has been folded in to that data set, not requiring future consumers of this data to have that really intimate expert knowledge that takes a whole career to build. So there's many, many more projects like this, from quality control of data to data search and distribution is another passion project of mine. How do we make it easy for you to find and cross-reference all the centuries of data we've collected about our oceans? All of these things are a crucial element of oceanography, something that we really have to pay attention to, not just collecting the data, not just doing the ocean science, but by making sure that information collected in this way is legible, is accessible, is consumable by scientists, by students, and by the public. We've got 4 minutes for questions. What do you got?
That was a really great presentation. Well, I mean, you went through a lot of really interesting websites. Sage wanted to know if anything specific inspired you to jump into oceanic data. You didn't really talk about like your trajectory in terms of when you started getting into oceanography.
Sure.
So spend a bit talking about
my
that.
trajectory was weird. I started life as a nuclear physicist and particle physicist. That was my original interests. But I just started volunteering with these IQUAD folks, actually. The oceanography community was really open and really engaged with the idea of doing this quality control work, right? Thinking about how to distribute this data effectively. And the more I worked with them,
when were you doing the volunteering? I was curious, like what stage in your life journey?
This would have been postdoc era. Okay. So I took a little detour between a couple of postdocs to work on this idea of interdisciplinary collaboration between private sector software developers and the sciences. And so we, stood up this little matchmaking service that would, match developers that wanted to contribute to the sciences with scientists that wanted that kind of help. And that's how I found this project originally. And I was so inspired by not just the opportunities for doing good science that the oceanography community had, but by their openness to engaging with these ideas and their excitement in engaging with doing research, software engineering, and good data science.
That's great. Moving toward talking about science for the public and even for the next generation. KG wants to know, how is the scientific community planning to safeguard science education for children, or how can the scientific community do that so that they can also appreciate the open source data and information shared?
Perfect. Excellent question. So the thing I love about working with kids as a scientist is they are so curious, and nothing matters more than curiosity in the sciences. And so how we try and make this data accessible to them is with things that sort of, that they can recognize. So for example, we did some outreach, not this project, but a different one that I'm involved in, to, I think the average median age in the room was about 5. These were kindergartners, grade 1ers. And the idea was to give them visualizations of things they can recognize, right? So they were learning about Antarctica, in one of their classes. So we presented, an appropriate Arctic stereographic projection so that they could recognize, Argo profiles distributed around Antarctica was something that they saw in the rest of their classes. So making things accessible and recognizable, even without a scientific background, is, I think it's a fundamental responsibility of the open data movement. That was kind of the point. I kind of had to rush through it. That was kind of the point that I was trying to make, was that data isn't truly open unless people, including kindergartners, have some hooks to be able to access it and understand it and engage with it. It's part of the job.
I think it's a really great ending point to really hone in what you want to say about open data, Katie. So everyone, please thank our speaker for such an engaging talk and interesting talk format too. I hope that you all enjoyed it. And thank you so much, Katie, for such a great and interesting talk. I really enjoyed looking at the websites.
It's my pleasure. Thank you for putting this together.
All right, everybody. How are we feeling? We're hitting hour 15 of the Weather and Climate live stream, so that means we have 85 more hours to go. I really love seeing all your positive comments. I read as many as I can. For those of you who are just joining, my name is Vanessa Sun. I'm a PhD student and atmospheric chemist, and I'll be your host for the next 2 more hours. For the next hour, we're going to have 2 more great weather and climate talks that I'm personally really looking forward to. Please remember that these speakers are not representing the views of any specific institutions or employers, but instead in their personal capacities. Before we begin, we want to remind you why you're here listening to the stream in the middle of the night. Or maybe in the morning. Weather and climate forecasts are important for you and to everyone in this country. Luckily, the United States has long been a world leader in weather and climate prediction. To make these forecasts work, we've created an unparalleled network of observations using everything from weather stations to satellites, planes, balloons, boats and floats, and the resulting forecasting and observation systems that we have are a true scientific miracle, and we're excited to share some of that miracle here with you. This miracle was made possible by decades of investment by you, the American public. But in recent weeks, funding cuts have put this miracle at risk. This has resulted in loss of observational coverage due to short staffing at weather stations, which is already hurting our forecasts. Laboratories dedicated to understanding our climate's future are being closed or shrunk, and funding for our basic understanding of the weather and climate is disappearing. Many meteorologists, atmospheric and climate scientists have lost their jobs, and programs that have trained generations of these scientists are being shut down. But it doesn't have to be this way. If you like what you see here through this live stream, then we urge you to use the link on the screen that's not appearing right now, but hopefully the director will get that up, to contact your representatives, to tell them to save our forecasts, to keep the lights on for weather and climate science so that we can keep this miracle alive. Either way, we hope that you learned something about weather and climate through our talks and that you've been enjoying them throughout this live stream. Please feel free to ask us any questions about our science in the chat while the talks are going on. Don't try not to leave them all to the end so that I have to go and filter out which ones to ask the speaker. If you can ask a little more throughout, it would be really helpful. And we'll have a few minutes at the end of each talk for the speaker to answer questions. So our first speaker for the hour is Victoria Boatwright, who is a PhD student at Scripps Institution of Oceanography. And she'll be teaching us about storms impacts to water quality in low inflow, intermittently closed estuaries.
Cool. Hi. Thanks for having me.
Great to have you, Victoria. Oh, you got your slides working. Great.
I did. It was a great success. Cool. Yeah, so just like Vanessa said, I'm Victoria. I don't know how long everybody has been watching the live stream, but a lot of people who are very longer experienced scientists have been talking before me, but I'm actually a second-year PhD student at Scripps Institution of Oceanography. And so I have not been doing this work for as long, but I really wanted to talk about it because I think it's really relevant in 2 ways. First, to do the work that we do, we depend a lot on weather and climate products, and I'll be talking about that later. But I also think that there's a lot of opportunity and a lot of direction going forward towards making climate and weather-like forecasts for the ocean and for coastal communities and beach communities. And so I just wanted to make sure that that would have some space here, even though it's not really about the atmosphere, which maybe everybody has seen so far a little bit of. But yeah, so excited to start talking about storm impacts to biogeochemistry in estuaries and on coastlines. And one thing that I was trying to do with all of my slides was talk a little bit about all of the funding sources who have been upkeeping the monitoring that's going on. And so at the bottom of each of my slides, I have the federal agencies that do the data monitoring and provide the ongoing products that we use for these results. And for me, one of them is me, I guess, because I'm currently supported by the National Science Foundation undergraduate research fellowship, and I wouldn't be here if it weren't for them paying me. So I realize that I actually don't have a lot of time in the practice talks that I've done, so I might not actually say every one of the agencies, but you will notice on the bottom of slides that there are a lot of different federal agencies that support the work that we do. So just to start off and give everybody a little bit of background, I look at estuaries. What are estuaries? They are considered the system between these river and terrestrial systems and the ocean. So they kind of mediate these terrestrial sources and how they enter the ocean and impact along coastlines. I put up a few examples here. They vary really greatly in how big and small they are and their dynamics. So we see the Chesapeake Bay on the left is the biggest one that I'm showing. The middle is the San Francisco Bay. And the right is the closest to where I am, which is where I'm in San Diego, as was the closest on the screen it's the Tijuana River estuary, but the smallest of the ones that I have right here. One thing to note is there are a lot of people who live on the coasts, and estuaries tend to be very anthropogenically impacted. They're very populated, and so there's a two-way system in which humans have a lot of impacts on the estuaries, and the estuaries have a lot of impacts on humans. So it's really important for us to understand. Where I am is Southern California. I'm in San Diego. A lot of the estuaries where we live are actually low inflow estuaries because we're in a Mediterranean climate, so it's quite dry and there's not a lot of rainfall, so there's only a small amount of river input. They will be intermittently closed, which Vanessa did a great job of pronouncing earlier. And that means that they will close sometimes with some cycle, often in the spring. And actually, the estuary that I'm going to be talking about is getting dredged open right now, or has been the last few days. And they close because the sill will build up. So sediments that come from the estuary and also that accumulate along the coast will build up from river discharge and wave action building up the sill, which will close the estuary at the end of this energetic wave time, which is around the spring in general. And like I said before about estuaries being vulnerable to anthropogenic impacts, these low inflow estuaries are especially vulnerable because they're in general smaller. And so when you build a bridge or some road system right next to the estuary, it tends to actually really impact the flow and the morphology because the estuary just isn't that big in comparison. But they do have a really big impact on our life. So it's really important to study still. And then I wanted to talk about just the estuary that I study, which is Los Penasquitos. It's just north of my institution, Scripps Institution of Oceanography. It's only a few kilometers large, so it's quite small, but you can see the entire watershed is a few tens of kilometers, and the star, which marks the pier, is where my institution is. And then you can see there's a lot of people who live right next to it. So in the top right of this figure, you can see Del Mar is right north of it, and there are a lot of people who live there. And so some of the data that I'm going to be using and showing to present my results are from the National Estuarian Research Reserve, and they maintain stations at different parts of the estuary. The Southwest one has actually been decommissioned in the 2017, but I still have some data that uses it, so I still wanted to show it. But they maintain water quality measurements, so including temperature, salinity, PO, dissolved oxygen, water level. And this stuff is important because temperature and salinity are conservative quantities that we look at to understand the properties of the water, what is the characteristics of that water parcel itself. And so we really want to understand what type of mixing is happening and what's happening. But also temperature, salinity are really important for the ecosystem that's living there. So some different invertebrates and benthic species can only handle some amount of temperature or salinity, and so understanding the impacts that those have, as well as dissolved oxygen and pH. And dissolved oxygen is really important for marine communities because they need to breathe often. Not all of them do. The photosynthesizers can just use sunlight, but the consumers, which make up a lot of the species in the ecosystem, depend on having enough oxygen to respire. So when it gets into hypoxic regions, it's really important to understand what is mediating the dissolved oxygen. And then pH is also how acidic or basic the water is, which has something to do with the amount of hydrogen ions in the water. But I'm using both dissolved oxygen and pH kind of as markers for biogeochemistry. So having some understanding of if you have a water parcel that comes from these further inland and more terrestrial sources, how does it kind of transform, not just in the physics, but also in the biogeochemistry as it kind of moves along the estuary? And what does that mean for what gets to the coast? Especially some people have thought of estuaries to be filterers and to mediate a lot of pollution and other contaminants that get to the ocean, which I'm actually going to talk more about right now. So what is this connection to climate and weather forecasts? Storms are really important, especially in our region where we have this low inflow. When we have this low inflow, we will have a storm event, which will actually bring all this river discharge and finally make it a river-dominated system. And these transport terrestrial materials, which will include things, like I said, of pollutants, but it will also include nutrients, sediment, larvae, so baby species in the ecosystem, and transport them often to the mouth and out into the ocean, and then impact the beaches and the coastline, but also impact the people who live right along the estuary, if it's coming from all those further inland regions. And so I just wanted to talk a little bit about this conditional existence of the estuary. Like I'm talking about, how much does it really become river dominated? Not really often. This top plot is showing in purple the river discharge, and then in this dark blue, it's showing the precipitation over 2 years. And you can really see there aren't a lot of events. The river discharge is also in a log, so it's most of the time very, very near zero. And you can see precipitation measurements are zero most of the time. For the last year, I also have a figure that shows the year of 2024, which to us was like a rainy year. And we really only have a few more than 4 events that surpass our the threshold for us as Southern Californians to consider something a rain event. Sorry, I'm from Rhode Island originally, so millimeters of rain is actually very small when you're coming from the East Coast, but it actually still makes a really big difference here because our infrastructure is just not made for it. And a question that I have really is how are these ecosystems prepared to deal with an average storm, and how long do these disturbances last, and can we even just identify the biogeochemical signature of an average storm? So next, I'll just talk a little bit about how I'm looking at the duration and the magnitude of storm impacts. So I am using storms from 2014 to 2024, all available because of the National Estuarian Research Reserve makes them available, and this is a project funded by NOAA, so really depend on them for these long-term monitoring studies. And then what we want to do is we aggregate all of these storms and try to find an average. So what do these storms look like in comparison to some baseline? Right now, how I'm showing it to you is just across all of these 60 storms, over 60 storms, what does the average signature look like in terms of the mean and then the standard deviation and the raw values. So on the left, I have the raw values, and on the right, I have the anomalies. And so you can see for salinity, we see drops in salinity after storms, which makes sense because we have all of this fresh water. So we're expecting to see a lot of fresh water. All these measurements are taken at the bottom of the estuary, but it varies how much it's impacted across these different locations. And you can also see, especially in this southeast orange plot, it's really the length of the duration is variable across storms. So, but on the average, we're seeing these impacts last about 5 days when we accumulate them all together. Oh, that's the wrong direction. Okay. Next, oh, I think I skipped something also. Okay, there, I totally did. Great. Next, I was looking at dissolved oxygen, and I wanted to see what were the impacts from dissolved oxygen. And in general, you see not really a big change from the mean or median, nothing that seems really significant from the standard deviation. And so then I looked at pH, and you see across all the locations and among all of these storms, you see pretty large drops in pH, especially because pH, even though is a logarithmic scale of how we measure it. So even like 0.1 drop in pH is lots of hydrogen ions. And so this would have a really big impact on the species there. So I was looking at all of that. Let me maybe give you a little bit of an intro. Anyway, I was looking at all of this and I was kind of like, okay, I can visually see that these things are lasting maybe 5 days, but can I actually characterize that across the different locations in the estuary? And so I tried to do it, and I did. So I was looking at in a subtidally filtered sense. So when I think of subtidal, I mean something that actually filters over just the tidal variations of water coming in and out of the estuary, but looks at the residual behind that. So a frequency that is over those like 12 hours and lasts up to a few days. And so if you don't see it in the residual circulation, then there's actually no change from the baseline state. And so what I did here is from those subtidally filtered quantities that I was looking at, how long would we see in the residual deviation from the baseline state, which I used just a mean and a annual cycle trend to remove. And we see actually long lasting, and I calculate this for each storm and then look at it in average. We actually see pretty long deviations, especially longer at the mouth. At the northwest station, and then also somewhat long at the southeast station in at least the physical traits. And then at the southeast station, we see actually not as long deviations for biogeochemistry, but at the closest to the mouth station, we see actually pretty long 4 days of change. And so I was kind of interested in like, okay, how are we still seeing dissolved oxygen deviations even when we thought we had seen nothing before? And so I started actually looking into different types of storms. And so I was looking at small storms, mid-sized storms, or large storms, just measured based on the cumulative amount of rains rainfall that was measured for each storm. This checks the salinity, makes sense to me. We see larger drops in salinity as we get to have bigger storms. But then in dissolved oxygen, we're actually seeing variations. So the smaller storms will drop in DO, but then the mid-sized storms will have pretty much not a big difference. And then the larger storms were actually having an increase in DO. And so I was trying to understand what could be driving that signature, which was in the averages getting kind of painted away. And so I've started to look at stratification, mediating these biogeochemical impacts. You can see two different storms on the top and the bottom, where the top storm, you actually don't really get the river. What we're seeing right now are current velocities. So we're measuring actually the speed of the water parcels and what direction they're going in. So this blue coloring is going out of the estuary and the red is coming into the estuary. And on the top storm, you see that this water flow that's going out of the estuary doesn't even get to the bottom. Whereas the bottom storm, the outflow is across the entire water column. And you see this even more strongly in the residual flow that I was talking about earlier. And now I'm trying to actually relate this to the biogeochemical impacts. So that's ongoing work right now. But the reason that this is important and why we want to do this is because if we can understand some of the physical drivers like advection and stratification that are playing roles, we can understand and predict maybe the impacts that storms will have to coastal communities and estuarian ecosystems. So these are some things that we're thinking about. My group also does a lot of other work that I wanted to showcase really briefly of how we can apply this stuff. So we have a pretty good understanding of the physics of the estuarian system, and we're trying to apply this via the work that I'm doing into biogeochemistry and understanding of pollution and contaminants. How do we make this model is a really huge feat, and I think we've been talking about climate models a lot today, but we actually have 4 nested domains so that we can actually resolve the physics at this very fine scale of a few kilometers. Well, a few tens of kilometers, sorry. And so we have a larger grid, and we have to actually force that larger grid with a lot of variables. So we have atmospheric forcing, which we use NOAA's models, NOAA's climate models to force. We use sea surface height measurements that are from NASA satellites in the air. We have river inputs, which are measured by how much river discharge is going into the ocean, into the estuary, and that's from the EPA and USGS. And then we also have wave forcing, which is funded by and maintained by the US Army Corps of Engineers. And so we have to have all of these components to just force the ocean correctly. And then we put it together and we have this grid of the San Diego coast. And one thing that our group is using these models for is looking at pollution. So especially in the region where we are, we have the coast is under contamination stress often. There are point sources that will input wastewater and sometimes raw sewage because of infrastructure challenges with the growth of Tijuana. And this is impacting the estuary flows. And we want to understand what's happening to this pollution. So we've been using these models to both identify data-based results of what are the best infrastructure scenarios, which was produced in 2022. And then we have an ongoing project trying to forecast coastal hazards of pathogens and pollutants. And so I'm just going to show, this is an image of our model domain that is further, just a little further south and closer to Tijuana, where we have 2 point sources of pollution and contaminants sometimes, which we would like to inform people what that looks like and when it gets to the coast. And I'm just going to run, I think that this should work, possibly. I'm streaming YouTube to YouTube. That's crazy, Inception. So what we're showing right now is starting in January 2017, we ran our numerical models to see when a passive tracer of something that could be like a particle, a nutrient, a pollutant was going from the estuary into the ocean. And so you can see the leftmost plot is just salinity, but the rightmost plot is that passive tracer. So just kind of a marker of a water parcel. And you can see during some of these like plume events that I've been talking about, these storm events and anything that is putting discharge into the ocean, you can see it interacting along the coast and either flowing south or north due to different wave dynamics and different coastal currents. So this is a product that we're also developing to better understand pathogens on the coast. And I would also like to implement some of the biogeochemistry into models like this to better understand how the water is getting transformed as it goes through the estuary. But this is just some of the work my group does. And I just want to thank everybody for your attention. There are a lot of people who do this work in our group and a lot of people who have helped me along the way. And I'd also just like to thank my funding providers of the past, which is the National Science Foundation. They actually just this past year, a month ago or so, they only gave out half the number of scholarships that they have in the past. And so just way fewer people have the opportunity to do work like I'm doing. And then also I was funded on a NOAA hauling scholarship during my undergrad, which really also helped me get here and be exposed to oceanography and climate science. And if I hadn't had the funding to do that either, I would probably not be here either. So just want to give a head nod to both the staffing ability of these federal organizations and agencies, and also all of the data that they provide to us that allows us to do this work. So yeah, I don't know if I was at the right time. I actually forgot to start.
You're all good. We have a couple minutes for questions. A lot of people were asking about climate change and salinity. So I'll try to attempt to mix them together. Sydney Lindquist wants to know, does climate change affect the salinity of estuaries? And Kelly, similarly, wanted to know about salinity drop as climate change causes more glacier melting. So kind of similar.
Yeah, totally. So it's a really good question. I think that salinity, it really depends on different estuaries because you have different amounts of like ocean impact and different amounts of like freshwater influence. So like a really large estuary will have a lot of freshwater and maybe the salinity won't change. But something that's happening, I haven't actually looked at this for our estuary, but something that's happening is oceans have been, their sea level rise, and so oceans have been encroaching on estuary regions. And so you'll find that, you know, a place that will normally be low salinity, mostly fresh, will become more often get intrusions from salty water. And then you'll also see, like, when the estuaries close, it's often because of evaporation that they get really salty at the surface too. And just the more often that there are closures and there's warm temperatures, the evaporation that's happening in estuaries is also playing a key role in making them saltier, potentially making them saltier. But I don't have any citations for that stuff. That's just how I've understood it.
Great. Annie Pinecone wants to know, is your group's data being currently used to publicly track estuary and coast hazards?
That's such an awesome question. So the video that I just showed was from a 2017 numerical model run, but we actually have in beta a forecast that looks at from 3 to 5 days ahead of time to warn coastal communities about, you know, what is the likelihood that there will be contaminants at the beaches that you frequent. And that is like in beta, and where our group is actually hoping to release it in the next few months. So, but it's something that we're working with communities about. So we're trying to make sure that it's the most useful for people. But that's a great question. And we're working on getting it there. So it will be open to the public once we disseminate it, once we finalize it, I guess. Yeah.
That's really exciting. It's important to get that data out there. Okay, thank you so much. If everyone can please give a round of applause and thank our great speaker. That'd be great.
Thank you, guys.
Okay, thank you. So we're halfway through hour 15 of the Weather and Climate live stream, which means that we have 84 and a half more hours to go. And for those of you who have just joined, my name is Vanessa Sun. I'm a PhD student and atmospheric chemist, and I'll be your host for the next hour and a half. For the next half hour, we have another great atmospheric science talk that we're going to have coming up. Please remember that these speakers are not representing the views of any specific institutions or employers, but instead in their own personal capacities. Before we begin, we want to remind you why you're here listening to the stream in the middle of the night or in the morning, very early morning. Weather and climate forecasts are important for you and to everyone in this country. Luckily, the United States has long been a world leader in weather and climate prediction. We developed the first computerized weather forecast to help you know what you can expect in the coming weeks. And we made the first computer models of the climate impacts of carbon pollution so you can know what to expect in the decades to come. To make these forecasts work, we've created an unparalleled network of observations using everything from weather stations to satellites, planes, balloons, boats, and floats. The resulting forecasting and observation system is a true scientific miracle, and we're excited to share some of that miracle here with you throughout the live stream. This miracle was made possible by decades of investment by you, the American public, but in recent weeks, funding cuts have put this miracle at risk. This has resulted in loss of observational coverage due to short staffing at weather stations, which is already hurting our forecasts. Laboratories dedicated to understanding our climate's future are being closed or shrunk, and funding for our basic understanding of the weather and climate is disappearing. Many meteorologists, atmospheric, and climate scientists have lost their jobs, and programs that have trained generations of these scientists are being shut down. It doesn't have to be this way. If you like what you see here, then we urge you to use the link on your screen to contact your representatives and tell them to save our forecasts, to keep the lights on for weather and climate science so we can keep this miracle alive. Either way, we hope you learned something about weather and climate through our talks. Please feel free to ask us any questions about our science in the chat. I've been seeing the questions have been slowing down throughout, so if you all can pick it up a bit throughout the next talk, that'd be great. And we'll have a few minutes for questions at the end of the talk. Our next speaker is Joel Thornton, an atmospheric scientist, and he will be discussing enhanced lightning frequency over maritime shipping lanes and its connection to aerosol and cloud microphysics. Take it away, Joel.
Okay, thanks very much. Thanks to the organizers for putting this together. It's really a tremendous effort. And for all of you who are either on the West Coast staying up late or on the East Coast getting up early, if you are listening to this, I appreciate that as well. I just need to figure out how to advance my slides. So I'm going to talk to you about a project that's been funded by the National Science Foundation in the Atmospheric and Geospatial Science Division, where we are studying how lightning is enhanced over major oceanic shipping lanes. And I want to give really a shout out to the student, Chris Wright, who's been leading the most recent version of this project. He's a graduate student. And Christine Neumeier, who was sort of seminal in putting the initial stage of this project together while she was an undergraduate student. She's now a graduate student at Colorado State University. And then Katrina Wirtz was a graduate student, and I was on her PhD committee almost 10 years ago. And she was the one who really got me into this project or this topic to begin with. A little bit about me, very quickly. I'm a professor of atmospheric and climate science for about 20 years. I study atmospheric chemistry, the composition of the atmosphere, how it is affected by or affects climate and air pollution. So I do a range of things in that regard related to instrumentation development, observations, and modeling. And I'm basically a product of federal science funding. So my research is largely funded by NSF, DOE, NOAA, and NASA, and a little bit of private funding and a little bit of state funding, but it's mostly federal funding by and large. And before I became an atmospheric and climate scientist, I got my PhD in chemistry, and it was a NASA graduate fellowship for Earth Systems Science Fellows, I think it was called, that really enabled me to pursue the chemistry of the atmosphere as my PhD. And before that, I really didn't even understand that was the thing you could study. And so I'm really grateful to that opportunity. And I also was able to work on some NSF and NOAA funded projects as a graduate student that formed the basis of my PhD. Okay, so in the remaining time, I'm going to talk to you about lightning and utilizing this really cool data set that is called the Worldwide Lightning Location Network. And what you're seeing here is an animation of about 10 years of lightning stroke density, which is the number of lightning strokes. We call them strokes if they're in the atmosphere or hitting the ground. When they hit the ground, we call them lightning strikes. Sometimes if you're looking at them from above and you see the flash, you can call it a lightning flash. I'll be using the terminology lightning stroke density, or just lightning is also fine. And what you saw in that animation, this is a global animation. This network is able to detect perturbations in essentially the electromagnetic radiation propagating through the atmosphere that is caused by individual lightning flashes or strokes. They are a very powerful phenomenon, and they cause a disruption that can be detected in radio waves. And with really just a small set of sensors distributed around the globe, lightning can be counted and located to within 5 kilometers every second around the world. And you can see there's pretty much global coverage of the lightning field. And you'll notice that where it's red, there's a lot of lightning, whereas it's white, there's not a lot of lightning being detected. And there's a lot of lightning in areas where we typically have lots of storms. So in the tropics and in the summertime in the hemispheres where it is summertime, where there's more sunlight. And so where there's storminess, there tends to be lightning. And the reason why we like to study lightning, or we should study lightning, is, as I mentioned, it's one of the most powerful natural phenomena to occur. A lightning stroke or lightning bolt heats the air to about 30,000 degrees Celsius. And that energy is basically 1 billion joules in a very short amount of time, causes significant damage to property, lives, and ecosystems. So I think about $1 billion per year in the U.S. In property damage is caused by lightning. And then, of course, lightning is a major source of wildfires. It also causes severe injury and even death. And so for these reasons, we'd like to know and be able to predict when it's going to occur or how it might change. Oops, so I want to go back. And as I was saying, lightning is one of the best indicators of severe weather and storm intensification, and its observation can therefore help improve timely weather forecasts and warnings of severe weather. And lightning plays a surprisingly important role in the composition of the atmosphere and therefore the climate system, being the most important natural source of nitrogen oxide radicals throughout the upper part of the atmosphere. And in that way, lightning actually regulates the oxidizing capacity of the atmosphere, the ability of the atmosphere to cleanse itself and to remove trace gases and or form trace gases that are greenhouse gases like methane and ozone, and pollutants like carbon monoxide or sulfur dioxide and so on. And in fact, one significant uncertainty in our understanding of the greenhouse gas methane and how it's changed over time is how lightning has changed over time since pre-industrial era to present day or going into the future, because of the way it might change the lifetime of methane and the cleansing power of the atmosphere. So there are a lot of reasons why we want to understand and predict lightning. And so I'm going to just give you one little snippet of this story. And there's lots of factors that control lightning. Obviously, there needs to be a storm, and the storms are controlled by both thermodynamic and dynamical factors occurring in the atmosphere. But then also the lightning forms inside of clouds, and those clouds have cloud droplets, and those cloud droplets depend on microscopic particles known as aerosols. So it goes down to the tiniest elements of the atmosphere to create some of the most powerful phenomena in the atmosphere. And if we're going to zoom in now on one part of that global picture I was just showing you, this is the location near Singapore, Malaysia, what we call the maritime continent here. And this is the southern tip of India here in the Indian Ocean on this side. And here's the port of Singapore right on the tip of this peninsula. And we're looking again at lightning stroke density, so the amount of lightning per kilometer squared shown as the color map. And it's on a log scale, so that means the red colors are 10 times more lightning than the orange colors. And what you'll notice is that over the ocean, there tends to be lower lightning in general compared to, say, over the land masses of these islands here. But then there are these strips of intense lightning occurring, coming out at these weird angles, say from Singapore in this sort of straight line going this way up to the South China Sea, and then from the tip of Sumatra here out straight across the Indian Ocean towards Sri Lanka. And this was an image that Katrina Wirtz, that PhD student I mentioned, brought to me right when she was winding up her PhD. We had been studying how lightning patterns were changing associated with a natural occurring pattern in the weather known as the Madden-Julian oscillation, and how that was regulating nitrogen oxides in the atmosphere on a sort of weekly to monthly timescale in this region. And she regridded the lightning data at higher resolution, and these lines of lightning originating out of Singapore sort of appeared. And she was leaving and said, "You should think about this," and I agreed. And because lightning is sort of a not quite a random process, but it's certainly not organizing in straight lines usually when we look at it on a global basis. And what struck me about this was that it's overlaying two of the world's busiest maritime shipping corridors or shipping lanes. And what I'm showing you here is an image taken from data probably 10 years ago now of each little dot on this screen is an individual cargo ship or container vessel that is traversing the ocean. And these two lanes that go into and out of Singapore are basically the two busiest shipping lanes in the world. And that is right where that enhanced lightning that we were looking at is located. And you can see this more clearly when we indicate the shipping lanes by their emissions of particulate matter. And I'll come back to that later, but this is just sort of giving you an idea of where these ships tend to travel. And what we're showing you here is a map of the particulate pollution that these ships emit as they're traversing the ocean from Singapore to Sri Lanka or up to China through the South China Sea. And this sort of overlaying of the lightning with the shipping lanes was really intriguing, because why would there be enhanced lightning out over the ocean over these shipping lanes? And so that question really was what started our foray into this field, to try to make a connection between ships moving across the ocean and storminess. And in particular, the metric of storminess here would be lightning. And to answer that question, it helps to understand a little bit about what causes lightning. So lightning is an electrical breakdown in air due to spatially separated positively and negatively charged hydrometeors, or parts of the cloud, of the storm cloud. And storm electrification, that is the creation of these charged hydrometeors and their separation in space, requires a number of factors to be present in the storm cloud. So that requires the storm cloud to be propagating high enough in the atmosphere where it's cold enough to form ice. And it needs to be also ice forming in the presence of liquid water. So liquid water that's propagated up from a warmer part of the atmosphere to a colder part but hasn't frozen yet. And then also strong updrafts, so strong upward motions of the air inside the storm cloud. in order to move those charged particles from one another. And so this is a cartoon animation by Noah showing you the charging process and then also the separation. So in the storm cloud, if it gets high enough to be in the freezing region, we get what we call the mixed phase region, because we have ice crystals that have formed and we have liquid water. So we have solid ice and liquid water. That's why we call it a mixed phase region. So the different phases of water are present. And it's the collision between the ice crystals and what we call grapple, which is essentially ice crystals that have had water, liquid water, hit them and freeze in sort of what we call rime and grow into almost little hailstones. And these hailstones are heavier than the snowflakes, the light crystals. So they're falling while the snowflakes are rising with the updrafts. And when those collide, it turns out that the positive, the snowflakes tend to accumulate positive charge, and the heavier hail-like particles or grapple tend to accumulate negative charges. And so as the updrafts are bringing the snowflakes upward, the grapple's falling downward, and you get a separation of charged hydrometeors, more positive aloft and more negative below. And then that separation of charge creates an electric field, and then the atmosphere needs to relax that disequilibrium, and so then we get a discharge, just like a Van de Graaff generator when you touch your finger to it in the physics class and get a static electric shock. It's all a little bit more complicated than what I'm explaining here, but this is a nice way to be able to think about it going forward. So lightning then is a response to the energy of the storm, the dynamics, the motions of the storm, but also the microphysics, what's going on to the ice crystals, the grapple, the liquid water droplets that are really, collections of hundreds or even thousands of these droplets in a cubic meter of the cloud. And so we need to be able to connect all of these different parts of the lightning formation process to understand why there would be enhanced lightning over the shipping lanes. And a key to that is that cloud droplets and or ice crystals in clouds do not form in Earth's atmosphere without a pre-existing particle. So water vapor cannot sort of self-organize itself from the gas phase into a condensed phase liquid or liquid droplet or ice crystal. The energetics of that just are not allowed. And so what is required is the place that the water vapor molecules can organize themselves, and we call those condensation sites or cloud seeds or cloud condensation nuclei, so where the cloud droplets are born. And these are essentially pre-existing particles that are in the atmosphere that tend to be on the scale of 100 nanometers to 1 micron in size, and I'll give you a little example of what that looks like in a minute. But what they do is they allow the water molecules to organize themselves, condense, and form a liquid layer that then is allowed to take up more water and grow into an actual cloud droplet. And so these cloud condensation nuclei are known as aerosol particles. These are just pre-existing solids or liquids floating around in the atmosphere, and there's many different sources and many different processes that occur in the atmosphere to transform these into different shapes and sizes. So some that you're probably directly familiar with would be wind-blown soil dust, either from a dirt road and a truck driving by, or large-scale winds over desert areas can loft lots of essentially soil sand into the atmosphere. Wave breaking on the oceans and wind can loft little bits of the ocean into the atmosphere. Wildfire creates smoke. Volcanoes emit ash, but they also emit lots of sulfur gases, and then those sulfur gases react in the atmosphere to convert into sulfates, and these then form particles if there aren't already ones existing to condense on. And then, of course, fuel combustion, so diesel trucks produce soot, and of course, large maritime vessels, ships also are burning diesel. Some of the dirtiest fuel in the that exists are often burned by large container ships and cargo vessels. And there are also emissions from vegetation in form of pollen, for example, but also volatile organic compounds, or VOCs, are emitted into the atmosphere, and these can also turn into particulate matter. And as I mentioned, most of the particles in any sort of bit of the atmosphere tend to be quite small. So this is showing you how many particles there are as a function of their size. So many tend to be 100 nanometers or 0.1 microns in size or even smaller. And just to give you a sense of that, the human hair is about 50,000 times larger than a 100 nanometer size particle. And so we're talking about hundreds to thousands of these sort of order tens to 100 nanometer size particles in any little tiny volume of air. They vary in space based on where there's lots of emissions of them or lots of formation and where there's removal of them. So they're very heterogeneous throughout the atmosphere. They're not uniformly distributed. And of course, you can see that from those images that I showed you based on what types of processes are giving rise to them in any location or time. Okay, but ship exhaust can certainly be a major source of particles, as well as the gases that become particles like sulfur dioxide. And so it's not too big of a leap to suggest that particles that are originating from the ships are acting as cloud condensation nuclei and changing the properties of the storm clouds. And you can think about it this way, where when a storm cloud forms, there's some amount of water in the atmosphere at that location that can condense into cloud droplets. If we give them fewer locations, if we give those water molecules fewer locations to condense on, then we're going to get fewer cloud droplets that are overall bigger than if we had the same amount of water available condensing on more numerous cloud condensation nuclei. They will have more numerous cloud droplets, but they have to be smaller because they were working from the same sort of available amount of water. So in this situation where we're more polluted, we say we have more particles from ships, we're going to end up with cloud droplets that are more numerous but smaller. And those more numerous but smaller droplets will not be able to coalesce and form rain droplets in time as the storm is propagating upwards before that water reaches the freezing level of the atmosphere. So we'll have more liquid water propagating upward into the mixed phase region of the clouds. So that was our leading hypothesis back in 2017 when we first published this enhanced lightning over the shipping lanes. More aerosol particles because of the ship pollution leads to smaller, more numerous cloud droplets. Smaller cloud droplets means there's less warm phase rain. Less warm phase rain means more mixed phase condensate. So there's more supercooled water into the freezing region and making more ice crystals and more graupel. And if we have more mixed phase hydrometeors, we can get more charging. And more charging means more lighting. So that was our hypothesis. We obviously don't prove that by just showing that there's enhanced lightning. But that was what we proposed as our leading hypothesis in that paper. Okay, so I think I'll skip this in the interest of time, but this is just showing you how if you have more of these particles in the same volume, they're going to run into each other more often, and that would lead to more charge transfer and more charge separation. So we really want to test this hypothesis more completely, and it turns out there was an unintended natural experiment, and this sort of shows you that science sort of, how should I say this, a rich or a broadly funded science enterprise leads to serendipity, and serendipity allows us to learn things we never knew we should have thought about. And I think that's really important for making advances in our understanding of how the world works. But we have this unintended experiment going on where in 2020, the International Maritime Organization, IMO, which regulates the shipping industry, required shipping companies to comply with a low sulfur fuel oil requirement so that they had to reduce the amount of sulfur that was emitted as they were traveling over the open ocean in international waters by almost a factor of 7. So the global limit went from 3.5% sulfur equivalent in the fuels to 0.5% sulfur equivalent in the fuels. And this is similar to what is required as ships come into coastal urban areas for regulating air pollution. But this applied all over the globe. And it's been a major source of hypothesis testing now on how ships have perturbed clouds globally, but not storm clouds as we were interested in. And so we recently published a paper where we took advantage of this experiment that was not our design. It just happened to be going on soon after we published this paper about enhanced lightning. And so this was published just a couple of months ago in Atmospheric Chemistry and Physics Letters by Chris Wright, a graduate student I was talking about. And one of the images here from that paper shows you, again, where the ships are. So these are ship transponder calls. It tells you how many ships are in a particular location at any given time. And you can see them coming in and out of Singapore. And this is the amount of lightning average from 2010 to 2023. Again, you can see enhanced lightning going into Singapore and coming out towards the South China Sea from the Indian Ocean and back. Of course, ships are going both directions. And then if we look at just after 2020, so from 2020 through 2023, and we subtract the amount of lightning that was there on average post 2020, and we from the pre-2020 amount of lightning, we can see that there's been significant declines in the amount of lightning since 2020. There's a negative difference there. And we can look at this a different way. Well, if we just organize the amount of lightning as distance away, either north or south of the shipping lanes, and plot that amount of lightning versus time, you can see that there's a lot of lightning over the shipping lanes. Within 100 kilometers or so of the shipping lanes, there's excess lightning compared to the surrounding region. But after 2020, that excess seems to disappear. And that's timed exactly with when fuel sales in Singapore switched from high sulfur, which is the red line, to low sulfur fuel. So the sort of correspondence of the cleanup of the fuel in the ships and the decrease in the amount of lightning are sort of timed almost perfectly. And one final test we could do is to take advantage of the suite of satellite sensors that we have in the atmosphere measuring weather and climate properties, again, funded in large part by US funding agencies. We can actually count how many cloud droplets there are on average in the cloud droplets and actually measure the average radius of cloud droplets from space on satellite sensors. And so what we're showing you here is before this regulation by the International Maritime Organization, you could see a region of enhanced cloud drop number just to the north of the shipping lane during the summer season. And that's because the wind is actually moving from south to north. It blows the pollution on average to the north. But if we look after the IMO, that is after 2020, that enhanced amount of cloud droplet number is basically gone. And we can look at it a different way as a function of latitude. For the Indian Ocean, we see that before 2020, there was always enhanced cloud droplets after 6 degrees north, which is where the shipping lane is. And then after 2020, from 2020 to 2023, that enhancement in cloud droplet number has basically gone away. So if lightning was caused by enhanced aerosol particles acting as cloud condensation nuclei, then our hypothesis would be because the shipping regulations reduce the amount of aerosol particles, and we know that through independent measurements, then the amount of cloud droplet number should have decreased, which it also did. And so this is sort of a corresponding test of our hypothesis that the shipping emissions are the cause of the enhanced lightning. So that's basically my story there. The aerosol particle pollution from maritime shipping traffic has likely changed the amount of lightning that occurs over the tropical oceans. And this finding helps identify how these tiny 100 nanometer so size particles can influence weather, not just human health and climate. And of course, this could be happening other places. It just requires perturbations to aerosol particles relative to what has been there in the past. And there's much still to discover, therefore, about how aerosol particles change in time and space and how that changes weather, atmospheric composition, and climate. And I'll stop there and happy to take any questions.
Thank you so much, Joel. If everyone can thank our speaker. We have time for maybe 1 or 2 questions. Claire S. wanted to know if the COVID pandemic pandemic factored into the results of CCNs and lightning occurrences in 2020. I think that was like on the last slide or 2 that you had, since global shipping was heavily regulated that year.
Yeah, that's a great question. So we look at the broadly, there is another paper by a different group that has shown right in the height of the pandemic in 2020, it seems like lightning globally decreased actually. So that's an interesting sort of corollary. It turns out in this region, in these busy shipping lanes, shipping was disrupted, trade was disrupted, but actually only for a pretty short amount of time. Most of that disruption was in the first few months of the pandemic, and then shipping sort of recovered. And it was actually only about a 6% decrease over sort of typical values. So it ended up not having a big impact on our sort of 3 or 4 year average after the 2020 IMO regulation. But yeah, so the COVID pandemic was another one of these unintended or natural experiments to see how emissions of pollution might affect various aspects of atmospheric chemistry and weather and climate.
Great. Thanks so much for the question, Clary. I think this is the first one I've seen that you've asked, so it's great. I think we have time for one more. Sage wanted to know what inspired you to go into research specifically on the impact on lightning and stormy weather. I always love learning what inspired others to follow their path. And I think you mentioned in the beginning that one of your collaborators got you into the project, but I know that you do a lot of work beyond lightning, Joel. So if you wanted to mention your general research interests, that might interest the audience too.
Yeah, so I could go on forever though. So I know we're short on time. Yeah. This particular project, again, was a bit serendipitous, but I was on the PhD committee of a graduate student who was studying lightning patterns and how they relate to the impact on nitrogen oxide, so atmospheric composition. And that's one of my areas that I've studied for a long time is nitrogen oxide chemistry in the atmosphere and how it regulates the cleansing power of the atmosphere. So lightning's always been an element of my research in that regard because it's an important natural source of nitrogen oxide. But really, the student, and this is usually how it happens, professors have ideas, but students are the ones who really are the ones that I think generate a lot of the new ideas and new ways of thinking, because they bring us like, oh, here's this data set I was looking at, and it's kind of got this interesting feature in it. And that's, the curiosity just takes over after that. And so in this particular case, it was a conversation with a graduate student literally as she was leaving for her postdoc. So yeah, that's how it happened.
Great. That's a really great ending point as well. Thank you so much for telling us about lightning and shipping lanes.
Yeah.
Thanks so much, Joel.
All right, take care.
Thank you. All right, so we're up to hour 16 of our weather and climate live stream. I hope that you've all been enjoying that. There's about 84 more hours to go, but not for me. This is going to be my last hour hosting. Yay. We've been powering through the last couple of hours. Thank you for the people who have stayed quite a bit for the past couple of talks. And I hope that you've been really enjoying them so far. For those of you who have just joined, my name is Vanessa Sun. I'm a PhD student and atmospheric chemist. As I mentioned before, it's going to be my last hour hosting. So for the next hour, we're going to have 2 graduate students. And I'm really excited to introduce you to them because I met them at a National Science Foundation funded conference, the Graduate Climate Conference, last year. So I'm really looking forward to their talks, and I hope that you are too. Please remember that these speakers are not representing the views of any specific institutions or employers, but instead in their own personal capacities. And before Lily here begins her talk, we want to remind you why we're here, listening to this live stream in the middle of the night or in the early morning. Weather and climate forecasts are important for you and to everyone in this country. Luckily, the United States has long been a world leader in weather and climate prediction. We developed the first computerized weather forecast to help you know what you can expect in the coming weeks. And we made the first computer models of the climate impacts of carbon pollution so you can know what to expect in the decades to come. To make these forecasts work, we've created an unparalleled network of observations using everything from weather stations to satellites, planes, balloons, boats, and floats. The resulting forecasting and observation system is a true scientific miracle, and we're excited to share some of that miracle here with you through this live stream. This miracle was made possible by decades of investment by you, the American public. But in recent weeks, funding cuts have put this miracle at risk. This has resulted in loss of observational coverage due to short staffing at weather stations, which is already hurting our forecasts. Laboratories dedicated to understanding our climate's future are being closed or shrunk, and funding for our basic understanding of the weather and climate is disappearing. Many meteorologists, atmospheric and climate scientists have lost their jobs, and programs that have trained generations of these scientists are being shut down. It doesn't have to be this way. If you like what you see here through this live stream, then we urge you to use the link on your screen to contact your representatives and tell them to save our forecasts, to keep the lights on for weather and climate science so we can keep this miracle alive. Either way, we hope that you learned something about weather and climate through our talks. Please feel free to ask us any questions about science in the chat, and we'll have a few minutes for questions at the end of each talk. Now we can get to our next talk by Lily Zhang, who is an atmospheric and climate science graduate student. She'll be sharing with us what drives year-to-year variations in Western U.S. summertime temperature.
Okay, thanks so much, Vanessa. And that was a perfect introduction because, as you can see, the work I'm about to present is also funded by the National Science Foundation. So Vanessa and I and our next speaker, we all met at this really cool National Science Foundation funded climate conference for graduate students. And there I talked about this project, which is understanding year-to-year variations in Western U.S. summertime temperature. If anyone else is joining from the West Coast, it's pretty late, so I'm going to be keeping it casual, and hopefully we'll get to answer some questions at the end. Okay, so to start out, I'm actually not going to talk about the Western US first, but introduce myself a little bit as a scientist. And so I like to say that I'm an atmospheric scientist who studies weather and climate over land. And so the reason I'm specifying that is because when we're thinking about Earth's climate, we really want to think about it like a coupled system. And what that means is like there's all these different components of the Earth system, and most of the times, like us atmospheric scientists, we're up here, you know, in the atmosphere, there's like the sun, energy coming into the atmosphere, there's clouds, there's rain, there's the aerosols that Joel was just talking about. So that's where atmospheric scientists are. But then when you are like talking about climate, you have to consider all these other components of the Earth system. Like we have the ice, the oceans, we have land where there's like vegetation, also humans, volcanoes, like all these sorts of different things together interact with one another to make up our coupled system. And so I am like here where the land surface is, but historically, the oceans have taken sort of like a main stage in climate science. And I'm going to give the ocean its kudos and like explain why, and then talk about why I chose to focus on the land surface instead. So the ocean, you know, it does matter for climate, like a lot. And why is that? Well, so if I just simplify this graphic from before, and I think about it like maybe a traditional climate scientist would, which is just like an aqua planet with only ocean. It has a lot going for it, you know, it's most of Earth's surface, the ocean covers over 70% of Earth's surface. Great. It also contains most of Earth's water, and you know we know that water is very important to climate and life and basically everything on Earth. And I'm just going to walk through that a little bit. So water, very important molecule, H2O. One thing that water does is that it absorbs and stores a lot of heat. So you know the sun shines down into the ocean uptakes a lot of that heat, and also it's really hard to change the temperature of water, so the ocean retains that heat for a long period of time. What else happens when we think about the ocean surface? Well, when there's evaporation, that returns water and then the associated energy back into the atmosphere. So water is super important. The ocean has a lot of water. That's why we care about the ocean. Now, what does the land surface have going for it? Well, it's where humans live. So, I don't know the exact number, but I would guess like 99% of humans live on land. The 70% of Earth is oceans, but land is where humans live. And it's also where we like build all these different structures, like our homes, our cities, etc. Now, what I'm really excited about is soil moisture. So, little known fact, soil is wet, it can hold water. So, we just said before that the ocean is really important to climate and thinking about interactions with the atmosphere because it's this like big bucket of water. But also land has some moisture in it too. Like you just think about it, like dirt can be wet, it can hold moisture. And so what does that mean? Well, that means that just like our ocean, just to a lesser degree, the soil can hold some heat. And also when there's evaporation, that evaporation is also like returning energy and water to the atmosphere. So the way I like to describe this is like the soil moisture, and when it evaporates, it's kind of like sweating. It's like sweating off of the Earth's surface. And just like with how humans sweat, that evaporation and release of heat has like a cooling effect. So this is actually like very important for understanding climate on the land surface. All right, so if we're like kind of stacking these two components of the Earth system up against each other, like we have the oceans, they're most of Earth's surface, big bucket of water. But land is, also holds water. But I really want to highlight this point here, which is that, land is where humans live. And so if we're able to understand how the land surface influences the atmosphere above it and like is influenced by weather and climate, that has really important implications for understanding how we as humans both influence and are influenced by weather and climate, particularly when we think about how, over the history of like mankind, like we live in these places that have favorable climate conditions. But then when we build our civilizations and build our cities, we modify the land surface. And in doing so, we also modify the weather and climate that we're experiencing. And so now I'm going to go back to the Western US and talk about my research, which is understanding year-to-year variations in summertime temperatures. So this project kind of like, started off when we're thinking about what do people really care about in the Western US? And so having lived here for a few summers now, I noticed that people typically talk a lot about these three things: drought, fire, and extreme heat. And what all three of these very consequential environmental hazards have in common is that they're all like very strongly influenced by year-to-year variations in summertime temperature. And this probably like isn't too surprising. So what I mean by year-to-year variations is just that if you have a hotter than average year, you're probably also going to have more extreme heat that year, more drought, more fire. And if you had a colder than average summer, you would probably, think that that summer had less extreme heat, less fire, less drought. And I want to stop here and like point out that we've had a lot of really great talks about like climate change so far. Super important and a big part of climate science, but this is also climate science, right? Just thinking about like on average, is this summer like warmer than the climatological mean? So thinking about these year-to-year variations in climate is also an example of climate science. And so if we try to characterize these year-to-year variations in summertime temperature, so whether it's hot or cold, a first attempt at doing that, we might just say like, okay, let's just like average June, July, August temperature over this region, and that gives us like a number for every year. So every year, what was the average June, July, August temperature over the Western US? That gives us a number that's kind of like an index. And so what we found in our research is that if you take that average and you do some statistics on it, you find that that pretty much describes temperatures from year to year in this like red region. it's like red everywhere, right? So don't worry too much about the specifics. If there are any math people in chat, like math people call this principal component analysis. We call it EOF analysis in climate science. Not super important. Basically, what this is telling us is that there's this pattern where from year to year, temperatures in this region, like in this red region, so everywhere, tend to vary together. So when it's a really hot summer here, we also expect it to be a hotter than average summer elsewhere in this pattern. And this pattern we find is like super important. If we do the statistics, it's explaining over like 50% of like the variations in summertime temperature. But then there was like a little bit of a plot twist. So, and this is where we get into the ocean versus land debate. Typically, when our forecast offices make these seasonal outlooks for things like temperature and precipitation, they rely a lot on these like ENSO, so El Nino Southern Oscillation indices. The reason for that is, as I just said, sea surface temperatures, they kind of have like this memory characteristic. And what I mean by that is that like water is retaining heat, so then it's retaining some information and it stays that way for a long time. You might have heard some talks about El Nino earlier. I won't go too much into it, but it was very shocking that our summertime temperature pattern had no relationship to sea surface temperatures at all. Like that, for a climate scientist, that is like really crazy and really out there. And what's even more crazy is that it did have this negative correlation with antecedent hydrological conditions, and that's really the focus of my research. So what I mean by that is if we try to look at the seasonal weather that's associated with our summertime temperature pattern, so like this is a summertime temperature pattern. What it means is that in summer, when it's hot here, it also tends to be dry. And that makes a lot of sense if we think about what I said before about like the soil moisture being like sweating and evaporation being cooling. So when it's hot, it tends to be dry. That's not really a hot take, I think, no pun intended. But what we also see is that, so this is the soil moisture anomaly of that same year. And this is the precipitation anomaly of that same year in winter and spring. So for some reason, there are these like moisture deficits in the Southwest US leading up to a hot and dry summer. And the big question always with science is like, why? So yeah, why is it that when we have a hot and dry summer in the Western US, so it's hot and dry everywhere, there's probably going to be more heat waves, there's going to be more drought, there's going to be more fire. Right before it, you know, it's dry down here in the Southwest during the spring, and then it's also, there's less rainfall being received here in the winter. And this is puzzling for a number of reasons. It's like I said earlier, like we know that when it's dry, we expect it to be hot, but what's really surprising is that it's happening like in the season before. So there's this long time scale over which it's happening. We're saying that moisture anomalies as far back as spring and maybe even winter have some sort of influence on the summertime temperature. But also there's this like spooky action at a distance that's going on where the soil moisture anomalies that seem to matter are the ones that are happening, you know, down here in the Southwest US. But when we're trying to think about the temperature and the summertime climate, it's up here more around like Idaho, almost like Mountain States, Pacific Northwest. So it's super mysterious. But if we manage to figure it out, there's some like really big implications for predictability, like seasonal forecasting. And yeah, so if I am able to figure out like what makes this connection work, then that would suggest that if we have like less rainfall in a given winter, so you know, maybe that happened this year, and it was followed by drier soils in the spring down here again, then we would be able to say that, oh, like we expect that in accordance with this pattern and its associated behaviors, there would be a warmer and drier summer. So sorry, my slides keep auto-playing, but yeah, so I'm gonna end my talk there and just like take questions for a bit. Like I have many backup slides with lots of different details about this, so you guys can pick what's most interesting to you, and I'll just end this here with a summary.
Thank you so much for sharing, Lily. People can put their questions in the chat, and hopefully we'll be able to answer a bit more than some of the other talks. And thank you so much for such a great talk, Lily. Astra H wants to know, speaking of soil, how do things like poor soil and dust bowls interact with weather? Is overused soil associated with bad weather, and if so, how?
That is such a great question. Okay, let me think about it a little bit. So in terms of like dust bowls and poor soil, from an atmospheric science perspective, like what I would say is those things are influenced by the like climate in a given year. And so there's a lot of studies that like talk about the usually like dry conditions that are producing those. But as for how they affect weather, that's something that I don't have as much expertise in because, well, dust in particular, like actually at some point when the dust is entering the atmosphere, it's like a particulate and it becomes like those things that Joel was talking about. So that's like a little bit more almost in the realm of like atmospheric chemistry and thinking about like clouds and how particles affect them. Overused soil associated with bad weather, and if so, how? So yeah, lots of great questions about soil. And I'm not like a soil scientist, so I can't say I have all the answers, but one thing that I think is in terms of land management that's super interesting is that scientists have found that sometimes it's not just like the condition of the underlying soil itself that matters, like how dry it is or what its properties are, but actually like something that's really important is the spatial gradients in soil properties. Okay, so what I mean by that is one example, when we think about precipitation and the convection, so forming clouds that's necessary for that to happen, scientists have found that when you have dry soil next to wet soil, like that actually creates very favorable conditions for convection. So it's not just about whether you're wet or dry, but it's about this sort of spatial difference. And then on a more like human level, so this applies like at the boundaries of urban areas, like that's a really interesting application of this research. You can look up urban meteorology if you're interested in learning more. But yeah, so if you are like thinking about what's happening at the edge of a city and where it's like meeting the non-urbanized land, like that actually that is something that those scientists would say like you have to account for in the models, and you have to actually have like a lot better resolution of the processes that are happening there to understand how they're affecting weather. Yeah,
that makes sense. I wanted to just say, Lily, that I really appreciate that you started your question being like that you don't 100% know the answer to the question. And I mean, out of the talks that I've heard so far, like I don't think I heard anyone say that. And I think it's really important for us to convey to, when we talk about science, like things that we don't know and like still make a guess toward what we think might be the answer, but you know, giving it that degree of uncertainty. So I really appreciate that.
Oh my God, yes. That like reminds me, don't think I ended up including this slide about it, but I think like the best part of studying when I do like land atmosphere interactions is like normally like I'm thinking about the atmosphere, like I'm up here. But in order to study land atmosphere interactions, like you have to combine insights from the field of atmospheric science, but also the field of hydrology. And so like there's a lot of like really cool opportunities for collaboration between atmospheric scientists and hydrologists in this space. And I think in general, like that is like the really fun part of doing climate and thinking about the Earth system as a whole, even though I still like haven't really touched the ocean. I think, you know, there's plenty of people working on it. Yeah.
Yeah, it's really interesting you say that. Like I'm probably going to take a land atmosphere interactions class. How it goes. It's kind of elective, and like someone on my committee is like really in that space, so it'd be kind of interesting. Yeah. Okay, Annie Pinecone asked a really good question. Do you think the mountain ranges might be a big factor in the disconnect between ocean and land climate changes in the Western U.S.? I'm not sure if you feel confident about answering it, given what we just talked about, but
Yeah, let me think a little bit about that. So, yes, the mountain range and like the continental divide is super important. And if you like just look at a map of the average soil moisture across the United States, like there's a pretty clear divide in like what we would consider a more arid or dry climate and like a wetter climate that is like very close to where the continental divide is. And that's because of like more hydrology things that I'm not an expert on, but like about how it relates to the positioning of the watersheds and whatnot. From a atmospheric dynamics perspective, this is actually like very much a topic of debate because one thing about mountains, so this is not volcano mountains. So one thing about mountains is that when air is like moving across the mountain, it has to like go up, right? But what happens as air goes up? Well, as air goes up, it cools, and cooler air holds less water vapor, and so some of that water vapor condenses and like maybe forms clouds, like maybe affects precipitation. But also just the fact that the air is like being lifted affects its other properties, like how spinny it is, like its vorticity and other things. So this is like very much a thing that people in the climate dynamics community like to like have debates about. Like obviously they're very important, but like are they important for everything? That's a kind of like a case by case basis, depending on what part of the climate you're talking about.
I think that was a really good explanation. I was like doing this for the air moves upward. I was like, yeah. I just finished a climate dynamics class, so.
Oh, yes.
Yeah. Okay. How's everyone feeling? People are asking really good questions today. Okay, I'm trying to see if there's any more that are a little bit less land focused for you, but it's okay otherwise.
Oh, I see a fun one.
Okay, which one?
About like how if you can affect weather by doing something to the ground, like planting trees to impact weather patterns or something similar. Yeah, so again, this is not my current research focus, but something I think is like super cool, and try to read a lot about like the field of urban meteorology. And so yeah, like when you have structures like skyscrapers and like trees, but especially like really tall skyscrapers, you're affecting like a lot of different things about the surface properties, especially like the what's called like the roughness of the surface, so how air is like moving across the surface. And this has this is like an active area of research, but people have looked at how like precipitation and even like tornado formation happens like either like upwind or downwind of cities, like one of those. So that's something to look into. But your question also reminded me. So one big thing that I didn't mention in this talk is like the albedo, right? So how reflective the Earth's surface is, and how reflective the Earth's surface is depends on like its color in a lot of ways, because the sun is like visible light, right? That's why we can see, and so color is some indicator of how reflective or absorbent a material is. And trees, they do a lot of things. Like I didn't mention plants, like they're a big that'd be a big reason why the land surface matters, like plants are on the land surface. But one thing that I think is lesser well known is that so one of the measures of like helping offset increased carbon dioxide is planting more trees, because trees uptake CO2. But something people don't think as much about is that trees have a pretty low albedo. Like that means is just that they're dark, like green is darker than white. So if you plant a lot of trees like up north, you actually get like a local warming effect in the winter. Then we could see this in the boreal forest. So if you're replacing snow with these like dark absorbent trees, then during the winter, instead of this like super reflective snow, you actually absorb more heat. And this is like something that I think Carbon Plan would be like, they would be a good organization to look into. They have written pieces about how we should be thinking about that part of it, and like people are maybe getting too many CO2 credits for their tree planting and for other reasons.
That's a really cool mention, yeah. Okay, so kind of running out of time. Sorry about that, Lily. But I've been having a good time talking to you and hearing about your research.
Yes, and I will be back to host in like maybe like I don't know, 2 hours or something. You'll see me again.
Yeah, so Lily's gonna be back later. Okay, well, thank you so much for now, Lily. That was a really great talk. Everyone say good job, Lily, and how much you liked her talk. All right, thank you. Okay, we are now halfway through hour 16 of the weather and climate live stream, and that means there's only 83.5 more hours to go. But for me, it's only going to be my last half hour. So for those of you who just joined, my name is Vanessa Sun. I'm a PhD student and atmospheric chemist. This is going to be the last talk that I'm hosting after 3.5 hours. So I saw all the love that people were giving graduate students when I introduced this segment in the beginning of this hour. So I wanted to say thank you all for appreciating our early career scientists, along with such great experienced professionals throughout this live stream. Thank you all for having me here, and I hope you continue to enjoy the coming weather and climate talks.
Thank you so much, Vanessa. The number of people, if you are... If you've never met a Virginia, the number of people who are confused by the name Virginia and call me Vanessa is so big. So hopefully this is a very smooth transition. Good morning to people who are at some hour where it is very early morning, like me. It's 5 a.m. my time. I have my tea. I also am more excited than I am going to sound like I am, but my kids are up there sleeping, and if I wake them up, everything will be less good. So welcome to hour 17 of the live stream. That sounds like a small number. There are 87 hours to go, but I'm very excited to shepherd you through the next 2 hours. This is going to be very fun. And I just want to start by reminding us why we are here on your screens. We know how important weather and climate forecasts are to you and to everyone in the United States. Luckily, we've been a world leader, the United States has, for a long time in weather and climate prediction. And the prediction part is so important. It's so much harder to do prediction than it is to just say what is happening outside. involves a lot of extra stuff. We developed the first computerized weather forecast to help you know what you can expect in the coming days and weeks. And we made the first computer models of the climate impacts on carbon pollution so you can know what to expect in the decades to come. To make these forecasts work, we've created an unparalleled network of observations using everything from weather stations to satellites, phones, balloons, boats, and floats, and the resulting forecasting and observation systems are true scientific miracles, and we're excited to share some of those miracles here with you right now in the next 2 hours with me. This miracle was made possible. These miracles were made possible by decades of investment by you, the American public. I am seeing so many comments, and I'm so excited that y'all are awake to and not just watching passively. Oh my gosh, I'm seeing people from India. There's someone who's a fellow mom. I was hoping I'd run into somebody who's maybe up with a little or something. Somebody from New Zealand. Okay, so I'm definitely, where are the United States people? Austria. You're here from Blue Sky. Okay, Denmark. All right. The global crowd is showing up in the comments. Is there anybody here from the US? Sound off. Where are you this evening, this time of day? This miracle, and people are commenting in the chat about how this is not just forecasts that affect the US. Our forecasting capabilities affect global models, affect global behaviors and decisions. So let me get back on track. I'm supposed to say some stuff. The investments, the miracles that were made possible by decades of investments from the American public. But in recent weeks, funding cuts in the United States have put our miracles at risk. Weather stations are so short-staffed that we're losing our observational coverage, which is already hurting our forecasts. Laboratories dedicated to understanding our climate's future are being closed or shrunk, and funding for our basic understanding of the weather and climate is disappearing. So I'm very excited to be here, but the reason that we are here is very serious. It doesn't have to be this way. If you like what you see here, then we ask you to please keep the link. Please use the link on your screen to contact your representatives, not if you are elsewhere in the world. We appreciate y'all globally showing up, but if you are in the States, it takes 2 to 5 minutes to use this link to contact your representatives, tell them to save our forecasts, to keep the lights on for weather and climate science so we can keep the miracle alive. And please spread the word to join this live stream. If you are in the United States, we got to show up. All these people in the chat from somewhere else. I am seeing North Carolina. I am seeing a fellow American tuning in from the UK, in New York. Let's see, San Diego, Washington, D.C. Yeah, I love this crowd. Y'all are doing great, doing great. Let's see. Our first speaker is going to be Craig. Good morning. Can we bring up, sorry, I said the wrong name because it is so early. I said Chris.
Hey, that's all right.
It is Chris.
It's not a problem at all.
Thank you so much for your flexibility. I got so excited about the mission statement that I lost myself a little. So Chris Osburn is a professor of marine biogeochemistry at North Carolina State University. I'm so excited because we overlap a little bit in expertise. I'm trained as a marine biologist, so I feel like I was looking at the stuff I could see moving with my eyeballs. And Chris, you were not doing moving stuff with eyeballs, right? You were a little bit different.
No, a little bit different. I'm a marine chemist, a biogeochemist, and so, but I do use vision in a certain way and optics, and so I'm going to be talking about that this morning.
All right. Well, I'm going to hand it off to you. Thank you so much for joining us, and take it away.
All right. Thanks so much. And good morning or good afternoon or good evening, wherever anyone or everyone is. So I'm going to talk a little bit about how we can use weather information and forecasting to help with biogeochemistry. So thinking about carbon cycles in coastal zones. We call this the seesaw concept. And I'm also going to end up talking a little bit about how we can use this to help municipalities look at their coastal infrastructure. So there's some connections we'll make here, and a way really not working so much with modeling weather data or generating forecasts, but rather how we can use that in a couple of different applications and why it's so critical for climate scientists and geoscientists broadly. So I just want to acknowledge also my collaborators, Hans Perl and Nathan Hall at the University of North Carolina Institute of Marine Sciences, and my student, Sarah Cornejo at NC State, who's helped out with some of this work. I'd also like to acknowledge funding. So as was just mentioned, the U.S. citizens fund an enormous amount of this work, both at the federal level and at the state level. And so that's supported our work over the years. And I just want to give a shout out to our supporters and to note the prominence of their missions. So what's the theme of this presentation? Well, the theme is that coastal ecosystems are dynamic interfaces between land and ocean, and about 40% of the US population live in the coastal zone. Over here on the right, you can see a little factoid that the NOAA agency has generated. And in addition to that population, it's also an economic powerhouse, 10 trillion in goods and services, over 54 million employed, and 4 trillion in annual wages. So it's an important space. A lot of us like to go to the coast to enjoy it recreationally, but a lot of people live and work there. Coastal ecosystems are very strongly influenced by weather. And so we need information on weather to be able to predict changes to these coastal ecosystems, because they do change. They are responsive and susceptible and even threatened by changing weather and climate. And so we need to be able to have that predictability to help protect, preserve, and utilize those ecosystems. So when you are in the coastal ecosystem game, a lot of times, especially in North Carolina, you can't get away from thinking about extreme weather events. They tend to wreak havoc on coastal communities. So these are just some examples. The one on the left here, this worst case flooding scenario, this is actually from South Louisiana about 15 years ago. In North Carolina, we experience frequent hurricanes. This is a picture of intense flooding in New Bern, North Carolina, in Hurricane Florence in 2018. And when this happens, a lot of times we also worry about public health issues, such as the increase in pathogenic bacteria caused by some of these floodwaters. So they can wreak havoc, causing a lot of damage. Now, North Carolina is a coastal state, and so when I think of North Carolina, this is the picture that always jumps in my mind, because this is where I do a lot of my research. We have over 1 million people in the coastal population of North Carolina. And what you can see in this image here is the nation's second largest estuarine system. It's called the Albemarle-Pamlico Sound System. There's a number of rivers that feed into that. And these rivers are estuarine, so that means they mix with seawater. They're microtidal. And this system is one of the most important Southeast U.S. fisheries nurseries. So it's a part of that economic powerhouse. One thing I want you to notice here that's going to relate the carbon to the weather is this change in color. So you can see the landscape, but if you notice these tributary estuaries here, the Chowan River, the Tar-Pamlico River, and the Neuse River, they have this really brown cover. They transition into kind of tan and green, and then offshore in the ocean here, you can see that nice blue color we usually think about when we think of ocean water. So this transition is really where me and my colleagues tend to play. So we're really interested in what the chemical, biological, and physical processes govern the color of these waters, and what it means for various aspects of carbon cycling, nitrogen cycling, nutrient cycling, but also ecosystem health and water quality. So why is weather important for these systems? Well, we appear to be in this period of increased tropical cyclone activity. So in North Carolina and in the Atlantic Basin in general, there are observations that the number of these storms and the intensity of these storms is increasing over recent years. And what this does, and what I'll be focusing on for this talk, is it delivers an enormous amount of precipitation inland. So a lot of times we think about coastal flooding, and that comes in to play and is quite important. But I'm also talking about the extreme flooding that happens in the coastal landscape and then tends to wash materials from the landscape, both natural and anthropogenic, into coastal waters. And so we kind of conceptualize this as the seesaw. So we focus on carbon, but there's other things involved like nitrogen, phosphorus, nutrients, and some other constituents. But we really look at that color change, which you can see represented here is this sort of tan part of the coastal zone. And what we're interested in understanding is how the variation happens over time and how weather is driving this variation. Now, I mentioned water's color, which is actually, we term this CDOM for colored dissolved organic matter. And this cartoon here sort of gives you an idea of what this is about. It's the substances largely coming from the landscape, such as soils, plant materials, and even some anthropogenic sources like sewage and other pollutants. These come into the coastal zone. They actually color the water, and then they absorb sunlight. And so that has important ramifications for the health of the ecosystem. It can suppress photosynthesis, so it affects plant growth. It can transport nutrients. It can transport contaminants such as metals. So there's a whole host of things that color can be a guide for. And as you saw from the picture before, it's easy to see from space as well. So when it rains, there's a lot of these sources of CDOM. So it's not just the amount that's there, it's where it's coming from. Where it's coming from is not always the same place. So it means that we can use the optics to track, that is the absorbance and then the fluorescence, which we'll talk about later, to track where this is coming from. So here's some examples. You can see this is stem flow. So this is rainwater running down the stem from a yellow birch compared to this stem flow collected from a maple tree. You can see the difference in color here. And this graph on the right just shows ways that scientists can actually measure the color more discreetly. And you can see, depending on the type of tree and where it comes from, either falling along the stem or through the canopy. This is what's called throughfall, that you have these differences in the amount of absorbance that goes on. Well, another way that we can map this out is by looking at something called fluorescence. And so that's light that's given off when these substances in CDOM absorb light. So you absorb some light and then you give off some light. And the giving off of light is actually rather sophisticated. We can tell differences and create these plots that we like to call eames. But things look different when they come from different places. And so you could very clearly see the difference between this soil leachate. So this is CDOM coming from soil versus what comes from plants. And you can see the differences here. So when it rains, there's a lot of CDOM sources, not just the stem flow and the throughfall from the plants, but also just that which accumulates in rivers, that which is discharged in wastewater, what runs off the street when it rains, wetlands, so on and so forth. So we can use this fluorescence property to make these maps and fingerprint these different sources. And this just kind of shows exactly what this looks like here. So you can see this is a wastewater treatment plant effluent, sewage or domestic and industrial sewage going into a wastewater treatment plant, and other types of sources. So we generate these fingerprints, and then we can see how these sources change with response to weather. So think about it this way. This is September 3rd, 2018. You can see this is the Pamlico River estuary. This is the Neuse River estuary. You can see some of that nice brown color here. Most of this is natural, mind you. It's not pollution. There's some pollution in there, but most of it's natural. And then you can see the coastal zone here. Weather has an effect on the color when this sort of thing happens. So this is the rainfall totals from Hurricane Florence. Our region of interest is right here that I'm encircling with the pointer. And you can see over that time, we got about, was not quite 15 inches or so of rainfall in the river's water, or the estuary's watershed. Notice now the change in color here. You can see that the brown persists. We've got this brown and tan overwhelming the green in the sound. And then in these smaller coastal plain estuaries, this export of the brown out into the coastal ocean. So you can see how rainfall dramatically changes the color that's related to the carbon cycling and even the nutrient loading and water quality that's going on. So we worry about this because what's happening also is that where we're seeing the material come from changes in the landscape based on the weather. And so the heavy precipitation floods wetlands. And this is just another map of heavy precipitation. This is after Hurricane Matthew in 2016. And then this is just showing the river above the estuary in this top graph before and then after the flooding. And what you can see here is that there's an increase in the amount of that color. It's basically, you can think about, we're steeping the landscape just like you steep a tea bag and make your tea. It's the same kind of thing here. We're extracting that carbon and nutrients out of the landscape and pushing it from the terrestrial environment into the coastal environment. So I want to raise an issue about this. It's kind of an emerging issue in my discipline, and it's, why would this color be a problem? I mean, it looks different. You know, you might think, oh, I don't like brown so much, I like blue better. Well, there's also another issue related to it called coastal darkening. And this is a link here to an article that was written a few years ago about this, but lays it out quite nicely. And part of the problem is that it's the absorption of that sunlight. So not only does the CDOM take light away that would be available for phytoplankton growth, but you can see in the cartoon on the right here that it also impacts other types of things like vision. So not just scuba divers or underwater vehicles, but also visual aquatic predators that use vision to find their food. So there's a number of different plant and animal species that can be affected by an increase in this color. Another particular effect can be a increase in oxygen consumption caused by the loading of organics and nutrients as well. So together, these can actually cause some problems, and we're trying to understand more about how that works. And so you can kind of see this put together in this cartoon here. The effects of darker water can reduce photosynthesis, it can reduce plant growth. There's also a sterilizing effect that sunlight, especially ultraviolet sunlight, has, and can break down some toxic chemicals and reducing this underwater vision here. So now let's look at a little bit of what we've observed in the lower Pamlico Sound. That's just where the Neuse River outflow or where the Neuse River flows into. And this is looking at light attenuation. So there's ways we can take instruments out and look over time, and you can see here that these are averages. This is a box and whisker plot, so you can think about median values over about nearly 20 years of time here. And you can see that from 2010 through 2014, it's about 1.2 or so in terms of what we call the attenuation coefficient. So just think about the values. Clearly, you can see after 2015 and in years where we had major hurricanes like Matthew in 2016 and Florence in 2018, that those attenuation coefficient values are increasing. You can also notice some variability there. But that variability is important. It's not just a unidirectional thing that we're seeing. We're seeing some variation over time, and being able to relate the atmospheric and meteorological drivers that are causing these changes is something that's quite important, and we're spending more efforts in order to understand that process. So another thing we did is we looked at that time series, and we only had particular chunks of it for this plot here. This is another way on that we can look at the color. It's this value of A350. And again, the more A350 you have, the more color that there is. So just stick with me here as we get through this one. The point being in this plot is that what we found was that during this 2010 to 2013 period, when it was a much drier period of time, we did have a hurricane, we had Hurricane Irene, but you'll notice here that the color was a lot lower in the way that we can quantify it compared to the stormier or wetter seasons or period of time that we've had from 2015 through 2019. The other thing I'll point out is that this tan line here in the dry period, here in the wet period, that corresponds to our ability to use fluorescence to map out where the color is coming from, where the CDOM is coming from. And what we show here is that it's very clearly becoming more dominated by wetlands as they become connected to the main stem of the river, and then that's exported into the estuary and then into the Pamlico Sound. So the drivers behind that are not just alone in North Carolina, but happen all along the eastern seaboard. And you can see that here. This is an image of the eastern coast of the United States, ranging from Chesapeake Bay that I'm noting here all the way down into the South Atlantic Bight and into Florida. So hopefully I've shown you here in this part that rainfall differentially affects coastal environments. Some of these lagoonal systems can retain this material, or the other estuaries will export it out to the coast. But the important point is we need agencies to provide weather, climate, and carbon, like CDOM information, so we can understand these processes and, again, make appropriate responses to them. So I'm just going to wrap up my part today with just a couple of points about how we can also turn our attention to using this technology along with weather data in support of municipal infrastructure. So the idea here is I'm showing you on the left, these are wastewater treatment plants that we've worked with within the state of North Carolina. You can also see the corresponding weather stations where we've been able to pull in weather information. And on the right, again, this visualization here that we're using this fluorescence technique to try to understand how this municipal infrastructure is being affected. So what's the problem? So the problem is for wastewater treatment plants. Again, we're moving a little away from carbon cycling, but there's still some connections here. Inflow and infiltration comes from rainwater, stormwater, or groundwater getting into our municipal infrastructure. And increasing the total volume is a problem for wastewater treatment plants because it overloads their capacity. It raises operating costs, so municipalities are spending more money to fix the plants. It's also to treat water, and it can cause these sanitary sewer outflows here. So inflow comes from stormwater getting in, and that's runoff from the road surface. It could also be from other sources. And then the infiltration comes from sort of cracks in the system, aging infrastructure, letting in groundwater, or even perhaps stream water, depending on where the sewer pipes are located. So what we did is we worked with the North Carolina State Climate Office, who provides critical and actionable information, weather data, as part of their EcoNet network of weather observations. We combine that with some of our fluorescence techniques to try to understand this problem. And so I'm going to show you here just two examples. This is from Wilson, North Carolina. And the top plot is showing in the blue dotted line, this is the summed 5-day rainfall before a sampling event. And you can see here that this is, there's some variations over time, some higher rainfall amounts and some lower rainfall amounts. The orange line is showing the rate of flow into the wastewater treatment plant in Wilson, North Carolina. And if you look at the peaks here, they roughly correspond to some of the higher rainflow amounts. Now, the bottom plot, this is kind of busy, but what I want you to focus on are two things. One is that the tan colors, that is the sewage source. Okay, so so we should, if all things being equal, we only really should be seeing just tan across the board. But what you can see here is that we don't in fact see that many times corresponding to these rain events, especially, we see both groundwater and rainwater getting in. And the importance of showing this is to say that many times last year, this plant was actually treating groundwater and rainwater. They weren't treating the sewage that the plant is designed to do. So you can see here how severe that some of this weather is causing problems in terms of the dilution of inflowing sewage into this plant, and then some of the operating costs that would be affected by that. Here's just another example. It's the same kind of thing, although the effects are less severe. So in this case, you can see that there's much less impact, only episodically throughout the year, but again, related to these heavy rainfall events. So the takeaways are that in addition to thinking about how coastal ecosystems and their health and public health is changing, that these types of chemical techniques that we can do in the lab can support also weather data, and just emphasizes how important this process is and the impacts of extreme weather on municipalities as well as our natural ecosystems. So just to wrap up, worrisome feedback is this seesaw. So we have more intense storms, which can cause more flooding, leading to more carbon that's mobilized, CO2 released, and the feedback into these more intense storms. And on this macro level, you can also have these more localized impacts to habitat, coastal water quality, and in the case of the municipalities, the coastal infrastructure. So it's critical for us to know where it rains, and gridded precipitation maps can be hugely important for this in order to understand where the carbon's coming from, or in the case of this infrastructure, where the dilutions, the source of the diluting water is occurring. And so just to conclude then for today, there's a national need for weather forecasting to benefit our coastal ecosystems, and predictions are indeed the key. We need to be able to create predictions for preparedness, for responses, to support and maintain and repair our public infrastructure, and to manage our natural resources. So I'll stop there, and thank you for your attention. And again, just highlight some of our supporters, and then also highlight some of the coming satellite missions that will improve our ability to connect carbon cycling, coastal management, and weather. Thanks.
Thank you so much, Chris. I know you were busy giving your presentation. If you have time sometime later today, you should read through the comments that were coming in while you were giving your presentation. Everything from beautiful visuals to Kat asked a question right as you switched to a slide that answered the question. It was just a beautifully done presentation. Thank you so much. I do want to address really quickly, Kelly in the chat asked, is there anything that citizens can do? And Lily responded with a link. There's also an action link that you can find in the description to this live stream for US people in the US to call their representatives. And I just want to remind y'all that one of the most powerful things that we can all do is talk to each other about whatever it is that we feel should be happening with weather, climate, science, the way that governments serve us. And I see some people in the chat saying like, but where are the active people? And like, first of all, some of us are on the stream right now, right? Not all the work gets done in public so that you can follow every piece. So I just want to put a little injection reminder that like, you don't be discouraged if you cannot always see an entire, movement or country of people rising up and screaming. Like people are always working to make things better. We are always fighting to make things better. Talking to each other is one of the things that can encourage us. So Chris, I do want to give you a chance to just leave with one kind of sign off. You had so many questions and we just don't have time to read them all. But I just want to give you a chance to address the first one that came in because it resonates with me. I was saying that I like to see stuff with my eyeballs. Honestly, I haven't thought about seeing chemistry in nature the way that you talked about it with the color and the imaging. And someone asked, I wonder if estuaries have unique ecosystems from the rest of the coast since that mixing of fresh and saltwater is there. Can you talk just a little bit about what it's like to be out in these ecosystems and what you see and how you read the ecosystem? Because it's like everything from the small, but you're seeing it large. So what's it like to be out there doing this work?
Yeah, thanks for that question. That's really good. And I think Kelly is right on that. The way we sort of first order view this is looking at the salinity, which tells us how much mixing there is between river and freshwater. And so oftentimes what you'll see is there's a good correlation or connection between the color and the water. And if you start looking at the phytoplankton contributions and distributions of species, or the fish species, or even if you go into the bottom waters and look at the benthos, you can really see dramatic changes along those gradients of both salinity and color. And so it's really fascinating. I've been on several different types of estuaries, ones like big river plumes in the Arctic, as well as in the Gulf of Mexico. and also, smaller and more lagoonal systems like the Neuse River Estuary and the Pamlico Sound. And they all share that kind of mixing and the palette of colors, but the way the palette manifests is really quite different and for different ecosystems. And one of the beautiful things is that estuaries are unique ecosystems compared to other types, but each one is unique itself. And so it's really fascinating to be able to work with all of these different systems and be able to see those transitions.
Thank you so much. We are going to transition to our next speaker. I will let you get off to your day. I know you're on East Coast time like me, so happy 5:30 in the morning.
Same to you. Thanks so much.
Bye.
Bye.
If you are just tuning in, we are in the middle of hour 17 of 100. That was Chris Osburn, professor of marine biogeochemistry at North Carolina State University. I am going to give a little bit of time for our next speaker to get ready, and I'm just going to remind you all in the interim that we are so excited, whatever time of day it is for you, wherever you are in the world, for us to be talking about science on this level, right? This is not just like fluffy, we're all happy together. That was some real learning that I just did, and I hope that y'all are doing too. And based on the comments, I love the energy y'all are bringing. So I just want to, focus. I'm going to remind us why we're here. Weather and climate forecasts are important. U.S. scientists have been world leaders in weather and climate predictions. And the prediction part, again, is so much more difficult than just reporting what's happening outside your window. Scientists in the U.S. developed the first computerized weather forecast, the first computer models of the climate impacts of carbon pollution. We have built an unparalleled network of observations, not just around the U.S., but in other spaces as well. This involves weather stations and satellites and planes and balloons and boats and floats and so many people that are not out there with that stuff, but are in front of a computer processing what they see, the data as it comes in, but then also sharing what it means and how we can make decisions based off of that data. This excellent stuff is all happening because of public investments, money, resources, support for the scientific system in general. U.S. federal funding for the engine that drives science has just absolutely been essential to making all this happen and is essential to keeping it going. Funding cuts in the United States are affecting all areas of weather and climate science. And so that's why we are doing this live stream, is because weather stations are short-staffed now. Climate labs are shrinking in terms of their capabilities, or they're being completely shuttered. Again, there's a link in the description for this video. Lily is posting links in the chat. And so if y'all feel the need to do something, there are things that you can do. So our next speaker, I want to take us back to the science. Our next speaker is Paul Staten, who is an associate professor at Indiana University, Bloomington. And I love how y'all are just so engaged in the chat. Good morning. Yes, good morning, Paul. Are you on East Coast time as well?
I am. It's bright and early here at my place, so I'm in my closet with moving blanket, recording studio equipment.
I wondered, your background looks a little bit like an abstract something of a road, and I was like, where are you? In your
Yeah, I
closet?
could unblur that, but then I thought the reflections might be even.
It's a nice artistic, especially with your red shirt on that black background. Oh, you look so professional. I feel like you are ready to give us a whole podcast episode with that setup. Those blankets make me think of somebody who's going to whip out like a really nice microphone.
Well, I do have the really pretty nice microphone. I teach an online class, and I try to make the recordings for my students as good as I can.
Honestly, from what I can see, it looks like the recordings are just spectacular. So I do want to give you, sorry, I'm taking up your time with chit chat. Let's get to the science. I'm going to hand it straight over to you. Take it away, and I'm excited to see what you're going to talk about.
All righty, sounds good. So I'm looking at it looks like I can see my slides on the left on yours, even though I'm not using presenter view. That's interesting.
Yeah.
Let's
It just
try
gives
this one
us
more
a
time.
sneak peek of your beautiful pictures. I mean, you are all about the visuals and the audio. My goodness.
All about the visuals here.
You could share a portion of your screen if you like and just highlight that little bit.
Right.
Or we could just have the surprise of another. Oh, there we go. That did it. Thank you.
There we go. How's that looking for you?
That's great. I can
There's
see
a little
menu
bit
top
extra.
and bottom, but I'm not having any surprises revealed before they come.
Yeah, great. Okay, so yeah, thanks. Yeah, we definitely are presenting here at our own places. Do you ever wonder why there are wispy clouds above you? If you're in the middle latitudes, like many of us here in the States are, you get wispy clouds above you sometimes. Or when you get stormy weather, you get stormy weather for days at a time. Here in the Midwest, we had this storm outbreak. We had a tornado come within 1.5 miles of our house a week and a half ago. It was really something else. But then now we have this cool, dry weather, and it lasts for days at a time as well. And these why questions, they're fun to chase for curiosity's sake, or if you're like me and you maybe took science classes, or you grew up watching Nature, Noah, or Bill Nye the Science Guy or something, and you had these, we're curious about these things. They're fun to chase for that reason, but also understanding why is pretty important. I'll get to that in a little bit. Or maybe you live a little further south than I do, like maybe you live in Arizona or something, and you wonder why it's a desert where you live. Sorry about the dark background. And why you get so many thunderstorms some years during July, but other years you just get nothing, right? The climate and weather are very different in Arizona than they are, just a few degrees further north, well, and east here in Indiana, where I'm living these days. But I'm from the West, and I really appreciated it, even as far north as Utah. Once that Southwest American monsoon would kick in and our weather, we'd finally get some good looking thunderstorms. And if you are tuning in from Arizona, I am quite jealous of the photogenic thunderstorms you get all the time. So why do we have these differences? And the answer is the jet stream. Here you can see this image of the jet stream over North America, and you can see it's these strong winds bending and blowing over Canada. And you can see that if you live down in Arizona, you are far away from the jet stream in this snapshot, where if you live in Indiana, you are right next to it. And the jet stream it looks wavy, right? It's got dips and it's got peaks and troughs. And when your peak goes through, you're left on the equatorward side, and you have warmer, typically drier weather. And then when a trough moves through, you get this dip in the Arctic or polar air, and you tend to get more storms just on the leading edge of these troughs. And you can see that these peaks and these troughs can be hundreds to thousands of miles wide. And so when a peak moves over you, you're going to be in a peak or under a ridge or high pressure for several days, likely. When a trough moves through, you can have low pressure moving in or low pressure over you for several days. So here in the middle latitudes, this jet stream really gets us settled in for weather types for days or even a week at a time. And it defines the weather experience that you and I have in the middle latitudes. Whereas if you're tuning in from, say, the tropics, you can get storms each afternoon, and the weather patterns that you experience can be the same for months at a time. And these are both part of something called the general circulation. That means like the global circulation of the atmosphere. If you study atmospheric science, there's a good chance you've seen this image in a textbook somewhere before. And you can see that the general circulation is this east-west pattern around the world. You have the doldrums in the tropics. So if you're sailing and you want to go west, the tropics are the place to go. You got good winds blowing from east to west pretty often near the equator, but you'll get little thunderstorms and rain each day. And if you want to go from west to east, you would want to go further north. And so you would want to go into the middle latitudes here where we have the jet. If you remember from your American history, when white settlers came from Europe, you can see Europe here on the right. They would often sail south to Africa, then sail west to South America and the West Indies, and then they would come sail back north before going back to Britain. And they would be, buying and selling goods and people along the way. But Great Britain had the perfect setup to form an empire back in the day. So this general circulation is really wrapped up in human history and the lived experience you and I have with weather. And this picture is a real oversimplification. It doesn't go straight west to east like this. It actually varies quite a bit. So why does it matter? I told you that it makes a difference for our history, but at the beginning of this slide, I started with why. Do you ever wonder why these things are the way they are? And this question is important for climate change because climate change is a big deal, right? It's going to be changing a whole lot of things. It's going to be changing ice. It's going to be changing extreme weather, like how much rain we get, flooding, hurricanes. Wildfires are even affected. Maybe you've been watching what's been going on in California. If you're impacted those, I'm sorry. Droughts, heat waves, all these things are big consequences of climate change. And these are the consequences that we are quite sure about. A lot of these are straightforward consequences of, well, we have a warmer atmosphere, right? Okay, well, if you have a warmer atmosphere, you can dry out a desert much more easily. On the other hand, if you have a warmer atmosphere, that atmosphere can not only dry up things more easily, that moisture goes somewhere. It can also take that moisture and dump it somewhere else more heavily. So a lot of these things in this slide have to do with heat and moisture. And some of those are the most straightforward consequences of global warming. But other consequences of global warming are trickier, like changes in the winds. So here I have listed a bunch of different consequences of climate change, and most of these are related to heat and moisture. 2, 3, 4, 5, 6, and 7. 4 is like permafrost melt. 5, sea level rise. 7, changing ocean currents. These are straightforward consequences. 1, ocean acidification. Well, if you pump out carbon dioxide in the atmosphere, it's got to go somewhere. So that's a pretty straightforward consequence. 9 is an interesting one. Maybe you've experienced more turbulence than you remember before. Pilots are experiencing this too, and this is a fairly well understood consequence of climate change nowadays. But the changing wind and ocean current patterns are really hard to get just right. I feel like the ocean is like the final frontier of climate modeling. We've got to get the ocean right to get the details right, because a few seconds ago I said these are sure consequences of climate change, but just where precisely these are going to occur is a little trickier. Like I can tell you the Midwest is going to continue seeing larger, heavier floods in the future. But if you were to ask me, what will Bloomington, Indiana, where I live and work, see? I would say, well, we'll probably see, larger heat and rain extremes. But if you want me to get more specific than that for a specific location, I need to know how the ocean currents are changing and how the wind patterns are changing. And just how precisely those change, that's where things get more challenging. And this is where that why comes in, because we understand things with we understand this large scale shift, but it isn't just zonal mean, west to east average, I should say. It does vary. And this is just how much it varies from west to east. These orange areas are the world's subtropical deserts. So, I'm from Utah. I mentioned Arizona. There's desert over there. I live in Indiana. I am no longer in a desert. You sneeze and it rains over here. And, I'm due east now of where I grew up. It's not much north or south, but it's very different. And in a changing climate, we expect these circulation patterns to shift. Actually, this subtropical high around 30 degrees north, we expect that subtropical high to expand, particularly on its poleward side. Now, if we lived in a world like this, you would look at this image and say, oh, well, I live in California or I live in Alabama or Georgia, and so I'm expecting more subtropical high kind of weather in the future, right? And well, you could be right. But again, it varies quite a bit. So an expansion of the subtropical high, that could mean very different things if you live in Arizona than if you live in Alabama. So not only is it expanding poleward because of global warming, but a few years ago, maybe you remember something called the ozone hole. When I was in elementary school, this was one of the big environmental issues we talked about a lot. And we don't talk about it so much anymore for some reason. Because and the reason is, as a society, as a global society, we basically got together and we fixed this problem. We've still got to be diligent to make sure we don't make it worse, but we've stopped the ozone hole from expanding. And that is tremendously exciting. You can actually, you can find research articles on what things would have been like today if it weren't for the Montreal Protocol back in, 92 was it? Way back when? And things would have been pretty rough today. Life would be very different if we hadn't fixed this problem. So one thing about global climate change is it is a big problem. Global warming is a large, intimidating problem. It's us, it's bad, but a great thing about it is that we can lick this. We have solved big problems like this before, and the ozone hole is gradually healing. But when the ozone hole was getting worse and worse each year, it actually shifted the general circulation in the southern hemisphere further south faster. And so when we discovered that general circulation was shifting, we discovered this first over the southern hemisphere where the jet stream was moving more quickly because of the deepening ozone hole. Now the ozone hole is recovering, which is actually offsetting some of the circulation shifts right now you see in the southern hemisphere. And just hearing that, speaking of southern hemisphere, Australia is in a drought right now, and these large-scale circulation shifts can have an impact on droughts. If you are having subtropical high move into your area, you'll probably experience drought more often. Australia is actually one of the places that's very interested in this kind of work. So good news is the ozone hole is healing. The circulation shifting in the southern hemisphere is offset a little bit now. In the northern hemisphere, we expect the circulation to continue shifting poleward the next several decades. And as global climate change, global warming gets stronger, the circulation in the southern hemisphere will eventually continue to shift poleward in spite of the healing ozone. And so here I mocked up some figures to say, well, how would things look different if we had an average west to east general circulation here on the left, and something more like what we see. And this is what I published in a 2018 paper with a working group of scientists all around the world. We wanted to better understand how this tropical circulation, or Hadley cell, I barely mentioned the Hadley cell. Let me rewind. That's this overturning pattern here. You have the storms in the tropics where air rises, and you get rising air causes thunderstorms. And then on the poleward side of the tropics, on either side, you have descending air, and subsiding air causes clear skies. And so a lot of the deserts around 30 north and south are related to that sinking, warming air. And the Hadley cell is in between the two. And if the Hadley cell were straight east to west, you'd see something kind of like this during December, January, February, northern hemisphere winter. But reading some other papers, I found a way people were looking at overturning locally, and I applied this to study the Hadley circulation, the subtropics. And so the doldrums, the ITCZ, this place you'd want to sail to the west and the equator, it's not straight west to east either. It's a little further south during the wintertime. And the northern edge of this Hadley cell, well, it's not even defined everywhere. If you want to know what subtropical circulation expansion means and you live in Arizona, well, I mean, this thing is barely defined way up in Arizona. And so it's actually a little hard to say what an expansion of the Hadley circulation means if you live in Arizona. If you live in North Africa or around the Mediterranean, it's a little easier. Or during the summertime, if you live in South America. And one thing that was interesting for me to learn from this is when I look at this from season to season, I can see how the boundaries of the Hadley circulation change from one season to another. And yeah, I could see where the wet season, where these little vertical ticks are, that's the wet season during DJF. And I thought, wow, Australia just doesn't have a really good, strong wet season. And yeah, you learn as you go. So this is what the Hadley circulation looks like as far as its strength goes. So red is like strong overturning circulation, and peach is a little weaker. And it really does change from west to east quite a bit. And that is changing. So here I'm zooming way in on this graphic, zooming in, getting things a little messy. The black thick line here shows where the Hadley circulation edge has been over the past several decades. You can't even define a Hadley cell edge at every longitude. And then the red ticks show where the Hadley circulation edge seems to be going. And this is based off of climate model projections. And so what you can see if you look closely is that there's a little orange shading dot here. We're getting a little more Hadley-ish, a little more subtropical here off Baja California. And so over the western United States and western Mexico, you may see an expansion of the subtropical high locally and the dry weather there. Kelly says, is it getting a little more wobbly? This graph is quite wobbly, and you can see that there are little wobbles in the black and the red, and that's part of this issue where things are so tricky once you actually start trying to take this global idea, which is pretty simple, and applying it regional. I can't say that the Hadley circulation edge is getting more wobbly. I think it looks more wobbly because you can see the red ticks more clearly than you can the black ticks because of all the other noise I left in this plot before presenting today. You can see that there are big changes over here. This is the East Asian monsoon circulation. This is the winter monsoon, and this is where some of the largest changes be experienced. This is where the overturning circulation is already strongest. So is it moving northward or southward? Here in the Pacific, you can see it's actually moving southward. It's not moving poleward. In the Eastern Pacific, it's moving poleward, Eastern Atlantic poleward. And here over East Asia, the East Asian monsoon, what is it doing? It's hard to say. And there are billions of people who will be affected, and we need to know. So there is much more work to be done understanding this regional shift in the large-scale wind patterns. Dry places will probably get drier, and these changes in the circulation can steer storms, and some places will get drier than you would expect just based off of get drier itself. And some places will get the storms moved to them, and so places will get wetter. Larkin asks, are monsoons shifting? Yeah, monsoon circulations in some places are shifting, and just how they shift, as you can imagine, can be very important for people who rely on the monsoon circulations for moisture, for rain, or for heat. And so what do the cuts real quick mean for this research or for me and my students? My funding comes from NASA, NOAA, and the NSF. And as you may have heard if you follow the news, all three are experiencing cuts to earth science funding. Part of my graduate school experience was funded through an educational grant from NSF, and the outreach grants by NSF have all been canceled. And so that the rung in that ladder has been removed. My most recent proposal with NASA, I submitted it last May. I was hoping to hear back by January or March. And I'm still waiting to hear back on that, and it's been delayed. Not sure why. And what don't we know about the monsoons, Failurson? Thanks for asking. We can tell you that the rainy seasons of mini monsoons will probably be stronger, but they will be shifting where they are occurring a little bit, and that's still a bit of an open question. And what do cuts mean for this research like this? Well, an important organization is NOAA, the National Oceanographic and Atmospheric Administration. It's part of the Department of Commerce. I mentioned the history of sailing, right, and commerce. NOAA has its origin in sailing and commerce. We really need to know what the weather is going to be like if we're going to send stuff across the ocean on boats. And so that's where NOAA came from. It's part of the Department of Commerce. Well, NOAA has the weather satellites. It has the weather balloons. It has the weather radars. They launched the weather balloons. They have the models that give you the forecasts that your weather apps then read, and interpret for you. They have the staff, the National Weather Service forecast officers all around the country. They have the expertise to understand what the models are showing and what that might actually mean where you and I live. And they also have the data archiving. On the right panel here, I have what's the most efficient way to store boatloads of weather data is still actually on magnetic tapes. And so there's a robot arm there. And if you need to retrieve a whole bunch of data, there are actually whole buildings where they just have tapes and robots that go around, and you choose a file and that robot goes and finds the tape and rewinds or fast forwards to that file. It's expensive to keep data like this. And NOAA does it for free. So if you're a researcher like me and you want to understand how climate's changing, you need decades of data, and NOAA archives the data. Now, there are private models for launching weather satellites or for running weather models, but I don't know of any private model for backing up decades of weather and climate data. There's just not a lot of money to be made in that for the near term, but it's in all of our interest to have that data so we can continue to do this research and better understand what to expect in the future. So that's how my research stands to be affected. But there are big questions ahead. And I have some students that have recently graduated and moved on to Colorado or Chicago, and they're doing exciting work. And I'm excited to someday bring on more students and push this work further forward. Thank you.
Thank you so much, Paul. That was excellent. I know you were monitoring the chat as you were presenting somehow. Again, you are completely set up to just like be your own one-person TV show. But I want to make sure you saw this comment from Imbilby that said, I love that scientists tell us we don't know, but we won't stop trying to find out, and we'll take you with us. That energy, I totally felt from your presentation. I'm going to take a minute to answer a comment very selfishly that is in my area of interest, and then I'm going to ask you one question before you go. So Isabel said a while back, that's actually so fascinating to see how the weather patterns shaped how some of our history happened. I've never put two and two together that way. Isabel, I'm going to drop the name of an article into the chat. It's called How Presidential Elections Are Impacted by a 100-million-year-old Coastline. I know that's not exactly weather, but since I'm a marine person, I just am fascinated by how habitat and nature affect current events, politics, that kind of stuff. So I'm just going to put this article title in there if anybody wants to know. Paul, the question that I'm going to ask you comes from Astra H. While deserts are not habitable to humans or our crops, they are still a vital biome home to many species. Can you explain why or how desertification harms global biodiversity or humans?
Yeah. So if you look at human history and beyond, say like the last 800,000 years in ice cores, we can see the carbon dioxide levels haven't been as high as they are today, not even close. And so anytime you have a change in biomes or a change in habitat that occurs on the scale of years to decades, the wildlife and the ecosystems have a very hard time adapting. If changes occur over hundreds of thousands of years, they don't really, the animals don't mind. They just live their lives as usual and do their thing. But when it happens over years to decades, this is what you call an ecological disturbance. And that destroys ecological capital that you and I rely on. And it makes things really tough for species, especially specialists that live in very particular biomes. As these biome shifts, they shift faster than the plants and animals can move or adapt.
Thank you so much. So it is 6:01 our time. Thank you so much for giving your presentation at this time of day, bringing your professional energy, and I will let you go. I'll see you around, Virginia. I hope. All right. If you have been here with me for the past hour and you're going to stay for a little bit, you'll notice potentially some background noise. Again, somebody mentioned it earlier that we are all doing cozy science from where we live, and I work from home, and I am home now. And so my family's going to start to wake up and get ready for school. I will be muted when that is a thing. But also this is how science works, is we're all just people out here doing our best. And for many of us in the science profession, it's a career of passion, not a career of I don't know what else. I don't know what else it would be besides a career of passion, just because we're here because we love it. So we are starting hour 18 of this live stream. We have, what is math? It's so early in the morning, 82 hours to go, which sounds daunting, but this is my last hour as host for today. If you want to see me again, I will be hosting tomorrow in the same time block and Saturday and Sunday the same time block. So if you like this vibe and you like the cozy science, come back. I do not have the strength to do the hour calculations to get you there, but 5 to 7 Eastern time, that's when I'll be here for the next few days. So right, we're in hour 18 of this live stream, 82 hours to go. I just want to take the time to remind y'all all why we are all here. We know how important weather and climate forecasts are to people in the US, but also everyone in the chat. Y'all are here globally, which is so exciting. I did a sound off last hour. Do y'all want to tell me where you're here from? I'd love to see who's come in, who's rotated off. So tell me where you're from. So we know how important weather and climate forecasts are to everyone globally. And luckily, the United States has long been a world leader in weather and climate prediction. We developed the first computerized weather forecast to help everyone know what to expect in the coming days and weeks. And we made the first computer models of the climate impacts of carbon pollution, so we can all know what to expect in the decades to come, although with the details still in the air, as we just saw in the last talk. To make these forecasts work, we've created an unparalleled network of observations using everything from weather stations to satellites, planes, balloons, floats, boats, and then magnetic tapes. Again, I'm learning so much just by hosting this live stream and being here with y'all. Oh, I'm seeing so many people, so many locations. I'm getting distracted from the mission. St. Louis, Northern Midwest. Oh, we're getting more people from the US. Denmark, Australia, UK, Spain, New Jersey, now living in Tel Aviv. I love that y'all are from everywhere. This support is so great. But I have to be serious for a second. I was talking about the importance of forecasts. The resulting forecasting and observation system is a true scientific miracle, and we're excited to share some of that miracle here with y'all today. I have been learning so much. This miracle was made possible by decades of investment by the American public, which is some of you in the chat right now. But in recent weeks, funding cuts have put the miracle at risk. Weather stations are so short-staffed that we're losing our observational coverage, which is already hurting our forecasts. Laboratories dedicated to understanding our climate's future are being closed or shrunk, and funding for our basic understanding of the weather and climate is disappearing. And I just want to emphasize, Paul mentioned in the last talk that the future is at risk when our students are impacted by funding, and people like Paul cannot take new students like they might otherwise with these funding cuts. It does not have to be this way. If you like what you see here on the live stream, then we ask you to please use the link on your screen. It's in the description for this live stream. I know Kelly's been posting it in the chat the whole time that I've been here. And people in the US can contact their representatives and tell them to save our forecasts. You have all that you need to act if you follow the links. You don't have to come up with any of this stuff yourself. You don't have to be a weather or climate expert to say that you think this is an important thing that should be funded by the government. If you are not in the US, talking to the people that you know about what's happening, but also just about the importance of science, the more that we all tell the people that we know and love in our trusted networks how we feel about science and whether it's important to us, the more people will know that science is important and maybe feel pretty positive about it. Please spread the word to join the live stream as well, especially if you're learning things and enjoying it. And we hope you just have a good time. I'm here for the next hour. And again, if you want to hang out with me the next couple days, I'll be here during the same time slot. Okay, so it is officially 6:30 East Coast time, which is where I am. I was scrolling back through your comments, and again, France, Denmark, Europe, Australia. I think someone's still here from India. Y'all are fantastic. I love that you are so, so amazingly supportive, and I am feeding off of your energy so much. I know I saw a comment, and Bilby, you have been just killing it with the comments. I've been scared to read and watch climate science communications for a long time. This event has completely flipped this for me. I'm so glad that we can be here kind of publicly visible to provide positivity and unity, because this is what I see. I'm a science communicator, and this is what I see behind the scenes all the time. Nobody got into this career path, and honestly, in the circles that I run in with other career paths, like, people are always working to make it better, but we don't always get to see it in public, partly because it's just too much work. You can't always show all your work to everyone, but also sometimes people don't need to know the back end of a live stream and how it works. Somebody mentioned that earlier in the chat, and I was talking about how I have 4 different tabs open on two screens. So if y'all do want to know the inner workings, we have a few minutes when I can talk to y'all about how we're pulling all of this off. I just want to emphasize, climate change needs great community. Thank you. I am a science communicator. I can tell you a little bit about me if you want to know. I haven't really done that besides saying the background noise is my family getting ready for the day. Yeah, I just want to emphasize that, I think one of the biggest challenges for me has been combating feeling kind of alone and like having the funding situation in the US not match what I feel it should be. And every time I feel that way, like I'm so used to that feeling because I have a PhD in ecology, and there's a whole thing for ecologists, especially called, I can't remember the name of it right now because it's 6:32 a.m. and I've been awake for 2 hours now, here with y'all for an hour and a half. It's so early, but there's a particular type of mental distress that you get when you're a scientist and you understand the details of how the world is changing and making it potentially in some places more difficult for humans to live, but you can't immediately change that. So just learning to cope with that kind of feeling, understanding the ins and outs, and learning to, cultivate hope like it is a resource, learning to find the people that will again, do that fighting and do that talking to make the world a better place. I get to do that as my job. And I'm so excited that we can bring that to y'all today. I love y'all are guessing the name for this thing in the comments: existential dread, existential frustration. I mean, yes, it is those things, but there's a specific name. I think it's people call it eco-anxiety, but there's another form of it that's elevated. And they started recognizing and documenting actually years ago how some scientists were exhibiting symptoms that are like PTSD, because again, it's intimately caring about humanity and knowing that some of the things that are happening in the world make it harder for humans to live on this planet, and then not being able to like march over to some place that's being affected and demand to speak to the manager and then change it immediately. Okay, so let's see. I am going to, y'all are getting me too excited. I keep doing this. I am excited to see you. I'm excited that we're all together. I love the vibes in the chat, but I have to do the serious business of this live stream, which is remind you of our mission and why we are all here. So let's see. We are in hour 18. We are halfway through hour 18. That means we have 81 and a half hours left to go. We have another great talk lined up for you next. But before we begin, we know how important weather and climate forecasts are to you and everyone in the US and also in the world. And we want to emphasize the important role that US climate science has played for knowing what's happening in the world, not just in the US, but the world over. US scientists have been leaders in weather and climate predictions, which is much harder than just understanding what's happening right now. And that investment has been brought about by dollars and also support from the public in the US. But now funding cuts are affecting all areas of weather and climate science and the future of how we run the things that we've been running for decades. If you want to take action, there is a link in the description of this video. You do not have to be an expert in weather or climate science. It has everything you need if you are in the US to call your representatives and urge them to support weather and climate science and the way that science gets done in this country. If you are not in the US, or even if you are, one of the most powerful things that we can all do is talk to the people that we know, the people that trust us, about how we feel about the importance of science, weather, climate, and all this. And then having these conversations means that everybody might feel a little bit more supportive of all this stuff. So I'm going to shift us to our next speaker, who is Dan Chavas. Am I saying your last name correctly? Can you say it yourself?
Chavas.
Chavas. Okay, my apologies. I am in New Jersey. It's 6:36 in the morning for me. Where are you and what time?
I'm in Indiana, also 6:36.
Okay, well, I'm going to hand it to you since you have woken up specifically to be here, I assume. Thank you so much, and take it away.
Great. Thanks, Virginia. Thanks to all the organizers for this great event. This is really awesome. So I'm happy to be participating in it. Yeah, so I'm Dan Chavas. I'm a professor of Earth, Atmosphere, and Planetary Sciences at Purdue University. So the title of my talk is just titled Hurricanes and Tornadoes from Hazard to Home. This is a video from, what you're seeing here is video from the catastrophic flooding in Asheville, North Carolina during Hurricane Helene last fall. This is in September of 2024, where Helene dumped kind of prodigious amounts of rain in and around Asheville and also caused widespread damage across the southeast U.S. So, I'm going to talk a little bit more about Helene in a moment. So briefly about myself, where I'm coming from. I grew up in Madison, Wisconsin. This is me as a little kid. And a formative event in my life, and that a lot of other folks, whether they study weather or not, often have had similar types of events, especially in the US. Those blue markers with the arrows pointing is extreme wind reports from a severe thunderstorm outbreak. When I was 5 years old, a tree fell in my house, or 4 years old, and a tree fell in my house during a thunderstorm. It's one of my earliest memories that got me into the weather. I'm now at Purdue. It turns out I found out that this is actually still today the largest tornado outbreak in Indiana state history. So I'm in Indiana now. And so I have a deep connection going back to my childhood that got me into the weather. So what do? So I study hurricanes, severe thunderstorms, and tornadoes. I study how they work and also how we can better predict their hazards and their impacts. So I work on the physics and also try to link those things to hazards and impacts. So this is background here. Now you got to see the damage from flooding from Helene before. This is now a satellite view in this video of Hurricane Helene. The top left, it says what category it is as it's strengthening. It's over the Gulf of Mexico. And whoops, and I paused it. Let's see if I can, oh no. See if I can get it again. I will not touch the screen. So you're seeing, looking down from space where we have all these satellites, which is a remarkable feat of human achievement to put satellites in space so we can be constantly observing, having eyes in space, looking down at our planet at all times. So you're seeing the tops of clouds, probably something like 15 kilometers above the surface. And you can start to see the swirl in these cloud tops where as Helene is developing. You can see Cuba just to the east there. This is at nighttime, so now you're seeing city lights at the surface. And you're starting to see it bubble up and swirl, these little blobs of white clouds starting to swirl faster and faster as Helene moved northward across the northern Gulf of Mexico and approaching Florida. You can see Louisiana to the west there, the coastline, and then here, now you can really see it right as Helene. This is a Category 3 hurricane, and it was intensifying as it approached land and then slammed into the Big Bend region of Florida. Again, this was last September. So, and then eventually it moved inland and actually moved west into the Appalachian Mountains, which is where it becomes harder to tell on the satellite, but eventually that's where it dumped a lot of rainfall, particularly within the Appalachians in western North Carolina. So let's just give you a flavor of what a hurricane looks like from space. So hurricanes and tornadoes continue to kill people frequently. This is at the top is a chart of hurricane deaths from 2000 to 2024. Where you can see there's this big yellow bar from 2005, which is mostly from Katrina. For the year we had Katrina, we had over 1,400 deaths, principally in and around the New Orleans area. But you can see that in many years we still have fatalities, and 2024 is actually an especially deadly year, the deadliest since 2005. We had 324 deaths across 4 different hurricanes that made landfall. So Helene was the one I just showed you, was the biggest one with 251. But Beryl killed 44 people, Debbie 18, and then Milton, which was another one that was pretty high profile. It hit Florida, killed 11 people. So hurricanes continue to be deadly, and it's something that we're trying to work on reducing this, both scientifically and for society. And on the bottom is tornadoes. So tornado deaths also oddly has one year that was really, really bad in the last 2011. It had over 500 deaths. There's a super outbreak in particular across the southeast that killed lots of people. And last year was also a relatively deadly year for the US. We had 54 deaths. The biggest event was in Iowa. There was an EF4 in Greenfield, Iowa that killed 7 people, EF4 tornado. So tornadoes in particular, often can, really intense ones, can annihilate whole towns or at least parts of towns, and unfortunately continue to take lives. So that's some of the motivation for what I do, and I'm going to talk more about that. In general, what I've done is my science has been strongly funded by federal sources, in particular the National Science Foundation, as well as some funding from NASA and from NOAA. So hopefully I'll make the case here for why some of that funding has been really beneficial for society. So I'm going to talk mostly about hurricanes here, and one particular aspect of what I work on in hurricanes. Come back to tornadoes briefly at the end. And I want to talk first about Helene. That's something that's also in its own right a success story of science for the last several decades. Is that Helene formed in the Gulf of or in the Caribbean, south of Cuba, and actually before it even existed, we had computer models that told us almost exactly where it was going to go 4 days later. So this is a map of the first time we knew Helene existed. This is a forecast from the National Hurricane Center, with the black line as the track of the hurricane where we thought it was going to go. And this is every 12 hours going forward. And then the letters on here are depression, tropical storm, hurricane. So we knew it was going to intensify. And then you can see where we thought it was going to make landfall and then eventually turn left into the Appalachians. And the big yellow X is the actual landfall point. So this is incredible, an incredible feat of science that before a hurricane even existed, we could know not only that it was going to form, that it was going to intensify, but almost exactly where it was going to go. So this is an amazing job by the National Hurricane Center, as well as by our computer models. But this is something 70 plus years ago. Sometimes we had hurricanes that we didn't even know existed before they hit us. So we've really done an incredible job of advancing the science of how hurricanes move, even how they intensify. But so ultimately it was still catastrophic, which is really, really unfortunate. So just because we knew the hurricane was going to be there and where it was going to go doesn't necessarily mean that we could prevent its impact on society. So at the end of the day, it's really, I love the weather. We study the weather, and I'll make the case for why we need to study the weather and the science and physics of the weather. But it's really about how the weather impacts our lives. That is a big motivator for why we want to study the weather, why we fund the weather, or what fund weather and climate science in general. So these are examples actually from, let's see if I can get these to play. This might be a lot to have them all play at once. Maybe it is. Well, these are videos. These are all images and or videos from Hurricane Milton, actually, but just as examples of wind can cause damage. So on the top left, this is Tropicana Field in Tampa Bay, where the roof was torn off. And I believe the team can't play this season, or at least early in the season, in the stadium. And then storm surge, which is just water being pushed on shore as the wind blows on shore from over the ocean, is just pushes water onto the shore and inundates the near coastal environment. And the bottom left, actually that's from Helene, is rainfall-induced flooding, is that hurricanes bring lots and lots of rain, which if you dump all that rain out over enough time, and especially in the presence of topography, you can funnel all that water into localized areas that can completely inundate communities. So, and then the bottom right is something that's actually less frequent, but was a big deal for Hurricane Milton, was that hurricanes can often cause tornadoes, and occasionally they can cause strong tornadoes. And so Hurricane Milton, let's see if I can get this one to run. Nope. All right. Let's see here. They can cause tornadoes, and tornadoes can cause very heavy localized wind damage then as well. So Milton had a few EF3 plus tornadoes that occurred in Florida. So it's really about how these impact our lives, take our lives, or cause damage to property. So, okay. So I'm going to transition that to talk about then the science, some of the science that I've done. I've worked on these topics in a variety of ways. I want to focus a little bit within this space, particularly for hurricanes, is that knowing the physics of weather in general really helps us better predict its impacts. So this is a silly but I think useful cartoon that I found, I think, on Facebook at some point a few years ago, about a dog being born and then growing bigger and then at its current state in the bottom left. And then if you try to just project it out without any real knowledge of how a dog works, you would get this ridiculous, silly looking thing in the bottom right that nobody would believe. And so the point is that when we do forecasts, whether it's on weather for tomorrow and the next day, or it's on longer timescales, if we want to know how how the hurricane season or tornado season will be in the coming months, or the upcoming season, or even longer term as the climate changes, we really need to understand how the system works, how the dog works, to be able to give trustworthy forecasts. You can't just extrapolate out into time based on past data, because that may give you something that doesn't make any sense. So like the dog is like the weather, but the weather much more impactful, and that's what we want to be able to understand in the end. So for a hurricane, the ways that hurricanes impact our lives through the hazards of wind, of storm surge, of rainfall and flooding, these are all physical hazards. And they're ultimately driven by the wind field, the low-level wind field of the hurricane itself. So we may think, obviously, wind is the first thing that comes to mind for a hurricane. You know that it's super windy outside, and it can knock down trees, knock down power lines. But the wind is also, as I mentioned, pushes water on shore through storm surge. And it's also very important for determining where and how heavily rain is falling in and around the storm. So they're all driven by the wind field. And so physics, something that I've worked on really for my whole career thus far, is that physics has allowed us to create a very good model of the hurricane winds along its track. So this is just an example from my model, a model that we published about 10 years ago now, that I'll be talking about is from Hurricane Katrina, just showing a footprint, what we call a footprint of the winds of a storm. And so you can model this quite well and get a very good estimate of the wind field, which then may mean you'd be able to get a good estimate of all of the hazards in a hurricane. So we can use this model, and we have in a variety of ways to predict things like the exposure to extreme hurricane winds. And so this is from a paper from last year where my colleagues mapped out basically the total exposure to extreme winds globally. So this is a model that we can use not just for the US, but for the whole world to try to understand where on Earth are there populations that may face extreme winds from hurricanes. And then also what we did was to look at the demographics of those populations that are being affected, to understand who is most at risk, who's perhaps most vulnerable, who's at risk globally in the face of extreme hurricane winds. We can also use this model to predict hurricane storm surge. So there are some really nice models for storm surge that what you need is a model. It's modeling the water in the ocean and leading up into the land surface, but then all of that again is pushed around by the near surface wind. So you need to force that model with the wind field model. And so you can do that. There's a few models to do this, but and this is too sciencey of a plot, but just what we're able to do is to go back and say for every single US hurricane landfall that's happened over the last 70 years, we can actually run a simulation of storm surge using this model and compare it to the observed peak storm surges that happen. And we can do a really good job all around the US coastline, which means this is a model that now we have a way to simulate surge quite confidently, and again, almost anywhere in the world, but we can do this for forecasting, we can do this for longer term risk assessment, so that's really nice. And then additionally, we can do this for hurricane rainfall. So on the left is a map of satellite observed mean annual hurricane rainfall. So on average each year, how much rain do you see from a hurricane? So the reds are more rainfall. So you can see the peak is in the South Carolina region. But generally the Southeast US gets a reasonable amount of rainfall each year from hurricanes. And so you can actually take a rainfall model that's also based on the physics of rainfall that takes in also a wind field at the surface. And so we can force that with our wind field model, again, for all US hurricane landfalls, and simulate the rainfall from all of these hurricanes. And you get a map that looks very similar on the right to what you get on the left. This is really amazing. These are relatively simple models, but we're able to simulate the rainfall in hurricanes, which again means you can do this on for forecasting purposes. You can do this for longer term risk assessment anywhere. So it's pretty remarkable. And then you can go one step further and actually take all of these pieces of modeling the wind speeds, modeling the storm surge, and modeling the rainfall, and actually look at, try to predict the county level hurricane economic damage for the United States. And something that was actually, we were just published with my colleague Abby Gori as the lead. And so what we're doing is you can compare this then to county level damage estimates. And it's not perfect by any means. There's a lot of other things going on when it comes to economic damage, but it's actually remarkably good at predicting this at a fine spatial scale. You can do this, which is pretty amazing. So again, we're going all the way from basic physics of hurricanes to economic damage at local scales. So all driven by our wind field model. And then additionally, we can go kind of at the other end, is that we have ways to predict aggregate hurricane economic damage. So those of you who maybe have, whether or not you study hurricanes, you may have heard of the categories 1, 2, 3, 4, 5 for hurricanes. So Helene, I believe, was a 3 or a 4 at landfall, I already forgot. Higher category means stronger winds, that's how it's defined. But recently, over the last few years, we've realized that a second way we define the intensity of a hurricane, the minimum pressure at the center of the storm instead of the maximum wind, is actually a better predictor, and a shockingly good predictor of total economic damage from a hurricane from the United States. And this is 1988 to 2021, a rank correlation between the two. And so it's much better than the maximum wind speed. And because of our understanding of the physics of the hurricanes, we're actually able to understand why this is, which is that the minimum pressure captures is a representative measure of both the maximum wind speed and the size of a hurricane. So a bigger hurricane causes more damage than a smaller one, all else equal. And so we've since also developed a really simple model based on the physics of the wind field to predict this minimum pressure from maximum wind speed and storm size as well. And so this is really exciting. This means that this is something that we now have a really simple tool to predict something that we know is a better representative measure of potential impacts from hurricanes. This is something the National Hurricane Center now is thinking about how to communicate better. But what this means is that we can make better forecasts, communicate the potential impacts better, so that you or individuals in your community can better protect life and property, which is really nice. So we're going all the way from physics, from basic physics, all the way into impacts and risk and even response to these events. So yeah, okay, so just a little bit briefly about science still to come, which is where the funding really continues to be important. Going back to this movie of the satellite view looking down from space at Hurricane Helene, a really notable aspect of Helene's evolution that you may be able to get a sense from here, I tried to trim this down, is that during about a 24-hour period just prior to landfall, Helene nearly doubled in size. Its wind field expanded rapidly in size in just a day. And that, without question, made Helene's wind and storm surge and flooding all dramatically worse. Bigger storm just has a bigger footprint of all of these hazards. And so it made all of its impacts much worse. And so something that this is a topic I've been working on for my whole career, but we've really recently cracked the code on what controls storm size and what controls changes in storm size. And so now we're developing simple models to predict these types of events as well, so that we can better predict, not only understand, but better predict how changes in size may then translate to changes in their impacts for communities across the US. And second, just a second one is going back to tornadoes. So severe thunderstorms and tornadoes, again, mentioned at the beginning, have taken hundreds of lives. And it's actually become the leading cause of the number of billion-dollar disasters over the last 15 years over the US. So severe weather has really become a really big deal. This is a video you're seeing from the total utter devastation from the Mayfield, Kentucky EF4 tornado last year. So this was pretty close to where I live. And so tornadoes can just cause absolute destruction to communities when they hit them. And unfortunately, we've had several of those this year as well. And so the map on the left is just showing you the distribution of intense tornadoes, which covers pretty much everywhere east of the Rockies, can have an EF3 plus tornado at some point during the year. And so some recent work that we've also done is deciphered the physics of these severe thunderstorms, so we can predict how strong they can be. And this is just the thunderstorm part. The tornado part we have not solved. There's lots about tornadoes that we still do not understand. But we've made a big jump in our physical understanding and the theoretical understanding of how thunderstorms work in general, and particularly severe thunderstorms. That's something that we believe we can use this tool to improve our forecasts of severe thunderstorms and hopefully of tornadoes as well. Again, so that we can better protect people and their loved ones to stay safe and be able to respond more quickly to protect themselves before these things hit their communities. So with that, I'll just end to go back to this Helene video and just point out that, again, these are funding for all of this science from NSF, from NASA, from NOAA, our choices to support federal or to fund science writ large really have a lot of benefits and have had a lot of benefits over the last 100 years, really, to making society more prepared and more able to deal with everything that weather in our country throws at us each year. So with that, I'll just say thank you very much.
Thank you, Dan. So we have only like 1 minute for questions. So I have 2 rapid fire if you're up for it. Number one, I just want to do a check. There was a lot of chatter in the comments about the difference between a hurricane and a cyclone. Is that just naming based on location?
Yeah, so cyclone is a very general term. So technically, as just a spinning weather system. So technically, a tornado is a cyclone. The low pressure weather systems that we get in the mid latitudes over the U.S., for example, or in Europe and Asia, those are called extratropical cyclones. So cyclone's very general. A hurricane is what we call the more general term for tropical cyclone, which is different than the mid-latitude cyclones. And so we call them hurricanes over the Atlantic and East Pacific. They're typhoons in the West Pacific, and some, I think Australia, India refers to them as cyclones in general. So yeah, tropical cyclone is probably the most general term.
Fantastic. And in like 20 seconds, people were asking about whether the predictions for this hurricane season for the U.S. are meant to be active, if people are predicting active. So yes or no, or medium. And then where can people go to learn more?
Sure. Yeah, above normal is expected. It's the Atlantic is warmer than normal, and that's the Atlantic SSTs. So our sea surface temperatures are a little bit warmer than normal, and so that generally promotes tropical or an active hurricane season. El Nino and La Nina are the other component, and that's neutral right now, so that's not expected to change things. Yeah, you can learn more. I guess. You can Google NOAA or the Colorado State team. There's a couple other folks that have great seasonal forecasts, and you can read about their expectations moving forward. So yeah, just Google seasonal forecasts. So
thank you so much. I know that was rapid fire. I am going to let you go. I really appreciate you being here. That was so informative. People loved the talk in the comments. I hope you have a great day.
All right. Thanks so much, Virginia. Take care, everyone.
Okay, everyone, we are nearly at the top of the hour. If you notice, this live stream has been going for nearly 8 hours, but we are almost done with hour 18 of this entire 100-hour live stream. Those numbers don't match, and that's because there's a cap on how long we can have a single live stream going on YouTube at any given moment. So we are actually going to reset the stream. I will not be your host when you come back, but if you want to hang out with me again or tell your friends that I'm a friendly person, I will be doing the same time block tomorrow and Saturday and Sunday, so 5 to 7 Eastern time. I'll be giving my talk about my science Saturday morning, 7 a.m. Eastern time. It has been just a delight to wake up super early and be here with y'all. And I'm going to take a quick selfie so I can post about this on social media before I go. So everyone say cheese, yay! And that's it. So you will have the link to rejoin after the reset on your screen in the comments. And I hope to see y'all again in just a couple of minutes. You will have access to that live stream. Don't worry if you get there before it's actually officially started. It just takes a little bit to coordinate something this big. Have a great day wherever you are. Hope to see y'all again. Been a delight. Bye for now.